Chapter 14 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a recording by Paul King, pjk.scripts.mit.edu/pkj. A short account of the history of mathematics, Chapter 14. Features of modern mathematics. The division between this period and that treated in the last 6 chapters is by no means so well defined as that which separates the history of Greek mathematics from the mathematics of the Middle Ages. The methods of analysis used in the 17th century and the kind of problems attacked changed but gradually, and the mathematicians at the beginning of this period were in immediate relations with those at the end of the last considered. For this reason, some writers have divided the history of mathematics into 2 parts only, treating the schoolmen as the lineal successors of the Greek mathematicians, and dating the creation of modern mathematics from the introduction of the Arab textbooks into Europe. The division I have given is, I think, more convenient, for the introduction of analytical geometry and of the calculus completely revolutionized the development of the subject, and it therefore seems preferable to take their invention as marking the commencement of modern mathematics. The time that has elapsed since these methods were invented has been a period of incessant intellectual activity in all departments of knowledge, and the progress made in mathematics has been immense. The greatly extended range of knowledge and the rapid intercommunication of ideas due to printing increase the difficulties of a historian, while the mass of materials which has to be mastered, the absence of perspective, and even the echoes of old controversies combine to make it very difficult to give a clear and just account of the development of the subject. As, however, the leading facts are generally known, and the works published during this time are accessible to any student, I may deal more concisely with the lives and writings of modern mathematicians than with those of their predecessors, and confine myself more strictly than before to those who have materially affected the progress of the subject. Roughly speaking, we may say that 5 distinct stages in the history of this period can be discerned. First of all, there is the invention of analytical geometry by Descartes in 1637, and almost at the same time the introduction of the method of indivisibles, by the use of which areas, volumes, and the positions of centres of mass can be determined by summation in a manner analogous to that effected nowadays by the aid of the integral calculus. The method of indivisibles was soon superseded by the integral calculus. Analytical geometry, however, maintains its position as part of the necessary training of every mathematician, and is incomparably more potent than the geometry of the ancients for all purposes of research. The latter is still no doubt an admirable intellectual training, and it frequently affords an elegant demonstration of some proposition the truth of which is already known, but it requires a special procedure for every particular problem attacked. The former, on the other hand, lays down a few simple rules by which property can be at once proved or disproved. In the second place, we have the invention of the fluxional or differential calculus about 1666, and possibly an independent invention of it in 1674. Wherever a quantity changes according to some continuous law, and most things in nature do so change, the differential calculus enables us to measure its rate of increase or decrease. And from its rate of increase or decrease, the integral calculus enables us to find the original quantity. Formerly, every separate function of x, such as 1 plus x quantity to the power n, or the logarithm of 1 plus x, the sine of x, or the arctan of x, etc., could be expanded in ascending powers of x only by means of such special procedure as was suitable for that particular problem. But by the aid of the calculus, the expansion expansion of any function of x in ascending powers of x is in general reducible to one rule which covers all cases alike. So again the theory of maxima and minima, the determination of the lengths of curves and the areas enclosed by them, the determination of surfaces of volumes and the centers of mass, and many other problems are each reducible to a single rule. The theories of differential equations, of the calculus of variations, of finite differences, etc., are the developments of the ideas of the calculus. These two subjects, analytical geometry and the calculus, became the chief instruments of further progress in mathematics. In both of them, a sort of machine was constructed to solve a problem. It was only necessary to put in the particular function dealt with, or the equation of the particular curve or surface considered, and on performing certain simple operations the result came out. The validity of the process was proved once and for all, and it was no longer requisite to invent some special method for every separate function, curve, or surface. In the third place, Huygens laid the foundation of a satisfactory treatment of dynamics, and Newton reduced it to an exact science. The latter mathematician proceeded to apply the new analytical methods not only to numerous problems in the mechanics of solids and fluids on the earth, but to the solar system. The whole of mechanics, terrestrial and celestial, was thus brought within the domain of mathematics. There is no doubt that Newton used the calculus to obtain many of his results, but he seems to have thought that, if his demonstrations were established by the aid of a new science which was at that time generally unknown, his critics, who would not understand the fluxional calculus, would fail to realize the truth and importance of his discoveries. He therefore determined to give geometrical proofs of all of his results. He accordingly cast the Principia into a geometrical form, and thus presented it to the world in a language which all men could then understand. The theory of mechanics was extended and was systematized into its modern form by Laplace and Lagrange toward the end of the 18th century. In the fourth place, we may say that during this period the chief branches of physics have been brought within the scope of mathematics. This extension of the domain of mathematics was commenced by Huygens and Newton when they propounded their theories of light, but it was not until the beginning of this century that sufficiently accurate observations were made in the most physical subjects to enable mathematical reasoning to be applied to them. From the results of the observations and experiments which have been since published, numerous and far-reaching conclusions have been obtained by the use of mathematics, but we now want some more simple hypotheses from which we can deduce those laws which at present form our starting point. If, to take one example, we could say in what electricity consisted, we might get some simple laws or hypotheses from which, by the aid of mathematics, all the observed phenomenon could be then deduced, in the same way as Newton deduced all the results of physical astronomy from the law of gravitation. All lines of research seem moreover to indicate that there is an intimate connection between the different branches of physics, e.g. between light, heat, electricity, and magnetism. The ultimate explanation of this and of the leading facts in physics seems to demand a study of molecular physics. A knowledge of molecular physics in its turn seems to require some theory as to the constitution of matter. It would further appear that the key to the constitution of matter is to be found in chemistry or chemical physics. So the matter stands at present. Helmholtz in Germany and Maxwell and Lord Kelvin, Sir William Thomson, in Great Britain have done a great deal in applying mathematics to physics, but the connection between the different branches of physics and the fundamental laws of those branches, if there be any simple ones, are riddles which are not yet solved. This history does not pretend to treat of problems which are now the subject of investigation, and though mathematical physics forms a large part of modern mathematics, I shall not discuss it in any detail. Fifthly, this period has seen an immense extension of pure mathematics. Much of this is the creation of comparatively recent times, and I regard the details of it as outside the limits of this book, though in chapter 19 I have allowed myself to mention some of the subjects discussed. The most striking features of this extension are the developments of higher geometry, of higher arithmetic, or the theory of numbers, of higher algebra, including the theory of forms, and of the theory of equations, and also the discussion of functions of double and multiple periodicity, and notably the creation of a theory of functions. End of section 20. Recording by Paul King, pjk.scripps.mit.edu/pkj. Chapter 15 of A Short Account of the History of Mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripps.mit.edu/pkj. A Short Account of the History of Mathematics by W. W. Rouse. Chapter 15. History of Mathematics from Descartes to Huygens, circa 1635 to 1675. I propose in this chapter to consider the history of mathematics during the 40 years in the middle of the 17th century. I regard Descartes, Cavalieri, Pascal, Wallis, Fermat, and Huygens as the leading mathematicians of this time. I shall treat them in that order, and I shall conclude with a brief list of the more eminent remaining mathematicians of the same date. I have already stated that the mathematicians of this period, and the remark applies more particularly to Descartes, Pascal, and Fermat, were largely influenced by the teaching of Kepler and Desargues, and I would repeat again that I regard these latter and Galileo as forming a connecting link between the writers of the Renaissance and those of modern times. I should also add that the mathematicians considered in this chapter were contemporaries, and although I have tried to place them roughly in such an order that their chief works shall come in chronological arrangement, it is essential to remember that they were in relation with one another, and in general were acquainted with one another's researches as soon as they were published. Descartes. Subject to the above remarks, we may consider Descartes as the first of the modern school of mathematics. René Descartes was born near Tours on March 31, 1596, and died at Stockholm on February 11, 1650. He was thus a contemporary of Galileo and Desargues. His father, who as the name implies was of a good family, was accustomed to spend half the year at Rennes when the local parliament in which he held a commission as a councillor was in session, and the rest of the time on his family estate at Les Cartes at La Haye. René, the second of a family of 2 sons and 1 daughter, was sent at the age of 8 years to the Jesuit school at La Flèche, and of the admirable discipline and education there given he speaks most highly. On account of his delicate health he was permitted to lie in bed till late in the morning. This was a custom which he had always followed, and when he visited Pascal in 1647 he told him that the only way to do good work in mathematics and to preserve his health was never to allow anyone to make him get up in the morning before he felt inclined to do so, an opinion which I chronicle for the benefit of any schoolboy into whose hands this work may fall. On leaving school in 1612, Descartes went to Paris to be introduced to the world of fashion. Here, through the medium of the Jesuits, he made the acquaintance of Midorge, and renewed his schoolboy friendship with Father Mersenne, and together with them he devoted the 2 years of 1615 and 1616 to the study of mathematics. At the time, a man of position usually entered either the army or the church. Descartes chose the former profession, and in 1617 joined the army of Prince Maurice of Orange, then at Breda. Walking through the streets he saw a placard in Dutch which excited his curiosity, and stopping the first passer asked him to translate it into either French or Latin. The stranger, who happened to be Isaac Beekman, the head of the Dutch college at Dort, offered to do so if Descartes would answer it, the placard being in fact a challenge to all the world to solve a geometrical problem there given. Descartes worked it out within a few hours, and a warm friendship between him and Beekman was the result. This unexpected test of his mathematical attainments made the uncongenial life of the army distasteful to him, but under family influence and tradition he remained a soldier, and was persuaded at the commencement of the 30 Years' War to volunteer under the court at Bucquoy in the army of Bavaria. He continued all this time to occupy his leisure with mathematical studies, and was accustomed to date the first ideas of his new philosophy and of his analytical geometry from 3 dreams he experienced on the night of November 10, 1619, at Neuburg, when campaigning on the Danube. He regarded this as the critical day of his life, and one which determined his whole future. He resigned his commission in the spring of 1621, and spent the next 5 years in travel, during most of which time he continued to study pure mathematics. In 1626 we find him settled at Paris, a little well-built figure, modestly clad in green taffety, and only wearing a sword and feather in token of his quality as a gentleman. During the first 2 years there he interested himself in general society, and spent his leisure in the construction of optical instruments, but these pursuits were merely the relaxations of one who failed to find in philosophy that theory of the universe which he was convinced finally awaited him. In 1628 Cardinal de Bray, the founder of the Oratorians, met Descartes, and was so much impressed by his conversation that he urged on him the duty of devoting his life to the examination of truth. Descartes agreed, and the better to secure himself from interruption moved to Holland, then at the height of its power. There for 20 years he lived, giving up all his time to philosophy and mathematics. Science, he says, may be compared to a tree. Metaphysics is the root, physics is the trunk, and the 3 chief branches are mechanics, medicine, and morals, these forming the 3 applications of our knowledge, namely to the external world, to the human body, and to the conduct of life, and with these subjects alone his writings are concerned. He spent the first 4 years, 1629 to 1633, of his stay in Holland in writing Le Monde, which embodies an attempt to give a physical theory of the universe, but finding that its publication was likely to bring on him the hostility of the Church, and having no desire to pose as a martyr, he abandoned it. The complete manuscript was published in 1664. He then devoted himself to composing a treatise on universal science. This was published at Leyden in 1637, titled The Discourse on Method, and was accompanied with 3 appendices entitled Optics, Meteorology, and Geometry. It is from the last of these that the invention of analytical geometry dates. In 1641 he published a work called Meditations, in which he explained at some length his views of philosophy as sketched out in the Discourse. In 1644 he issued the Principia Philosophiae, as a greater part of which was devoted to physical science, especially the laws of motion and the theory of vortices. In 1647 he received a pension from the French court in honour of his discoveries. He went to Sweden on the invitation of the Queen in 1649, and died a few months later of inflammation of the lungs. In appearance Descartes was a small man with a large head, projecting brow, prominent nose, and black hair coming down to his eyebrows. His voice was feeble. Considering the range of his studies he was by no means widely read, and he despised both learning and art unless something tangible could be extracted therefrom. In disposition he was cold and selfish. He never married and left no descendants, though he had one illegitimate daughter who died young. As to his philosophical theories, it would be sufficient to say that he discussed the same problems which have been debated for the last 2000 years. It is hardly necessary to say that the problems themselves are of great interest, but from the nature of the case no solution ever offered is capable either of proof or disproof, and whenever a philosopher like Descartes believes that he has at last finally settled a question, it has been easy for his successors to point out the fallacy in his assumptions. All that can be effected is to make one explanation somewhat more probable than another. I have read somewhere that philosophy has always been chiefly engaged with the interrelations of God, nature, and man. The earliest philosophers were Greeks, who occupied themselves mainly with the relations between God and nature, and dealt with man separately. The Christian Church was so absorbed in the relation of God to man as to entirely neglect nature. Finally, modern philosophers concern themselves chiefly with the relations between man and nature. Whether this is a correct historical generalization of the views which have been successfully prevalent, I do not care to discuss here, but the statement as to the scope of modern philosophy marks the limitations of Descartes' writings, and they may be taken as the commencement of the modern school. Descartes' chief contributions to mathematics were his analytical geometry and his theory of vortices, and it is on his researches in connection with the former of these subjects that his reputation rests. Analytical geometry does not consist merely, as sometimes is loosely said, in the application of algebra to geometry. That had been done by Archimedes and many others, and had become the usual method of procedure in the works of the mathematicians of the 16th century. The great advance made by Descartes was that he saw that a point in a plane could be completely determined if its distances, say x and y, formed two fixed lines drawn at right angles in the plane, were given, with the convention familiar to us as to the interpretation of positive and negative values, and that though an equation f of xy equals 0 was indeterminate and could be satisfied by an infinite number of values of x and y, yet these values of x and y determine the coordinates of a number of points which form a curve of which the equation f of xy equals 0 expresses some geometrical property, that is, a property true of the curve at every point on it. Descartes assured that a point in space could be similarly determined by three coordinates, but he confined his attention to plane curves. It was at once seen by Descartes and his successors that in order to investigate the properties of a curve it was sufficient to select any characteristic geometrical property as a definition, and to express it by means of an equation between the current coordinates of any point on the curve, that is, to translate the definition into a language of analytical geometry. The equation so obtained contains implicitly every property of the curve, and any particular property can be deduced from it by ordinary algebra without troubling about the geometry of the figure. The points in which the two curves intersect can be determined by finding the roots common to their two equations. I need not go further into details, for nearly everyone to whom the above is intelligible will have read analytical geometry and be able to appreciate the value of its invention. Descartes' Geometrie is divided into 3 books. The first 2 of these treat of analytical geometry, and the third includes an analysis of the algebra then current. It is somewhat difficult to follow the reasoning, but the obscurity was intentional and due to the jealousy of Descartes.
Translated, I omitted nothing, says he, except design. I had expected that people who have any math skill would not fail to say that I had not said anything that has not already been said about the coordinate system, but I have hopefully made this topic more intelligible. The first book commences with an explanation of the principles of analytic geometry, and contains a discussion of a certain problem which has been propounded by Pappus in the 7th book of his Synagogue, and of which some particular cases have been considered by Euclid and Apollonius. The general theorem has baffled previous geometricians, and it was in the attempt to solve it that Descartes was led to the invention of analytical geometry. The full enunciation of the problem is rather involved, but the most important case is to find the locus of a point such that the product of the perpendiculars on M given straight lines shall be in a constant ratio to the product of the perpendiculars on N given straight lines. The ancients had solved this geometrically for the case m equals 1, n equals 1, and the case m equals 1, n equals 2. Pappus had further stated that if m equals n equals 2, the locus was a conic, but he gave no proof. Descartes also failed to prove this by pure geometry, but he shewed that the curve was represented by an equation of the second degree, that is, it was a conic section. Subsequently, Newton gave an elegant solution of the problem by pure geometry. In the second book, Descartes divides curves into two classes, namely geometrical and mechanical curves. He defines geometrical curves as those which can be generated by the intersection of two lines each moving parallel to one coordinate axis, with commensurable velocities, by which he meant that dy by dx was an algebraical function, as for example is the case in the ellipse and the cissoid. He calls the curve mechanical when the ratio of the velocities of these lines is incommensurable, by which he meant that dy by dx was a transcendental function, as for example is the case in the cycloid and the quadratrix. Descartes confined his discussion to algebraical curves, and did not treat of the theory of mechanical curves. The classification into algebraical and transcendental curves now usual is due to Newton. Descartes also paid particular attention to the theory of the tangents to curves, as perhaps might be inferred from his system of classification just alluded to. Then the current definition of a tangent at a point was a straight line through the point such that, between it and the curve, no other straight line could be drawn, i.e., the straight line of closest contact. Descartes proposed to substitute for this that the tangent was the limiting position of the secant. Fermat, and at a later date Maclaurin and Lagrange, adopted this definition. Barrow, followed by Newton and Leibniz, considered the curve as the limit of an inscribed polygon when the sides become indefinitely small, and stated that the side of the polygon when produced became in the limit a tangent to the curve. Roberval, on the other hand, defined a tangent at a point as the direction of the motion at that instant of a point which was describing the curve. The results are the same whichever definition is selected, but the controversy as to which definition was the correct one was none the less lively. Descartes illustrated his theory by giving the general rule for drawing tangents and normals to a roulette. The method used by Descartes for finding the tangent or normal at any point of a given curve was substantially as follows. He determined the center and radius of a circle which should cut the curve in two consecutive points there. The tangent to the circle at that point will be the required tangent to the curve. In modern textbooks it is usual to express the condition that two of the points in which a straight line, such as y equals mx plus c, cuts the curve shall coincide with the given point. This enables us to determine m and c, and thus the equation of the tangent there is determined. Descartes, however, did not venture to do this, but selecting a circle as the simplest curve, and one to which we know how to draw a tangent, he so fixed his circle as to make it touch the given curve at the point in question, and thus reduce the problem to drawing a tangent to a circle. I should note in passing that he only applied this method to curves which are symmetrical about an axis, and he took the center of the circle on the axis. Much of the reasoning in these two books is not easy to follow, but a Latin translation of them with explanatory notes was prepared by F. de Boon, and an edition of this with commentary by F. van Schooten was issued in 1659 and had a wide circulation. The third book of Géométrie contains an analysis of the algebra then current, and it has affected the language of the subject by fixing the custom of employing the letters at the beginning of the alphabet to denote known quantities, and those at the end of the alphabet to denote unknown quantities. Descartes further introduced the system of indices now in use, but I would here remind the reader that the suggestion had been made by previous writers, though it had not been generally adopted, but very likely it was the original on the part of Descartes. I think also that Descartes was the first to realize that his letters might represent any quantities, positive or negative, and that it was sufficient to prove a proposition for one general case, compared to the old procedure. In this book he made use of the rule for determining a limit to the number of positive and negative roots of an algebraical equation, which is still known by his name, and introduced the method of indeterminate coefficients for the solution of equations. He believed that he had given a method by which algebraical equations of any order could be solved, but in this he was mistaken. He made use of the method of indeterminate coefficients. Of the other two appendices to the discourse was one devoted to optics. The chief interest of this consists in the statement given of the law of refraction. This appears to have been taken from Snell's work. But not only is there no acknowledgment of the source from which it was obtained, but it is enunciated in such a way so as to lead a careless reader to suppose that it is due to the researches of Descartes. Descartes would seem to have repeated Snell's experiments when in Paris in 1626 or 1627, and it is possible that he subsequently forgot how much he owed to the earlier investigations of Snell. A large part of the optics is devoted to determining the best shape for the lenses of a telescope, but the mechanical difficulties in grinding a surface of glass to a required form are so great as to render these investigations of little practical use. Descartes seemed to have been doubtful whether to regard the rays of light as proceeding from the eye and, so to speak, touching the object, as the Greeks had done, or as proceeding from the object and so affecting the eye. But since he considered the velocity of light to be infinite, he did not deem the point particularly important. The other appendix on meteors contains an explanation of numerous atmospheric phenomena, including the rainbow. Descartes was unacquainted with the unequal refrangibility of rays of light of different colors, and the explanation of the latter is necessarily incomplete. Descartes' physical theory of the universe, embodying most of the results contained in his earlier and unpublished Le Monde, was given in his Principia 1644 and rests on a metaphysical basis. He commences with a discussion on motion and then lays down 10 laws of nature, of which the first two are almost identical with the first 2 laws of motion as given by Newton. The remaining 8 laws are inaccurate. He next proceeds to discuss the nature of matter, which he regards as uniform in kind, though there are 3 forms of it. He assumes that the matter of the universe must be in motion, and that the motion must result in a number of vortices. He states that the sun is the center of an immense whirlpool of this matter, in which the planets float and are swept round like straws in a whirlpool of water. Each planet is supposed to be the center of a secondary whirlpool by which its satellites are carried. These secondary whirlpools are supposed to produce variations of density in the surrounding medium, which constitute the primary whirlpool, and so cause the planets to move on in ellipses and not circles. All these assumptions are arbitrary and unsupported by any investigation. It is not difficult to prove that on his hypothesis the sun would be in the center of these ellipses and not at a focus, as Kepler had shewn was the case, and that the weight of a body at every place on the surface of the earth except the equator would act in a direction which was not vertical. But it will be sufficient here to say that Newton, in the second book of his Principia in 1687, considered the theory in detail and shewed that its consequences are not only inconsistent with each of Kepler's laws and with the fundamental laws of mechanics, but are also at variance with the 10 laws of nature assumed by Descartes. Still, in spite of its crudeness and its inherent defects, the theory of vortices marks a fresh era in astronomy, for it was an attempt to explain the phenomenon of the whole universe by the same mechanical laws which experiments shews to be true here on earth. Cavalieri. Almost contemporaneously with the publication in 1637 of Descartes' geometry, the principles of the integral calculus, so far as they are concerned with summation, were being worked out in Italy. This was effected by what was called the principle of indivisibles, and was the invention of Cavalieri. It was applied to numerous problems connected with the quadrature of curves and surfaces, the determination of volumes, and the positions of centres of mass, to the complete exclusion of the tedious method of exhaustions used by the Greeks. In principle the methods are the same, but the notation of indivisibles is more concise and convenient. It was in its turn superseded at the beginning of the 18th century by the integral calculus, but its use will be familiar to all mathematicians who have read any commentary on the first section of the first book of Newton's Principia, in the application of lemmas 2 and 3 to the determination of areas, volumes, and so on. Bonaventura Cavalieri was born at Milan in 1598 and died at Bologna in November 27, 1647. He became a Jesuit at an early age, and on the recommendation of the order he was in 1629 made professor of mathematics at Bologna, and he continued to occupy the chair there until his death. I have already mentioned Cavalieri's name for the part of the book that he took in introducing the use of logarithms into Italy. He was one of the most influential mathematicians of his time, but his subsequent reputation rests mainly on his invention of the principle of indivisibles. The principle of indivisibles has been used by Kepler in 1604 and 1615 in somewhat crude form. It was first stated by Cavalieri in 1629, but he did not publish his results till 1635. In his early enunciation of the principle in 1635, Cavalieri asserted that a line was made up of an infinite number of points, each without magnitude, and a surface of an infinite number of lines, each without breadth, and a volume of infinite number of surfaces, each without thickness. To meet the objections of Guldinus and others, the statement was recast, and in its final form used by the mathematicians of the 17th century. It was published in Cavalieri's 6 Geometrical Exercises in 1647, the third of which is devoted to a defense of the theory. These exercises contain the first rigid demonstration of the properties of Pappus. Cavalieri's work on the subject were reissued with his later corrections in 1653. The method of indivisibles is simply that any magnitude may be divided into an infinite number of small quantities which can be made to bear any required ratios, for example equality, one to the other. The analysis given by Cavalieri is hardly worth quoting except as being one of the first steps taken toward the formation of an infinitesimal calculus. One example will suffice. Suppose it be required to find the area of a right-angled triangle. Let the base contain n points and the other side n times a points. Then the ordinates at the successive points of the base will contain a, 2a, and so on to n times a points. Therefore the number of points in the figure is a plus 2a plus ... plus na, the sum of which is half n squared a plus 1/2 n times a. Since n is very large, we may neglect the 1/2 na as inconsiderable compared with the 1/2 n squared a, and the area is 1/2 na times n, that is 1/2 the altitude times the base. There is no difficulty in criticizing such a proof,
but although the form in which it is presented is indefensible, the substance of it is correct. It would be misleading to give the above as the only specimen of the method of indivisibles, and I therefore quote another example, taken from a later writer, which will fairly illustrate the use of the method when modified and corrected by the method of limits. Let it be required to find the area bounded by the parabola APC, the tangent at A, and any diameter DC. Complete the parallelogram ABCD. Divide AD into n equal parts. Let AM contain r of them, and Mn be the r plus 1th part. Draw MP and NQ parallel to AB, and draw PR parallel to AD. Then, when n becomes indefinitely large, the curvilinear area APCD will be the limit of the sum of all parallelograms like Pn. Now the ratio of the area Pn to the area BD equals the ratio MP times Mn is to DC times AD. But by properties of the parabola, MP over DC equals AM squared over AD squared, which is also equal to r squared over n squared. And Mn over AD equals 1 over n. Hence, MP times Mn over DC times AD equals r squared over n cubed. Therefore, the area of Pn over the area of BD equals r squared over n cubed. Therefore, ultimately, the area of APCD over area BD equals 1 squared plus 2 squared plus 3 squared plus ... plus n minus 1 squared all over n cubed, which is also equal to 1/6 of n times n minus 1 times 2n minus 1 all over n cubed, which in the limit 1 to 3. It is perhaps worth noticing that Cavalieri and his successors always used the method to find the ratios of two areas, volumes, or magnitudes of the same kind and dimensions. That is, they never thought of an area as containing so many units of area. The idea of comparing a magnitude with a unit of the same kind seems to have been due to Wallis. It is evident that in its direct form the method is applicable to only a few curves. Cavalieri proved that if m be a positive integer, then the limit, when n is infinite, of 1 to the m plus 2 to the m plus 3 to the m ... plus n to the m all over n to the m plus 1 is 1 over m plus 1, which is equivalent to saying that he found the integral to x of x to the m from x equals 0 to x equals 1. He also discussed the quadrature of the hyperbola. End of chapter 21, part 1. Recording by Paul King, http://pjk.scripts.mit.edu/pkj.
Chapter 15, Part 2 of A Short Account of the History of Mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This reading is by Paul King, pjk.scripts.mit.edu/pkj. Pascal. Among the contemporaries of Descartes, none displayed greater natural genius than Pascal, but his reputation rests more on what he might have done than on what he actually effected, as during a considerable part of his life he deemed it his duty to devote his whole time to religious exercises. Blaise Pascal was born at Clermont on June 19, 1623, and died at Paris on August 19, 1662. His father, a local judge at Clermont and himself of some scientific reputation, moved to Paris in 1631, partly to prosecute his own scientific studies, partly to carry on the education of his only son who had already displayed exceptional ability. Pascal was kept at home in order to assure his not being overworked, and with the same object it was directed that his education should be at first confined to the study of languages and should not include any mathematics.
This naturally excited the boy's curiosity, and one day, being then 12 years old, he asked in what geometry consisted. His tutor replied that it was the science of constructing exact figures and of determining the proportions between their different parts. Pascal, stimulated no doubt by the injunction against reading it, gave up his playtime to the new study, and in a few weeks had discovered for himself many properties of figures, and in particular the proposition that the sum of the angles of a triangle is equal to two right angles. I have read somewhere, but I cannot lay my hand on the authority, that his proof merely consisted in turning the angular points of a triangular piece of paper over so as to meet in the centre of the inscribed circle. A similar demonstration can be got by turning the angular points over so as to meet at the foot of the perpendicular drawn from the biggest angle to the opposite side. His father, struck by this display of ability, gave him a copy of Euclid's Elements, a book which Pascal read with avidity and soon mastered. At the age of 14 he was admitted to the weekly meetings of Roberval, Mersenne, Midorge, and other French geometricians, from which the French Academy ultimately sprung, being created by ordinance of Louis XIV on December 22, 1666. At 16 Pascal wrote an essay on conic sections, and in 1641, at the age of 18, he constructed the first arithmetical machine, an instrument which 8 years later he further improved and patented. His correspondence with Fermat about this time shews that he was then turning his attention to analytical geometry and physics. He repeated Torricelli's experiments by which the pressure of the atmosphere could be estimated as a weight, and he confirmed his theory of the cause of barometrical variations by obtaining at the same instant readings at different altitudes on the hill of Puy de Dôme. In 1650, when in the midst of these researches, Pascal suddenly abandoned his favourite pursuits to study religion, or, as he says in his Pensées, to contemplate the greatness and the misery of man, and about the same time he persuaded the younger of his two sisters to enter the Port Royal Society. In 1653 he had to administer his father's estate. He now took up his old life again, and made several experiments on pressure exerted by gases and liquids. It was also about this period that he invented the arithmetical triangle, and together with Fermat created the calculus of probabilities. He was meditating marriage when an accident again turned the current of his thoughts to a religious life. He was driving a four-in-hand on November 23, 1654, when the horses ran away. The two leaders dashed over the parapet of the bridge at Neuilly, and Pascal was only saved by the traces breaking. Always somewhat of a mystic, he considered this a special summons to abandon the world. He wrote an account of the accident on a small piece of parchment, which for the rest of his life he wore next to his heart to perpetually remind him of his covenant, and shortly moved to Port Royal, where he continued to live until his death in 1662. Always delicate, he had injured his health by his incessant study. From the age of 17 or 18 he suffered from insomnia and acute dyspepsia, and at the time of his death was completely worn out. His famous provincial letters directed against the Jesuits and his Pensées were written towards the close of his life, and are the first example of that finished form which is characteristic of the best French literature. The only mathematical work that he produced after retiring to Port Royal was the essay of the cycloid in 1658. He was suffering from sleeplessness and a toothache when the idea occurred to him, and to his surprise his teeth immediately ceased to ache. Regarding this as a divine intimation to proceed with the problem, he worked incessantly for 8 days at it, and completed a tolerably full account of the geometry of the cycloid. I now proceed to consider his mathematical works in rather greater detail. His early essay of the geometry of conics, written in 1639 but not published until 1779, seems to have been founded on the teachings of Desargues. Two of the results are important as well as interesting. The first of these is the theorem known now as Pascal's theorem, namely that if a hexagon is inscribed in a conic, the points of the intersection of the opposite sides will lie in a straight line. The second, which is really due to Desargues, is that if a quadrilateral be inscribed in a conic and a straight line be drawn cutting the sides taken in order in the points A, B, C, and D, and the conic in P and Q, then PA times PC over PD times PD equals QA times QC over QB times QD.
Pascal's arithmetical triangle, known today as Pascal's triangle, was written in 1653, but not printed until 1665. The triangle is constructed as in the annexed figure. By the way, the annexed figure shows Pascal's triangle as being kind of on its side by today's standards. A 1 at the apex, followed by a 1, 1, and then in the third row 1, 2, 1, and in the fourth row 1, 3, 3, 1, and in the fifth row 1, 4, 6, 4, 1. So they will refer to these lines as diagonal lines. The horizontal lines, the way they're depicted, are 1, 1, 1, 1, 1, 1, 2, 3, 4, 5, 1, 3, 6, 10, 15, 1, 4, 10, 20, 35, and 1, 5, 15, 35, 70. And they have that written in actual rows and columns. So taking the latter description, each horizontal line being formed from the one above it by making every number in it equal to the sum of those above it and to the left of it in the row immediately above. For example, in the fourth line, 20 is equal to 1 plus 3 plus 6 plus 10. Then Pascal's arithmetical triangle to any required order is got by drawing a diagonal downwards from the right to left as in the figure. The numbers are what are now called the figurate numbers. Those in the first line are called the numbers of the first order. Those in the second line, 1, 2, 3, 4, 5, and so on, are called natural numbers or numbers of the second order. Those in the third line, numbers of the third order, and so on. It is easily shown that the mth number in the nth row is m plus n minus 2 factorial divided by m minus 1 factorial times n minus 1 factorial. The numbers in any diagonal give the coefficients of the expansion of a binomial. For example, the figures in the fifth diagonal, namely 1, 4, 6, 4, 1, are the coefficients in the expansion of a plus b raised to the power 4. Pascal used the triangle partly for this purpose, and partly to find the numbers of combinations of m things taken n at a time, which he stated correctly to be n plus 1 times n plus 2 times n plus 3 times m divided by m minus n factorial. Perhaps as a mathematician Pascal is best known in connection with his correspondence with Fermat in 1654, in which he laid down the principles of the theory of probabilities. This correspondence arose from a problem proposed by a gamester, the Chevalier de Mer, to Pascal, who communicated it to Fermat. The problem was this. Two players of equal skill want to leave the table before finishing the game. Their scores and the number of points which constitute the game being given, it is desired to find in what proportion should they divide the stakes. Pascal and Fermat agreed on the answer but gave different proofs. The following is a translation of Pascal's solution. That of Fermat is given later. The following is my method for determining the share of each player when, for example, two players play a game of 3 points and each player has staked 32 pistoles. Suppose that the first player had gained 2 points and then the second player 1 point, they now have to play for a point on this condition, that if the first player gain, he takes all the money which is at stake, namely 64 pistoles, while if the second player gain, each player has 2 points, so that they are on terms of equality, and if they leave off playing, each ought to take 32 pistoles. Thus, if the first player gain, then 64 pistoles belong to him, and if he loses, then 32 pistoles belong to him. If therefore the players do not wish to play this game but to separate without playing it, the first player would say to the second, "I am certain of 32 pistoles, even if I lose this game, and for the other 32 pistoles perhaps I shall have them and perhaps you will have them. The chances are equal. Let us divide these 32 pistoles equally, and give me also the 32 pistoles of which I am certain." Thus the first player will have 48 pistoles and the second 16 pistoles. Next, suppose that the first player has gained 2 points and the second player none, and they are about to play for a point. The condition is that if the first player gain this point, he secures the game and takes 64 pistoles, and if the second player gain this point, then the players will be in the situation already examined, in which the first player is entitled to 48 pistoles and the second to 16 pistoles. Thus, if they do not wish to play, the first player would say to the second, "If I gain this point, I gain 64 pistoles. If I lose it, I am entitled to 48 pistoles. Give me then the 48 pistoles of which I am certain, and divide the other 16, since our chances of gaining the point are equal." Thus the first player will have 56 pistoles and the second player 8 pistoles. Finally, suppose that the first player had gained 1 point and the second player none. If they proceed to play for a point, the condition is that if the first player gain it, the players will be in the situation first examined, in which the first player is entitled to 56 pistoles. If the first player lose the point, each player has then a point, and each is entitled to 32 pistoles. Give me the 32 pistoles of which I am certain, and divide the remainder of the 56 pistoles equally, that is, divide the 24 pistoles equally. Thus the first player will have the sum of 32 and 12 pistoles, that is 44 pistoles, and consequently the second will have 20 pistoles. Pascal proceeds next to consider the similar problem when the game is won by whomever first obtains m plus n points, and one player has m while the other has n points. The answer is obtained by using the arithmetical triangle, or Pascal's triangle. The general solution, in which the skill of the players is unequal, is given in many modern textbooks on algebra and agrees with Pascal's result, though of course the notation of the latter is different and less convenient. Pascal made a most illegitimate use of the new theory in the 7th chapter of his Pensées. He practically puts his argument that, as the value of eternal happiness must be infinite, then even if the probability of a religious life ensuring eternal happiness be very small, still the expectation, which is measured by the product of the two, must be of sufficient magnitude to make it worth while to be religious. The argument, if worth anything, would apply equally to any religion which has promised eternal happiness to those who accepted its doctrines. If any conclusion may be drawn from the statement, it is the undesirability of applying mathematics to questions of morality, of which some of the data are necessarily outside the range of an exact science. It is only fair to add that no one had more contempt than Pascal for those who changed their opinions according to the prospect of material benefit, and this isolated passage is at variance with the spirit of his writings. The last mathematical work of Pascal was that on the cycloid of 1658. The cycloid is the curve traced out by the point on the circumference of a circular hoop which rolls along a straight line. Galileo in 1630 had been the first to call attention to this curve, and had suggested that the arches of bridges should be built in the form of it. It is a graceful curve, but the only bridge with a cycloidal arch of which I have heard is the one built by Essex in the grounds of Trinity College at Cambridge. 4 years later, in 1634, Roberval found the area of the cycloid. Descartes thought little of this solution and defied him to find its tangents, the same challenge also being sent to Fermat, who at once solved the problem. Several questions connected with the curve and with the surface and volume generated by its revolution about its axis, base, or the tangent at its vertex were then proposed by various mathematicians. These, and some analogous questions as well as the positions of the centres of mass of the solids there formed, were solved by Pascal in 1658, and the results were issued as a challenge to the world. Wallis succeeded in solving all the questions except those connected with the centre of mass. Pascal's own solutions were effected by the method of indivisibles, and are similar to those which a modern mathematician would give by the aid of the integral calculus. He obtained by summation what are equivalent to the following integrals: the integral of sine phi d phi, also the integral of sine squared phi d phi, and also the integral of phi times sine phi d phi, one limit being either 0 or half pi. He also investigated the geometry of the Archimedean spiral. These researches, according to D'Alembert, form a connecting link between the geometry of Archimedes and the infinitesimal calculus of Newton. Wallis. John Wallis was born at Ashford on November 22, 1616, and died at Oxford on October 28, 1703. When 15 years old he happened to see a book on arithmetic in the hands of his brother. Struck with curiosity at the odd signs and symbols in it, he borrowed the book, and in a fortnight mastered the subject. It was intended that he should be a doctor, and he was sent to Emmanuel College, Cambridge. While there he kept an act on the doctrine of the circulation of the blood. This is said to have been the first occasion in Europe on which this theory was publicly maintained in disputation. His interests, however, centred on mathematics. He was elected to a fellowship at Queen's College, Cambridge, and subsequently took orders, but on the whole adhered to the Puritan party, whom he rendered great assistance in deciphering the royalist despatches. He, however, joined the moderate Presbyterians in signing the remonstrance against the execution of Charles I, by which he incurred the lasting hostility of the Independents. In spite of their opposition, he was appointed in 1649 to the Savilian chair of geometry at Oxford, where he lived until his death on October 28, 1703. Besides his mathematical works, he wrote on theology, logic, and philosophy, and was the first to devise a system for teaching deaf mutes. I confine myself to a few notes on his more important mathematical writings. They are notable partly for the introduction of the use of infinite series as an ordinary part of analysis, and partly for the fact that they revealed and explained to all students the principles of those new methods which distinguish modern from classical mathematics. The most important of Wallis's works was his Arithmetica Infinitorum, which was published in 1656. In this treatise the methods of analysis of Descartes and Cavalieri were systematized and greatly extended, but their logical exposition is open to criticism. It at once became the standard book on the subject, and is constantly referred to by subsequent writers. It is prefaced by a short tract on conic sections, which was subsequently expanded into a separate treatise. He commences by proving the law of indices, shews that x to the 0, x to the minus 1, x to the minus 2, and so on represent 1, 1 over x, 1 over x squared, and so on. That x to the power of 1/2 represents the square root of x. That x to the power of 2/3 represents the cube root of x squared, and that generally that x to the exponent minus n represents the reciprocal of x to the power n, and that x to the p over q represents the qth root of x to the p. Leaving the numerous algebraical applications of this discovery, he next proceeds to find by the method of indivisibles the area enclosed between the curve y equals x to the m, the axis of x, and any ordinate x equals h, and he proves that the ratio of this area is equal to that of the parallelogram on the same base and of the same altitude, and is equal to the ratio 1 over m plus 1. He apparently assumed that the same result would be true also for the curve y equals ax raised to the power m, where a is any constant and m is any number positive or negative. But he only discusses the case of which the parabola of m equals 2 and that of the hyperbola in which m equals minus 1. In the latter case his interpretation of the result is incorrect. He then shews that similar results might be written down for any curve of the form y equals the sum of ax raised to the power m, and hence that if the ordinate y on a curve can be expanded in powers of the abscissa x, its quadrature can be determined. Thus he said that if the equation of a curve were y equals x to the 0 plus x to the 1 plus x squared and so on, its area would be x plus 1/2 x squared plus 1/3 x cubed and so on. He then applies this to the quadrature of the curves y equals quantity x minus x squared to the power 0, y equals the quantity x minus x squared to the power 1, y equals x minus x squared quantity to the power 2, y equals quantity x minus x squared to the power 3, and so on, taken between the limits x equals 0 and x equals 1, and shows that the areas are respectively 1, 1 over 6, 1 over 30, 1 over 140, and so on. He next considers the curve of the form y equals x to the power 1 over m, and establishes the theorem that the area bounded by the curve, the axis of x, and the ordinate x equals 1 is to the area of the rectangle on the same base and the same altitude as m over m plus 1. This is equivalent to finding the value of the integral from 0 to 1 of x raised to the power 1 over m dx. He illustrates this by the parabola in which m equals 2. He states, but does not prove, that the corresponding result of the curve of the form y equals x raised to the p over q. This work contains also one of the earliest investigations of the formation and properties of continued fractions, a discussion that was suggested by Bruckner's use of these fractions. Wallis shewed considerable ingenuity in reducing the equations of curves to the forms given above, but as he was unacquainted with the binomial theorem, he could not effect the quadrature of the circle, whose equation is y equals quantity x minus x squared to the half, since he was unable to expand this in powers of x. He laid down, however, the principle of interpolation. Thus, as the ordinate of the circle y equals x minus x squared raised to the half is a geometrical mean between the ordinate of the curve y equals quantity x minus x squared raised to the 0 and y equals quantity x minus x squared raised to the 1, it might be supposed that as an approximation the area of the semicircle, the integral from 0 to 1 of quantity x minus x squared dx, which is 1/8 pi, might be taken as the geometrical mean between the values of the integral from 0 to 1 of quantity x minus x squared raised to the 0 dx and the integral of 0 to 1 of quantity x minus x squared raised to the 1 dx, that is, the values 1 and 1/6. This is equivalent to taking 4 multiplied by the root of 2/3, or 3.26 approximately, as the value of pi. But Wallace argued, we have in fact a series, 1, 1/6, 1 over 30, 1 over 140, and so on, and therefore the term interpolated between 1 and 1/6 ought to be so chosen as to obey the law of the series. This, by an elaborate method, which I need not describe in detail, leads to a value for the interpolated term which is equivalent to taking pi equals 2 times 2 over 1 times 2/3 times 4/3 times 4/5 times 6/5 times 6 over 7 times 8 over 7 times 8 over 9, and so on. The subsequent mathematicians of the 17th century constantly used interpolation to obtain results which we should attempt to obtain by direct analysis. A few years later, in 1659, Wallace published a tract containing the solution of the problems on the cycloid which had been proposed by Pascal. In this he incidentally explained how the principles laid down in his Arithmetica Infinitorum could be used for the rectification of algebraic curves, and gave a solution of the problem to rectify the semicubal parabola x cubed equals ay squared, which had been discovered in 1657 by his pupil William Neal. This was the first case in which the length of a curved line was determined by mathematics, and since all attempts to rectify the ellipse and the hyperbola had been necessarily ineffectual, it had been previously supposed that no curves could be rectified, as indeed Descartes had definitely asserted to be the case. The cycloid was the second curve rectified, and this was done by Rennes in 1658. Early in 1658 a similar discovery, independent of that of Nile, was made by Van Heuraet, and this was published by Van Schooten in his edition of Descartes' Geometria in 1659. Van Heuraet's method is as follows. He supposes the curve to be referred to rectangular axes. If this be so, and if xy be the coordinates of any point on it, and n the length of the normal, and if another point whose coordinates are x nu to be taken such that nu to h equals the ratio n to y, where h is a constant, then if ds be the element of the length of the required curve, then we have by similar triangles the ratio ds to dx equals n to y. Therefore HDS equals nu dx. Hence, if the area of the locus of the point x nu can be found, the first curve can be rectified. In this way Van Heuraet effected the rectification of the curve y cubed equals ax squared, and added that the rectification of the parabola y squared equals ax is impossible, since it requires the quadrature of the hyperbola. The solutions given by Nile and Wallace are somewhat similar to that given by Van Heuraet, but no general rule is enunciated, and the analysis is clumsy. A third method was suggested by Fermat in 1660, but it is both inelegant and laborious. In 1665 Wallace published the first systematic treatise on analytical conic sections. I have already mentioned that the Geometrie of Descartes is both difficult and obscure, and to many of his contemporaries to whom the method was new, it must have been incomprehensible. Wallace made the method intelligible to all mathematicians. This is the earliest book in which these curves are considered and defined as curves of the second degree, and not as sections of a cone on a circular base. The theory of the collision of bodies was propounded by the Royal Society in 1668 for the consideration of mathematicians. Wallace, Rennes, and Huygens sent correct and similar solutions, all depending on what is now called the conservation of momentum. But while Rennes and Huygens confined their theory to perfectly elastic bodies, Wallace considered also imperfectly elastic bodies. This was followed in 1669 by a work on statics, centers of gravity, and in 1670 by one on dynamics. These provide a convenient synopsis of what was then known on the subject. In 1685 Wallis published an algebra preceded by a historical account of the development of the subject, which contains a great deal of valuable information. The second edition, issued in 1693 and forming the second volume of his opera, is considerably enlarged. This algebra is noteworthy as containing the first systematic use of formulae. A given magnitude is here represented by the numerical ratio which it bears to the unit of the same kind of magnitude. Thus, when Wallis wants to compare two lengths, he regards each as containing so many units of length. This perhaps will be made clearer if I say that the relation between the space described in any time by a particle moving with uniform velocity would be denoted by Wallis by the formula S equals vt, where S is the number representing the ratio of the space described to the unit of length, while previous writers would have denoted the same relation by stating what is equivalent to the proportion S1 over S2 equals V1T1 over V2T2. See, for example, Newton's Principia, Book 1, Section 1, Lemma 10 or 11. It is curious to note that Wallis rejected as absurd the now usual idea of a negative number as being less than nothing, but accepted the view that it is something greater than infinity. The latter opinion may be right and consistent with the former, but it is hardly a more simple one. Fermat. While Descartes was laying down the foundation of analytical geometry, the same subject was occupying the attention of another and hardly less distinguished Frenchman. This was Fermat. Pierre de Fermat, who was born near Montauban in 1601 and died at Castres in January 12, 1665, was the son of a leather merchant. He was educated at home. In 1631 he obtained the post of councillor for the local parliament at Toulouse, and he discharged the duties of the office with scrupulous accuracy and fidelity. There, devoting most of his leisure to mathematics, he spent the remainder of his life, a life which, but for a somewhat acrimonious dispute with Descartes on the validity of analysis used by the latter, was unruffled by any event which calls for special notice. The dispute was due chiefly to the obscurity of Descartes, but the tact and courtesy of Fermat brought it to a friendly conclusion. Fermat was a good scholar and amused himself by conjecturally restoring the work of Apollonius on plane loci. Except for a few isolated papers, Fermat published nothing in his lifetime, and gave no systematic exposition of his methods. Some of the most striking of his results are found after his death on loose sheets of paper written on the margins of works which he had read and annotated, and are unaccompanied by any proof. It is thus somewhat difficult to estimate the dates and originality of his work. After his death his papers and correspondences were printed by his nephew at Toulouse in 2 volumes, 1670 and 1679. A summary of it with notes was published by Brazin in Toulouse in 1853, and a reprint of it was issued at Berlin in 1861. A new edition is now being issued by the French government, which will include some letters on his discoveries and methods in the theory of numbers recently found at Leyden by M. Charles Henry. Fermat was constitutionally modest and retiring, and does not seem to have intended his papers to be published. It is probable that he revised his notes as occasion required, and that his published works represent the final form of his researches, and therefore cannot be dated much earlier than 1660. I shall consider separately: 1. His investigations into the theory of numbers; 2. His use in geometry of analysis and of infinitesimals; and 3. His method of treating questions of probability. 1. The theory of numbers appears to have been the favourite study of Fermat. He prepared an edition of Diophantus, and the notes and comments thereon contain numerous theorems of considerable elegance. This forms the first of 2 volumes of his works.
Most of the proofs of Fermat are lost, and it is possible that some of them were not rigorous, an induction by analogy and the intuition of genius sufficing to lead him to correct results. The following examples will illustrate these investigations. A. If p be prime and a be a prime to p, then a to the power of p minus 1 subtract 1 is divisible by p. That is, when you subtract 1 from a to the power of p minus 1, this is equivalent to 0 modulus p. A proof of this, first, given by Euler, is well known. A more general theorem, that of a to the power of phi of n, subtracting 1 from that result, is equivalent to 0 mod n, where a is prime to n and phi of n is the number of integers less than n and prime to it. B. A prime greater than 2 can be expressed as the difference of two square integers in one and only one way. Fermat's proof is as follows. Let n be the prime and suppose it equal to x squared minus y squared, that is, to the product x plus y times x minus y. Now by hypothesis the only integral factors of n are n in unity, hence x plus y equals n and x minus y equals 1. Solving these equations we get x equals a half times n plus 1 and y equals a half times n minus 1. C. He gave a proof of the statement by Diophantus, quoted above, that the sum of the squares of two integers cannot be of the form 4n minus 1, and that he added a corollary which I take to mean that it is impossible that the product of a square and a prime of the form 4n minus 1, even if multiplied by a number prime to the latter, can be either a square or the sum of two squares. For example, 44 is a multiple of 11, which is of the form 4 times 3 minus 1. By 4, hence it cannot be expressed as a sum of two squares. He also stated that a number of the form a squared plus b squared, where a is prime to b, cannot be divided by a prime of the form 4n minus 1. D. Every prime of the form 4n plus 1 is expressible, and that in one way only, as a sum of two squares. This problem was first solved by Euler, who shewed that the number of the form 2 to the power m times 4n minus 1 can be always expressed as a sum of two squares. E. If a, b, c are integers such that a squared plus b squared equals c squared, then a times b cannot be a square. Lagrange gave a solution of this. F. The determination of a number x such that x squared n plus 1 may be a square, where n is a given integer which is not a square. G. There is only one integral solution of the equation x squared plus 2 equals y cubed, and there are only two integral solutions of the equation x squared plus 4 equals y cubed. The required solution are evidently for the first equation x equals 5 and for the second equation x equals 2 and x equals 11. This question was issued as a challenge to the English mathematicians Wallis and Digby. H. No integral values of x, y, z can be found to satisfy the equation x to the n plus y to the n equals z to the n, if n be an integer greater than 2. This proposition, known as Fermat's last theorem, has acquired extraordinary celebrity from the fact that no general demonstration of it has ever been given, but there is no reason to doubt that it is true. Probably Fermat discovered its truth for the case of n equals 3, and then for the case of n equals 4. His proof for the former of these cases is lost, but that for the latter is extant, and a similar proof for the case of n equals 3 was given by Euler. These proofs depend on shewing that if three integral values of x, y, z can be found which satisfy the equation, then it will be possible to find three and other similar integers which satisfy it. In this way, finally, we shew that the equation must be satisfied by three values which obviously do not satisfy it.
Thus no integral solution is possible. It would seem that this method is inapplicable to any cases except those of n equals 3 and n equals 4. Fermat's discovery of the general theorem was made later. An easy demonstration can be given on the assumption that a number can be resolved into prime or complex factors in one and only one way. The assumption has been made by some writers, but it is not universally true. It is possible that Fermat made some such supposition, though it is perhaps more likely that he discovered a rigorous demonstration. In 1823 Legendre obtained a proof for the case of n equals 5. In 1832 Lejeune de Richelieu gave one for n equals 14, and in 1840 Lamé and Lebesgue gave proofs for n equals 7. The proposition appears to be true universally, and in 1849 Kummer, by means of ideal primes, proved it to be so for all numbers except, if any, which satisfy three conditions. It is not certain whether any number can be found to satisfy these conditions, but there is no number less than 100 which does so. The proof is complicated and difficult, and there can be no doubt is based on the considerations unknown to Fermat. I may add that, to prove the truth of the proposition where n is greater than 4, it is obviously sufficient to confine ourselves to cases where n is a prime, and the first step in Kummer's demonstration is to shew that in such cases one of the numbers xyz must be divisible by n.
A letter exists now in the University at Leyden which gave an idea of Fermat's methods. The letter is undated, but it would appear that, at the time Fermat wrote it, he had proved the proposition h above only for the case when n equals 3. 2. I next proceed to mention Fermat's use in geometry of analysis and of infinitesimals. It would seem from his correspondence that he had thought out the principles of analytic geometry for himself before reading Descartes' Géométrie, and had realized that from the equation, or as he calls it, the specific property of a curve, all its properties could be deduced. His extant papers on geometry deal, however, mainly with the application of infinitesimals to the determination of the tangents to curves, and to the quadrature of curves, and to the questions of maxima and minima. Probably these papers are a revision of his original manuscripts, which he destroyed, and were written about 1663, but there is no doubt that he was in possession of the general idea of his methods for finding maxima and minima as early as 1628 and 1629. He obtained the subtangent to the ellipse, cycloid, cissoid, conchoid, and quadratrix by making the ordinates of the curve and a straight line the same for 2 points whose abscissae were x and x minus e. But there is nothing to indicate that he was aware that the process was general, and though in the course of his work he used the principle, it is probable that he never separated it, so to speak, from the symbols of the particular problem he was considering. The first definite statement of the method was due to Barrow and was published in 1669. Fermat also obtained the areas of parabolas and hyperbolas of any order, and determined the centre of mass of a few simple curves and of a paraboloid of revolution. As an example of his method of solving these equations, I will quote his solution of the problem to find the area between the parabola y cubed equals px squared on the axis of x and the line x equals a. He says that if the several ordinates at the points for which x is equal to a times the quantity 1 minus e, and a times the quantity 1 minus e to the power of 2, and so on, be drawn, the area will be split into a number of little rectangles whose areas are respectively ae times pa squared to the power of 1/3, AE times 1 minus E multiplied by the quantity PA squared times the quantity 1 minus E squared, all under a cube root. The sum of these is P to the 1/3 A to the 5/3 times E divided by the quantity 1 minus E to the 5/3, and by a subsidiary proposition, for of course he was not acquainted with the binomial theorem, he finds the limit of this when E vanishes to be 3/5 P to the 1/3 A to the 5/3. The theorems last mentioned were published only after his death, and probably they were not written till he had read the works of Cavalieri and Wallis. Kepler had remarked that the values of a function immediately adjacent to and on either side of a maximum or minimum value must be equal. Fermat applied this principle to a few examples. Thus, to find the maximum value of x times the quantity a minus x, his method is essentially equivalent to taking a consecutive value of x, namely x minus e, where e is very small, and putting x times quantity a minus x equal to quantity x minus e multiplied by the quantity a minus x plus e. Simplifying and ultimately putting e equals 0, we get x equals half a. This value of x makes the given expression a maximum. 3. Fermat must share with Pascal the honour of having founded the theory of probabilities. I have already mentioned the problem proposed to Pascal and which he communicated to Fermat, and have there given Pascal's solution. Fermat's solution depends on the theory of combinations and will be sufficiently illustrated by the following example, the substance of which was taken from a letter dated August 24, 1654, which occurs in the correspondence with Pascal. Fermat discusses the case of two players, and supposes that the first wants 2 points to win and the second 3 points. The game will be then certainly decided in the course of 4 trials. Take the letters A and B and write down all the combinations that can be formed of 4 letters. These combinations are the following, 16 in all. Now let big A denote the player who wants 2 points, and big B denote the player who wants 3 points. Then in these 16 combinations, every combination in which A occurs twice or oftener represents a case favorable to big A, and every combination in which little b occurs 3 times or oftener represents a case favorable to player big B. Thus, on counting them, it will be found that there will be 11 cases favorable to A and 5 cases favorable to B, and since these cases are all equally likely, A's chance of winning the game is to B's chances as 11 is to 5. The only other problem on this subject which, as far as I know, attracted the attention of Fermat was also proposed to him by Pascal and was as follows. A person undertakes to throw a 6 with a die in 8 throws. Supposing him to have made 3 throws without success, what proportion of the stake should he be allowed to take on condition of giving up his 4th throw? Fermat's reasoning is as follows. The chance of success is 1 in 6, so that he should be allowed to take 1/6 of the stake on condition of giving up his throw. But if we wish to estimate the value of the 4th throw before any throw is made, then the first throw is worth 1/6 of the stake. The second is worth 1/6 of what remains, that is 5/36 of the stake. The third throw is worth 1/6 of what now remains, that is 25 over 216ths of the stake. The fourth throw is worth 1/6 of what now remains, and that is 125 over 1296ths of the stake. Fermat does not seem to have carried the matter much further, but his correspondence with Pascal shews that his views on the fundamental principles of the subject were accurate. Those of Pascal were not altogether correct. Fermat's reputation is quite unique in the history of science. The problems on numbers which he had proposed long defied all efforts to solve them, and many of them yielded only to the skill of Euler. One still remains unsolved. This extraordinary achievement has overshadowed his other work, but in fact it is all of the highest order of excellence, and we can only regret that he thought fit to write so little. End of part 2. Read by Paul King, pjk.scripts.mit.edu/pkj. Chapter 15, Part 3 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This reading is by Paul King, pjk.scripts.mit.edu/pkj. A short account of the history of mathematics by W. W. Rouse Ball. History of mathematics from Descartes to Huygens circa 1635 to 1675. Part 3. Huygens. Christian Huygens was born at The Hague on April 14, 1629, and died in the same town on June 8, 1695. He generally wrote his name as Huygens, Hugens, but I follow the usual custom in spelling it as Huygens. It is also sometimes written as Huygens. His life was uneventful, and is a mere record of the dates of his various works. In 1651 he published an essay in which he shewed the fallacy in a system of quadratures proposed by Gregoire de Saint-Vicent, who was well versed in the geometry of the Greeks, but had not grasped the essential points in the more modern methods. This essay was followed by tracts on the quadrature of the conics and the approximate rectification of the circle. In 1654 his attention was directed to the improvement of the telescope. In conjunction with his brother he devised a new and better way of grinding and polishing lenses. As a result of these improvements, he was able, during the following 2 years, 1655 and 1656, to resolve numerous astronomical questions, as for example the nature of Saturn's appendage. His astronomical observations required some exact means of measuring time, and he was thus led in 1656 to invent the pendulum clock, as described in his tract on Horologium, 1658. The timepieces previously in use had been balance clocks. In the year 1657 Huygens wrote a small work on the calculus of probabilities founded on the correspondence of Pascal and Fermat. He spent a couple of years in England about this time. His reputation was now so great that in 1665 Louis XIV offered him a pension if he would live in Paris, which accordingly then became his place of residence. In 1668 he sent to the Royal Society of London, in answer to a problem they had proposed, a memoir in which, simultaneously with Wallis and Wren, he proved by experiment that the momentum in a certain direction before the collision of two bodies is equal to the momentum in that direction after the collision. This was one of the points in mechanics on which Descartes had been mistaken. The most important of Huygens's work was in his Horologium Oscillatorium, published in Paris in 1673. The first chapter is devoted to the pendulum clocks. The second chapter contains a complete account of the descent of heavy bodies under their own weights in a vacuum, either vertically down or on smooth curves. The second chapter contains a complete account of the descent of heavy bodies under their own weights in a vacuum, either vertically down or on smooth curves. Amongst other propositions, he shews that the cycloid is tautochronous. In the third chapter, he defines evolutes and involutes, proves some of their more elementary properties, and illustrates his methods by finding the evolutes of the cycloid and the parabola. These are the earliest instances in which the envelope of a moving line is determined. In the fourth chapter, he solves the problem of the compound pendulum and shews that the centers of oscillation and suspension are interchangeable. In the fifth and last chapter, he discusses again the theory of clocks, points out that if the bob of the pendulum were made by means of cycloidal checks to oscillate in a cycloid, the oscillations would be isochronous, and finishes by shewing that the centrifugal force on a body which moves in a circle of radius r with uniform velocity v varies directly as v squared and inversely as r. This work contains the first attempt to apply dynamics to bodies of finite size and not merely to particles. In 1675, Huygens proposed to regulate the motion of watches by use of the balance spring, in the theory of which he had been perhaps anticipated in a somewhat ambiguous and incomplete statement made by Hooke in 1658. Watches or portable clocks had been invented early in the 16th century, and by the end of that century were not very uncommon, but they were clumsy and unreliable, being driven by a main spring and regulated by a conical pulley and verge escapement. Moreover, until 1687 they had only one hand. The first watch whose motion was regulated by a balanced spring was made at Paris under Huygens' directions, and presented by him to Louis XIV. The increasing intolerance of the Catholics led to his return to Holland in 1681, and after the revocation of the Edict of Nantes, he refused to hold any further communication with France. He now devoted himself to the construction of lenses of enormous focal length. Of these, 3 of focal length 123 feet, 180 feet, and 210 feet was subsequently given by him to the Royal Society in London, in whose possession they still remain. It was about this time that he discovered the achromatic eyepiece for a telescope, which is known by his name. In 1689 he came from Holland to England in order to make the acquaintance of Newton, whose Principia had been published in 1687, the extraordinary merits of which Huygens had at once recognized. On his return in 1690, Huygens published his treatise on light, in which the undulatory theory was expounded and explained. Most of this had been written as early as 1678. The general idea of the theory had been suggested by Robert Hooke in 1664, but he had not investigated its consequences in any detail. This publication falls outside the years considered in this chapter, but here it may be briefly said that according to the wave or undulatory theory, space is filled with an extremely rare ether, and light is caused by a series of waves or vibrations in this ether, which are set in motion by the pulsations of the luminous body. From this hypothesis, Huygens deduced that the laws of reflection and refraction explain the phenomenon of double refraction, and gave a construction for the extraordinary ray in biaxial crystals, while he found by experiment the chief phenomenon of polarization. The immense reputation and unrivalled powers of Newton led to the disbelief in the theory which he rejected, and to the general adoption of Newton's emission theory. But it should be noted that Huygens' explanation of some phenomenon, such as the colors of thin plates, was inconsistent with the results of experiments, nor was it until Young and Wollaston at the beginning of this century revived the undulatory theory and modified some of its details, and Fresnel elaborated their views, that its acceptance could be fully justified. Besides these works, Huygens took part in most of the controversies and challenges which then played so large a part in the mathematical world, and wrote several minor tracts. In one of these he investigated the form and properties of the catenary. In another he stated in general terms the rule for finding maxima and minima of which Fermat had made use, and shewed that the subtangent of an algebraical curve fxy equals 0 was equal to y fy by fx, where fy is the derivative of fxy regarded as a function of y. In some posthumous works, issued at Leyden in 1703, he further shewed how from the focal lengths of the component lenses the magnifying power of a telescope could be determined, and explained some of the phenomena connected with halos and parhelia. I should add that almost all of his demonstrations, like those of Newton, are rigidly geometrical, and he would seem to have made no use of the differential or fluxional calculus, though he admitted the validity of the methods used therein. Thus, even when first written, his works were expressed in an archaic language, and perhaps received less attention than their intrinsic merits deserved. I have now traced the development of mathematics for a period which we may take roughly as dating from 1635 to 1675 under the influence of Descartes, Cavalieri, Pascal, Wallis, Fermat, and Huygens. The life of Newton partly overlaps this period. His works and influence are considered in the next chapter. I may dismiss the remaining mathematicians of this time, whom I dare to mention with comparatively slight notice. The following is an alphabetical list of the more remarkable among them. The dates given to those are the birth and death of the mathematician to whose name they are appended. Bachet, 1581 to 1638. Barrow, 1630 to 1677. Brochner, 1620 to 1684. Collins, 1625 to 1683. Coursier, 1604 to 1692. Debonne, 1601 to 1652. De la Lubert, 1600 to 1664. Frenicle, 1605 to 1670. Gregory, 1638 to 1675. Hooke, 1635 to 1703. Hood, 1633 to 1704. Kinckhuysen, 1630 to 1679. Mercator, 1620 to 1687. Mersenne, 1588 to 1648. Midorge, 1585 to 1647. Pell, 1610 to 1685. Ritchie, 1619 to 1692. Roberval, 1602 to 1675. Roemer, 1644 to 1710. St. Vincent, 1584 to 1667. Sluys, 1622 to 1685. Torricelli, 1608 to 1647. Turnhausen, 1631 to 1708. Van Schooten died in 1661. And Wren, 1632 to 1723. In the following notes I have arranged the above-mentioned mathematicians so that as far as possible their chief contributions shall come in chronological order. Bachet. Claude Gaspard Bachet de Mézirac was born in Bourg in 1581 and died in 1638. He wrote the Problème Plaisant, 1612, second and enlarged edition, 1624, which contains an interesting collection of arithmetical tricks and questions, many of which are quoted in Chapter 1 of my Mathematical Recreations and Problems, also Les Éléments Arithmétiques, which exists in manuscript, and a translation of Arithmetic by Diophantus. Bachet was the earliest writer who discussed the solution of indeterminate equations by means of continued fractions. Midorge. Claude Midorge, born in Paris in 1585 and died in 1647, belonged to a distinguished family of the robe, and was himself a councillor at Châtelet, then treasurer to the local parliament at Amiens. He published some works on optics, of which one issued in 1631 is extant, and in 1641 a treatise on conic sections. He also left a manuscript containing solutions of over 1,000 geometrical problems, many of which are said to be ingenious. The enunciations were published by M. Charles Henry in 1882. Mersenne. Marin Mersenne, born in 1588 and died in Paris in 1648, was a Franciscan friar who made it his business to be acquainted and correspond with the French mathematicians of that date and many of their foreign contemporaries. In 1634 he published a translation of Galileo's Mechanics. In 1644 he issued his Cogitata Physico-Mathematica, by which he is best known, containing an account of some experiments in physics. He also wrote a synopsis of mathematics, which was printed in 1664. The preface to the Cogitata contains a statement, probably due to Fermat, that in order that 2p-1 may be prime, the only values of p not greater than 257 which are possible are 1, 2, 3, 5, 7, 13, 17, 19, 31, 67, 127, and 257, to which list Herr Seelhoff has shewn we must add the number 61. With this addition, the statement has been verified for all except 23 values of p, namely 61, 71, 89, 101, 103, 107, 109, 127, 137, 139, 149, 157, 163, 167, 173, 181, 193, 197, 199, 227, 229, 241, and 257. Of these values, Mersenne asserted that p equals 67, p equals 127, and p equals 257 make 2 to the exponent p minus 1 a prime, and that the other values make 2p minus 1 a composite number. It is most likely that these results are particular cases of some general theorem on the subject which remains to be discovered. The number 2 to the power 61 minus 1 contains 19 digits, and is the highest number at present known to be prime. Its value in digits is 2305843009213693951. The theory of perfect numbers depends directly on that of Mersenne's numbers. It is probable that all perfect numbers are included in the formula 2 to the power of p minus 1, as opposed to negative 1 plus 2 to the p, where negative 1 plus 2 to the p is prime. Euclid proved that any number of this form is perfect. Euler shewed that the formula includes all even perfect numbers, and there is reason to believe, though a rigid demonstration is wanting, that an odd number cannot be perfect. If we assume that the last of these statements is true, then every perfect number is of the above form. Thus if p equals 2, 3, 5, 7, 13, 17, 19, 31, 61, then by Mersenne's rule the corresponding values of negative 1 plus 2 to the p are prime. They are 3, 7, 31, 127, 8,191, 131,071, 524,287, 2,147,483,647, and finally 2,305,213,813,693,951. And the corresponding perfect numbers are 6, 28, 496, 8,128, 33,550,336, 8,589,869,056, 137,438,691,328. Next is 2,305,843,000,000, 8,139,952,128. And finally, 2 undecillion, 658 decillion, 455 nonillion, 991 octillion, 569 septillion, 831 hexillion, 744 quintillion, 654 quadrillion, 692 trillion, 615 billion, 953,842,176.
De Beaume. Florimond de Beaume was born in Blois in 1601 and died in 1652. Wrote explanatory notes on the obscure and difficult analytical geometry of Descartes. He also discussed the superior and inferior limits to the roots of an equation. This was not published till 1659. Roberval. Gilles Personnier de Roberval, born at Roberval in 1602 and died at Paris in 1675, described himself from the place of his birth as de Roberval, a seigneurial title to which he had no right. He discussed the nature of the tangents to the curves, solved some of the easier questions connected with the cycloid, generalized Archimedes' theorems on the spiral, and wrote on mechanics and the method of indivisibles, which he rendered more precise and logical. He was a professor in the University of Paris and in correspondence with nearly all of the leading mathematicians of his time. A complete edition of his works was included in the old Memoir of the Academy of Sciences, published in 1693. Van Schooten. Franz van Schooten, to whom we owe an edition of Vieta's works, succeeded his father, who had taught mathematics to Huygens, Hood, and Sluys as a professor at Leyden in 1646. He brought out in 1659 a Latin translation of Descartes' Géométrie, and in 1657 a collection of mathematical exercises in which he recommended the use of coordinates in space of 3 dimensions. He died in 1661. Saint Vincent. Grégoire de Saint Vincent, a Jesuit, born at Bruges in 1584 and died at Ghent in 1667, discovered the expansion of the logarithm of 1 plus x in ascending powers of x. Although a circle squarer, he is worthy of mention for the numerous theorems of interest which he discovered in his search after the impossible, and Montucla ingeniously remarks that no one ever squared the circle with so much ability except for his principal object with so much success. He wrote 2 books on the subject, one published in 1647 and the other in 1668, which cover some 2,000 or 3,000 closely printed pages. The fallacy in the quadrature was pointed out by Huygens. In the former work he had used indivisibles. An earlier work entitled Theoremata Mathematica, published in 1624, contains a clear account of the method of exhaustions which is applied to several quadratures, notably that of the hyperbola. For further details of St. Vincent's life and works, see L. A. J. Quetelet, Histoire des sciences chez les Blages, Brussels, 1866. Torricelli. Evangelista Torricelli, born at Faenza in October 15, 1608, died at Florence in 1647, wrote on the quadrature of the cycloid and conics, the theory of the barometer, the value of gravity found by observing the motion of 2 weights connected by a string passing over a fixed pulley, the theory of projectiles, and the motion of fluids. His mathematical writings were published in 1644. Hood. Johann Hood, a burgomaster of Amsterdam, was born there in 1633 and died in the same town in 1704.
He wrote two tracts in 1659. One was on the reduction of equations which have equal roots. In the other he stated what is equivalent to the proposition that if f of xy equals 0 be the algebraical equation of a curve, then its subtangent is negative y of the partial derivative of x with respect to y divided by the partial derivative of x with respect to x. But being ignorant of the notation of the calculus, his enunciation is involved. Frenicle. Bernard Frenicle de Bessy, born in Paris circa 1605 and died in 1670, wrote numerous papers on combinations and on the theory of numbers, and also on magic squares. It may be interesting to add that he challenged Huygens to solve the following system of equations in integers: x squared plus y squared equals z squared, x squared equals u squared plus v squared, and x minus y equals u minus v. A solution was given by M. Pepin in 1880. Frenicle's miscellaneous works, edited by De la Hare, was published in the Mémoires de l'Académie, Volume 5, 1691. De Laloubert. Antoine de Laloubert, a Jesuit born in Languedoc in 1600, died at Toulouse in 1664, is chiefly celebrated for an incorrect solution of Pascal's problems on the cycloid, which he gave in 1660, but he has a better claim to distinction in having been the first mathematician to study the properties of the helix. Kinckhuysen. Gerard Kinckhuysen, born in Holland in 1630 and died in 1679, wrote in 1660 a textbook on analytical conics, in 1661 an algebra, and in 1669 formed a collection of geometrical problems solved by analytical geometry. Coursier. Pierre Coursier, a Jesuit, born at Troyes in 1604 and died in Auxerre in 1692, wrote on the curves of intersection of a sphere with a cylinder or cone, also on spherical polygons. The latter work was published in 1663. Ricci. Michel-Ange Ricci, born in 1619, made a cardinal in 1681 and died in Rome in 1692, wrote in 1666 a treatise in which he solved by Greek geometry those problems on maxima and minima and on tangents to curves which had been considered by Descartes, Pascal, and Fermat. N. Mercator. Nicholas Mercator, sometimes known as Kaufmann, born in Holstein about 1620, but resided most of his life in England. He went to France in 1683, where he designed and constructed the fountains at Versailles, but when they were finished, Louis XIV refused to make him the payment agreed on unless he would turn Catholic. He died of vexation and poverty in Paris in 1687. He wrote a treatise on logarithms entitled Logarithmotechnia, published in 1668, and discovered the series log of 1 plus x equals x minus x squared over 2 plus x squared over 3 minus x to the power 4 over 4, and so on. He proved this by writing the equation of a hyperbola in the form of y equals 1 over 1 plus x, which would be equal to 1 minus x plus x squared minus x cubed plus, and so on, to which Wallace's formula, stated before, could be applied. The same series had been independently discovered by St. Vincent. Barrow. Isaac Barrow was born in London in 1630 and died at Cambridge in 1677. He went to school first at Charterhouse, where he was so troublesome that his father was heard to pray that if it pleased God to take any of his children, he could best spare Isaac, and subsequently to Felsted. He completed his education at Trinity College, Cambridge. After taking his degree in 1648, he was elected to a fellowship in 1649. He then resided for a few years in college, but in 1655 he was driven out by the persecution of the Independents. He spent the next 4 years in the east of Europe, and after many adventures returned to England in 1659. He was ordained the next year and appointed to the professorship of Greek at Cambridge. In 1662 he was made professor of geometry at Gresham College, and in 1663 was selected as the first occupier of the Lucasian chair at Cambridge. He resigned the latter to his pupil Newton in 1669, whose superior abilities he recognized and frankly acknowledged. For the remainder of his life he devoted himself to the study of divinity. He was appointed the master of Trinity College in 1672, and he held the post until his death. He is described as low in stature, lean and of a pale complexion, slovenly in dress, and an inveterate smoker. He was noted for his strength and courage, and once when travelling in the east he saved the ship by his own prowess from capture by pirates. A ready and caustic wit made him a favourite of Charles II, and induced the courtiers to respect even if they did not appreciate him. He wrote with a sustained and somewhat stately eloquence, and with his blameless life and scrupulous conscientiousness he was an impressive personage of the time. His earliest work was a complete edition of the Elements of Euclid, which he issued in 1655. He published an English translation in 1660, and in 1657 an edition of the Data. His lectures, delivered in 1664, 1665, and 1666, were published in 1683 under the title of Lectiones Mathematicae. These are mostly on the metaphysical basis for mathematical truths. His lectures for 1667 were published in the same year, and suggest the analysis by which Archimedes was led to his chief results. In 1669 he issued his Lectiones Opticae Geometricae. It is said in the preface that Newton revised and corrected these lectures, adding matter of his own, but it seems probable from Newton's remarks in the fluxional controversy that the additions were confined to the parts which dealt with optics. This, which is his most important work in mathematics, was republished with a few minor alterations in 1674. In 1675 he published an edition with numerous comments on the first 4 books of the Conics of Apollonius and of the extant works of Archimedes and Theodosius. In the optical lectures, many problems connected with the reflection and refraction of light are treated with great ingenuity. The geometrical focus of a point seen by a reflection or refraction is defined, and it is explained that the image of an object is the locus of the geometrical foci of every point on it. Barrow also worked out a few of the easier properties of thin lenses, and considerably simplified the Cartesian explanation of the rainbow. The geometrical lectures contain some new ways of determining the areas of the tangents of curves. The most celebrated of these is the method given for the determination of tangents to curves, and this is sufficiently important to require a detailed notice because it illustrates the way in which Barrow, Hood, and Sluys were working on the lines suggested by Fermat towards the methods of the differential calculus. Fermat had observed that the tangent at point P on a curve was determined if one other point besides P on it were known. Hence, if the length of the subtangent MT could be found, thus determining the point T, then the line TP would be the required tangent. Now Barrow remarked that if the abscissa and ordinate at a point Q adjacent to P were drawn, he got a small triangle PQR, which he called the differential triangle because its sides PR and PQ were the differences of the abscissa and ordinates of P and Q, so that TM to MP equals QR to RP. To find QR to RP, he supposed that XY were the coordinates of P, and x minus e, y minus a, those of Q. Barrow actually used P for x and M for y, but I alter these to agree with the modern practice. Substituting the coordinates of q in the equation of the curve and neglecting the squares and higher powers of e and a as compared with their first powers, he obtained the ratio e to a. The ratio a over e was subsequently, in accordance with a suggestion made by Sluys, termed the angular coefficient of the tangent at the point. Barrow applied this method to the curves 1. X squared multiplied by the quantity x squared plus y squared equals r squared y squared. 2. X cubed plus y cubed equals r cubed. And 3. X cubed plus y cubed equals rxy, called Lagalande. 4. Y equals the quantity r minus x multiplied by the tangent of pi x divided by 2r, the quadratrix. And 5. Y equals r times tan pi x over 2r. It will be sufficient here if I take as an illustration the simpler case of the parabola y squared equals px. Using the notation given above, we have for the point P y squared equals px, and for the point Q y minus a quantity squared equals p multiplied by the quantity x minus e. Subtracting, we get 2ay minus a squared equals pe. But if a be an infinitesimal quantity, a squared must be infinitely smaller and therefore may be neglected. Hence the ratio e to a equals the ratio 2y to p. Therefore tm to y equals e to a equals 2y to p. That is, tm equals 2y squared divided by p, which is equal to 2x. This is exactly the procedure of the differential calculus, except that we there have a rule by which we can get the ratio a over e or dy by dx directly without the labor of going through a calculation similar to the above for every separate case. Bruckner. William Viscount Bruckner, one of the founders of the Royal Society of London, born in 1620 and died on April 15, 1684, was among the most brilliant mathematicians of his time, and was in intimate relations with Wallis, Fermat, and other leading mathematicians. I mentioned on page 155 his curious reproduction of Brahmagupta's solution of a certain indeterminate equation. Bruckner proved that the area enclosed between the equilateral hyperbola xy equal 1 and the axis of x, and the ordinates x equals 1 and x equals 2 is equal either to 1 over 1 times 2 plus 1 over 3 times 4 plus 1 over 5 times 6 plus and so on, or to 1 minus 1/2 plus 1/3 minus 1/4 and so on. He also worked out similar expressions for different areas bounded by the hyperbola and straight lines. He wrote on the rectification of the parabola and of the cycloid. It is noticeable that he used infinite series to express quantities whose values he could not otherwise determine. In answer to a request of Wallis to attempt the quadrature of the circle, he shewed that the ratio of the area of the circle to the area of the circumscribed square, that is, the ratio of pi to 4, is equal to the ratio 1 over 1 plus 1 squared over 2 plus 3 squared over 2 plus 5 squared over 2 plus 7 squared over 2 and so on to 1. Continued fractions had been introduced by Cataldi in his treatise on finding the square roots of numbers published at Bologna in 1613, but he treated them as common fractions. Bruckner was the first writer who investigated or made any use of their properties. For further details, see C. Hutton's Mathematical Dictionary. James Gregory. James Gregory, born at Drumoak near Aberdeen in 1638 and died in Edinburgh in October 1675, was successively professor at St Andrews and Edinburgh. In 1660 he publishes Optica Promota, in which the reflecting telescope known by his name is described. In 1667 he issued his Vera Circuli et Hyperbolae Quadratura, in which he showed the areas of the circle and hyperbola could be obtained in the form of infinite convergent series, and here, I believe for the first time, we find a distinction drawn between convergent and divergent series. This work contains a remarkable geometrical proposition to the effect that the ratio of the area of any arbitrary sector to that of the inscribed or circumscribed regular polygons is not expressible by a finite number of algebraical terms. Hence he inferred that the quadrature was impossible. This was accepted by Montucla, but it is not conclusive, for it is conceivable that some particular sector might be squared, and this particular sector might be the whole circle. This book contains also the earliest enunciations of the expansions in the series of sin x, cosine of x, inverse sine of x, and inverse cosine of x. It was reprinted in 1668 with an appendix, Geometriae Pars, in which Gregory explained how the volumes of solids of revolution could be determined. In 1671, or perhaps earlier, he established the theorem that theta equals tan theta minus 1/3 tan cubed theta minus 1/5 tan to the fifth theta, and so on. The result being true only if theta lie between negative 1/4 pi and positive 1/4 pi. This is the theorem on which the work of most of the subsequent calculation of approximations to the numerical value of pi has been based. For further detail see C. Hutton's Mathematical Dictionary. Wren. Sir Christopher Wren was born in Noyle in 1632 and died in London in 1723. Wren's reputation as a mathematician has been overshadowed by his fame as an architect, but he was Savilian Professor of Astronomy at Oxford from 1661 to 1673 and for some time President of the Royal Society. Together with Wallis and Huygens, he investigated the laws of collision of bodies. He also discovered the two systems of generating lines on the hyperboloid of one sheet, though it is probable that he confined his attention to the hyperboloid of revolution. Besides these, he communicated papers on the resistance of fluids and the motion of the pendulum. He was a friend of Newton, and like Huygens, Hooke, Halley, and others, had made attempts to shew that the force under which the planets move varies inversely as the square of the distance from the sun. Wallis, Bruckner, Wren, and Boyle, the last named being a chemist and physicist rather than a mathematician, were the leading philosophers who had founded the Royal Society of London. The society arose from the self-styled Indivisible College in London in 1645. Most of its members moved to Oxford during the Civil War, where Hooke, who was then an assistant in Boyle's laboratory, joined in their meetings. The society was formally constituted in London in 1660 and was incorporated on 15th of July 1662. Hooke. Robert Hooke, born at Freshwater on July 18, 1635, and died in London on March 3, 1703, was educated at Westminster and Christ Church, Oxford, and in 1665 he became professor of geometry at Gresham College, a post which he occupied till his death. He is still known by the law which he discovered, that the tension exerted by a stretched string is, within certain limits, proportional to the extension, or as it is better stated, that the stress is proportional to the strain. He invented and discussed the conical pendulum, and was the first to state explicitly that the motions of the heavenly bodies were merely dynamical problems. He was as jealous as he was vain and irritable, and accused both Newton and Huygens of unfairly appropriating his results. Like Huygens, Wren and Halley He made efforts to find the law of force under which the planets move about the sun, and he believed the law to be that of the inverse square of the distance. He, like Huygens, discovered that the small oscillations of a coiled spiral spring were practically isochronous, and was thus led to recommend, possibly in 1658, the use of the balance spring in watches. He had a watch of this kind made in London in 1675. It was finished just 3 months later than the one made under the directions of Huygens in Paris. Collins. John Collins, born near Oxford on March 5, 1625, and died in London on November 10, 1683, was a man of great natural ability, but of slight education. Being devoted to mathematics, he spent his spare time in correspondence with the leading mathematicians of the time, for whom he was always ready to do anything in his power, and he has been described, not inaptly, as the English Mersenne. To him we are indebted for much information on the details of the discoveries of the period. Pell. Another mathematician who devoted considerable part of his time to making known the discoveries of others and to correspondence with leading mathematicians was John Pell. Pell was born at Sussex on March 1, 1610, and died in London on December 10, 1685. He was educated at Trinity College, Cambridge. He occupied in succession the mathematical chairs at Amsterdam and Breda. He then entered the English diplomatic service, but finally settled in 1661 in London, where he spent the last 20 years of his life. His chief works were an edition, with considerable new matter, of the Algebra by Brenker and Ronius, London 1668, and a table of square numbers, London 1672. For further details, see my History of Mathematics at Cambridge. Sluys. René Francois Walter de Sluys, or Slusius, canon of Liege, born on July 7, 1622, and died on March 19, 1685, found for the subtangent of a curve fxy equals 0 an expression which is the equivalent to negative y multiplied by the partial derivative delta f by delta y divided by the partial derivative delta f by dx. He wrote numerous tracts, and in particular discussed at some length spirals and points of inflection. Tschirnhausen. Ehrenfried Walter von Tschirnhausen was born at Kislingswald on April 10, 1631, and died at Dresden on October 11, 1708. In 1682 he worked out the theory of caustics by reflection, or as they were usually called, catacaustics, and shewed that they were rectifiable. This was the second case in which the envelope of a moving line was determined. He constructed the burning mirrors of great power. The transformation by which he removes certain intermediate terms from a given algebraical equation is well known. Romer. Olaf Romer was born at Aranus in September 25, 1644, and died in Copenhagen on September 19, 1710, and was the first to measure the velocity of light. This was done in 1675 by means of the eclipses of Jupiter's satellites. He brought the transit and mural circle into common use, the altazimuth having been previously generally employed, and it was on his recommendation that astronomical observations of stars were subsequently made in general on the meridian. He was also the first to introduce micrometers and reading microscopes into an observatory. He also deduced from the properties of epicycloids the form of the teeth and the toothed wheels best fitted to secure a uniform motion. End of part 23. Chapter 16, Part 1 of a short account of the history of mathematics.
This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripps.mit.edu/pkj. A short account of the history of mathematics by W. W. Rouse Ball. Chapter 16. The life and works of Newton. The mathematicians considered in the last chapter commenced the creation of those processes which distinguish modern mathematics. The extraordinary abilities of Newton enabled him within a few years to perfect the more elementary of these processes and to distinctly advance every branch of mathematical science then studied, as well as to create some new subjects. Newton was the contemporary and friend of Wallis, Huygens, and others of those mentioned in the last chapter, but though most of his mathematical work was done in between the years 1665 and 1686, the bulk of it was not printed, at any rate in book form, till some years later. I propose to discuss the works of Newton somewhat more fully than those of other mathematicians, partly because of the intrinsic importance of his discoveries, and partly because this book is mainly intended for English readers, and the development of mathematics in Great Britain was for a century entirely in the hands of the Newtonian school. Isaac Newton was born in Lincolnshire, near Grantham, on December 25th, 1642, and died at Kensington, London, on March 20th, 1727. He was educated at Trinity College, Cambridge, and lived there from 1661 till 1696, during which time he produced the bulk of his work in mathematics. In 1696 he was appointed to a valuable government office, and moved to London, where he resided till his death. His father, who had died shortly before Newton was born, was a yeoman farmer, and it was intended that Newton should carry on the paternal farm. He was sent to school at Grantham, where his learning and mechanical proficiency excited some attention, and as one instance of his ingenuity I may mention that he constructed a clock worked by water, which kept very fair time. In 1656 he returned home to learn the business of a farmer under the guidance of an old family servant. Newton, however, spent most of his time studying problems, making experiments, or devising mechanical models. His mother, noticing this, sensibly resolved to find some more congenial occupation for him, and his uncle, having been himself educated at Trinity College, Cambridge, recommended that he should be sent there. In 1661 Newton accordingly entered as a subsidar at Trinity College, where for the first time he found himself among surroundings which were likely to develop his powers. He seems somewhat to have but little interest for the general society or for any pursuits save science and mathematics, and he complained to his friends that he found the other undergraduates disorderly. Luckily he kept a diary, and we can thus form a fair idea of the course of education of the most advanced students at an English university at that time. He had not read any mathematics before coming into residence, but was acquainted with Sanderson's logic, which was then frequently read as preliminary to mathematics. At the beginning of his first October term he happened to stroll down to Southridge Fair, and there picked up a book on astrology, but could not understand it on account of the geometry and trigonometry. He therefore bought a Euclid, and was surprised to find how obvious the prepositions seemed. He thereupon read Oughtred's Clavis and Descartes' Geometrie, and the latter of which he managed to master by himself, though with some difficulty. The interest he felt in the subject led him to take up mathematics rather than chemistry as serious study. His subsequent mathematical reading as an undergraduate was found on Kepler's Optics, the works of Vieta, Van Schooten's Miscellanies, and Descartes' Geometrie, and Wallis's Arithmetica Infinitorum.
He also attended Barrow's lectures. At a later time, on reading Euclid more carefully, he formed a high opinion of it as an instrument of education, and he used to express his regret that he had not applied himself to geometry before proceeding to algebraic analysis. There is a manuscript of his, dated May 28, 1665, written in the same year as that which he took his BA degree, which is the earliest documentary proof of his invention of fluxions. It was about the same time that he discovered the binomial theorem. On account of the plague, the college was shut down in the summer of 1665, and for a large part of the next year and a half Newton lived at home. This period was crowded with brilliant discoveries. He thought out the fundamental principles of his theory of gravitation, namely that every particle of matter attracts every other particle, and he suspected that the attraction varied as the product of their masses and inversely as the square of the distance between them. He also worked out the fluxional calculus tolerably completely. Thus, in a manuscript dated November 13, 1665, he used fluxions to find the tangent and the radius of curvature at any point on a curve, and in October 1666 he applied them to several problems in the theory of equations. Newton communicated these results to his friends and pupils from and after 1669, but they were not published in print till many years later. It was also while staying at home at this time that he devised some instruments for grinding lenses to particular forms other than spherical, and perhaps he decomposed solar light into different colors. Leaving out details and taking round numbers only, his reasoning at this time on the theory of gravitation seems to have been as follows. He suspected that the force which retained the moon in its orbit about the earth was the same as terrestrial gravity, and to verify this hypothesis he proceeded thus. He knew that if a stone were allowed to fall near the surface of the earth, the attraction of the earth, that is, the weight of the stone, caused it to move through 16 feet in 1 second. The moon's orbit relative to the earth is nearly a circle, and as a rough approximation, taking it to be so, he knew that the distance of the moon, and therefore the length of its path. He also knew the time the moon took to go once round it, namely a month. Hence, he could easily find its velocity at any point such as m. He could therefore find the distance mt, through which he would move in the next second if it were not pulled by the earth's attraction. At the end of that second it was however at m prime, and therefore the earth must have pulled it through the distance tm prime in 1 second, assuming the direction of the earth pull to be constant. Now he and several physicists of the time had conjectured from Kepler's third law that the attraction of the earth on a body would be found to decrease as the body was removed further away from the earth in a proportion inversely as the square of the distance from the center of the earth. If this were the actual law, and gravity were the sole force which retained the moon in its orbit, then Tm prime should be to 16 feet in a proportion which inversely is the square of the distance of the moon from the center of the earth to the square of the radius of the earth. In 1679, when he repeated the investigation, Tm prime was found to have the value which was required by the hypothesis, and the verification was complete, but in 1666 his estimate of the distance of the moon was inaccurate, and when he made the calculation he found that Tm prime was about 1/8 less than it ought to have been on his hypothesis. This discrepancy does not seem to have shaken his faith in the belief that gravity extended to the moon and varied inversely as the square of the distance, but from Whiston's notes of a conversation with Newton it would seem that Newton inferred that some other force, probably Descartes' vortices, acted on the moon as well as gravity. This statement is confirmed by Pemberton's account of the investigation. It seems, moreover, that Newton already believed firmly in the principle of universal gravitation. that is, every particle of matter attracts every other particle, and suspected that the attraction varied as the product of their masses and inversely as the square of the distance between them. But it is certain that he did not then know what the attraction of a spherical mass on any external point would be, and he did not think it likely that a particle would be attracted by the earth as if the latter were concentrated into a single particle at its centre. On his return to Cambridge in 1667, Newton was elected to a fellowship at his college, and permanently took up his residence there. In the early part of 1669, or perhaps in 1668, he revised Barrow's lectures for him. The end of lecture 14 is known to have been written by Newton, but how much of the rest is due to his suggestions cannot now be determined. As soon as this was finished, he was asked by Barrow and Collins to edit and add notes to a translation of King Huyson's Algebra, which he consented to do, but on condition that his name should not appear in the matter. In 1670 he also began a systematic exposition of his analysis by infinite series, the object of which was to express the ordinate of a curve in an infinite algebraical series, every term of which could be integrated by Wallace's rule. His results on the subject have been communicated to Barrow, Collins, and others in 1669. This was never finished. The fragment was published in 1711, but the substance of it had been printed as an appendix to the Optics in 1704. These works were only the first of Newton's leisure, most of the time during these 2 years being given up to optical researches. In October 1669 Barrow resigned the Lucasian chair in favour of Newton. During his tenure of the professorship it was Newton's practice to lecture publicly once a week, from half an hour to an hour at a time, in one term of each year, probably dictating his lectures as rapidly as they could be taken down, and in the week following the lecture to devote 4 hours to appointments which he gave to students who wished to come to his rooms to discuss the results of the previous lecture. He never repeated a course, which usually consisted of 9 or 10 lectures, and generally the lectures of one course began from the point at which the preceding course had ended. The manuscripts of his lectures for 17 out of the first 18 years of his tenure are extant. When first appointed, Newton chose optics for the subject of his lectures and researches, and before the end of 1669 he had worked out the details of his discovery on the decomposition of a ray of white light into rays of different colours by means of a prism. The complete explanation of the theory of the rainbow followed from this discovery. These discoveries form the subject matter of the lectures which he delivered as Lucasian professor in the years 1669, 1670, and 1671. The chief new results were embodied in a paper communicated to the Royal Society in February 1672, and subsequently published in the Philosophical Transactions. The manuscript of his original lectures was printed in 1729 under the title Lectiones Opticae. This work is divided into 2 books, the first of which contains 4 sections and the second 5. The first section of the first book deals with the decomposition of solar light by a prism in consequence of the unequal refrangibility of the rays that compose it, and a description of his experiments is added. The second section contains an account of the method which Newton invented for the determining of the coefficients of refraction of different bodies. This is done by making a ray pass through a prism of the material so that the deviation is a minimum, and he proves that if the angle of the prism be I and the deviation of the ray be delta, then the refractive index will be the sine of 1/2 I plus delta multiplied by the cosecant half I. The third section is on refractions at plane surfaces. Here he shews that if a ray passed through a prism with minimum deviation, the angle of incidence is equal to the angle of emergence. Most of this section is devoted to geometrical solutions of different problems. The fourth section contains a discussion of refractions at curved surfaces. The second book treats of the theory of colours of the rainbow. By a curious chapter of accidents, Newton failed to correct the chromatic aberration of two colours by means of a couple of prisms. He therefore abandoned the hope of making a refracting telescope which should be achromatic, and instead designed a reflecting telescope, probably on the model of a small one which he had made in 1668. The form he used is that still known by his name. The idea of it was naturally suggested by Gregory's telescope. In 1672 he invented a reflecting microscope, and some years later he invented the sextant, which was rediscovered by Hadley in 1731. His professorial lectures from 1673 to 1683 were on algebra and the theory of equations, and are described below. But much of his time during these years was occupied with other investigations, and I may remark that throughout his life Newton must have devoted at least as much attention to the chemistry and theology as to mathematics, though his conclusions are not of sufficient interest to require mention here. His theory of colours and his deductions from his optical experiments were attacked with considerable vehemence by Paradis of France, Linus and Lucas at Liège, Hooke in England, and Huygens in Paris, but his opponents were finally refuted. The correspondence which this entailed on Newton occupied nearly all his leisure in the years 1672 to 1675, and proved extremely distasteful to him. Writing on December 9, 1675, he says, "I was so persecuted with discussions arising out of my theory of light that I blame my own imprudence for parting with so substantial a blessing as my quiet to run after a shadow." Again, after November 18, 1676, he observes, "I see I have made myself a slave to philosophy, but, if I get rid of Mr. Linus's business, I will resolutely bid adieu to it eternally, excepting what I do for my private satisfaction, or leave to come out after me. For I see a man must either resolve to put out nothing new, or to become a slave to defend it." The unreasonable dislike to have his conclusions doubted, or to be involved in any correspondence about them, was a prominent trait in Newton's character. He next set himself to examine the problem as to how light was really produced, and by the end of 1675 he had worked out the corpuscular or emission theory, a theory to which he was perhaps led by his researches on the theories of attraction. Only three ways have been suggested in which light can be produced mechanically. Either the eye may be supposed to send out something which, so to speak, feels the object, as the Greeks believed, or the object perceived may send out something which hits or affects the eye, as assumed in the emission theory. Or there may be some medium between the eye and the object may cause some change in the form or nature of this intervening medium and thus affect the eye, as Hooke and Huygens supposed in the wave or undulatory theory. It will be enough here to say that on either of the two latter theories all the obvious phenomena of geometrical optics, such as reflection, refraction, etc., can be accounted for. Within the present century, crucial experiments have been devised which give different results according as one or the other theory is adopted. All these experiments agree with the results of the undulatory theory and differ from the results of the Newtonian theory. The latter is therefore untenable, but whether the former represents the whole truth and nothing but the truth is still an open question. Until, however, the theory of interference suggested by Young was worked out by Fresnel, the hypothesis of Huygens failed to account for all the facts, and was open to more questions than that of Newton. It should be noted that Newton nowhere expresses an opinion that the corpuscular theory is true, but always treats it as a hypothesis from which, if true, certain results would follow. It would moreover seem that he believed that the wave theory to be intrinsically more probable, and it was only the difficulty of explaining diffraction on that theory that led him to reject it. His remarks on the other physical subjects shew a similar caution. Newton's corpuscular theory was expounded in memoirs communicated to the Royal Society in December 1675, which are substantially reproduced in his Optics, published in 1704. In the latter work he dealt in detail with his theory of fits of easy reflection and transmission, and the colours of thin plates, to which he added an explanation of the colours of thick plates, and observations on the inflection of light. Two letters written by Newton in the year 1676 are sufficiently interesting to justify an allusion to them. Leibniz, who had been in London in 1673, communicated some results to the Royal Society, which he had supposed to be new, but which, it was pointed out to him, had been previously proved by Mouton. This led to a correspondence with Oldenburg, the secretary of the Society. In 1674 Leibniz wrote, saying that he possessed general analytical methods depending on the infinite series. Oldenburg in reply told him that Newton and Gregory had used such series in their work. In answer to a request for information, Newton wrote on June 13, 1676, giving a brief account of his method, but adding the expansions of a binomial, i.e. the binomial theorem, and of the arc sine of x, from the latter of which he deduced that of sine of x. This seems to be the earliest known instance of the reversion of a series. He also inserted an expression for the rectification of an elliptic arc in an infinite series. Leibniz wrote on August 27th asking for fuller details, and Newton, in a long but interesting reply dated October 24th, 1676, and sent through Oldenburg, gives an account of the way in which he had been led to some of his results. In this letter, Newton begins by saying that altogether he had used three methods for expansion in a series. His first was arrived at from the study of the method of interpolation, by which Wallis had found expressions for the area of a circle and hyperbola. Thus, by considering the series of expressions 1 minus x squared quantity to the power 0 over 2, 1 minus x squared quantity to the power 2 over 2, and 1 minus x squared quantity to the 4 over 2, and so on, he deduced by interpolations the law which connects the successive coefficients in the expansions of 1 minus x squared to the power of a half, 1 minus x squared to the power of 3 halves, and so on, and then by analogy obtained the expression for the general term in the expansion of a binomial, i.e. the binomial theorem. He says that he proceeded to test this by forming the square of the expansion 1 minus x squared to the power of a half, which reduced to 1 minus x squared. And he proceeded in a similar way with other expansions. He next tested the theorem in the case of 1 minus x squared quantity to the power of 1 half by extracting the square root of 1 minus x squared, more arithmetico. He also used the series to determine the areas of the circle and the hyperbola in infinite series, and found that the results were the same as those he had arrived at by other means. Having established this result, he then discarded the method of interpolation in series and employed his binomial theorem to express, when possible, the ordinate of a curve in an infinite series in ascending powers of the abscissa, and thus, by Wallis's method, he obtained expressions in an infinite series for the areas and arcs of curves in the manner described in the appendix to his Optics, and his De Analysi per Equationes Numero Terminorum Infinitorum. He states that he had employed his second method before the plague in 1665-66, and goes on to say that he was then obliged to leave Cambridge, and subsequently, i.e. presumably on his return to Cambridge, he ceased to pursue these ideas as he found that Nicholas Mercator had employed some of them in his Logarithmotechnica published in 1668, and he supposed that the remainder had been or would be found out before he himself was likely to publish his discoveries. Newton next explains that he had also a third method, of which, he says, he had about 1669 sent an account to Barrow and Collins, illustrated by applications to areas, rectification, cubature, and etc. This was the method of fluxions, but Newton gives no description of it here, though he adds some illustrations of its use. The first illustration is on the quadrature of the curve represented by the equation y equals ax to the power m multiplied by the quantity b plus cx to the power n quantity to the power p, which he says can be effected as a sum of quantity m plus 1 divided by n terms if quantity m plus 1 divided by m be a positive integer, and which he thinks cannot otherwise be affected except by an infinite series. He also gives a list of other forms which are immediately integrable, of which chief are x is raised to the power of m times n minus 1 multiplied by open bracket a plus bx to the power n plus cx to the power of 2n close bracket raised to the power of minus 1. Next, x to the power of open bracket m plus 1 half close bracket n minus 1 multiplied by open bracket a plus bx to the power of n plus cx to the power of 2n close bracket raised to the power of minus 1. The next term, x to the power of m times n minus 1 multiplied by open bracket a plus bx to the power of n plus cx to the power of 2n close bracket raised to the power of plus or minus a half. Next term, x to the power of m times n minus 1 multiplied by open bracket a plus bx to the power of n close bracket plus or minus a half open bracket c plus dx to the power of n close bracket raised to the power of minus 1. Next term, x to the power of m times n minus 1 multiplied by open bracket a plus bx to the power of n close bracket raised to the power of 1 half multiplied by open bracket c plus dx to the power of n close bracket raised to the power of negative 1 half, where m is a positive integer and n is any number whatever. Lastly, he points out that the area of any curve can be easily determined approximately by the method of interpolation described below, in discussing his Methodus Differentialis. At the end of his letter, Newton alludes to the solution of the inverse problem of tangents, a subject on which Leibniz had asked for information. He gives formulae for reversing any series, but says that besides these formulae he has two methods for solving such questions, which for the present he will not describe except by an anagram, which being read is as follows: Une methodis consistent in extractione fluentis quantitatis ex equationes simul evolvente fluxionem ejus. Alteratantum in assumptione seriae pro quantitate qualibet incognitia ex qua cetera commodi derivare possunt, et in collagione terminorum homologorum equationis resultantis ad eruendos terminos assumptae seriae. He implies in this letter that he is worried by the questions he has asked and the controversies raised about every new matter which he produces, which shew his rashness in publishing Quod ombrum captando e tennis perdiderum, quietam rem prorsus substantialem. Leibniz did not reply to this letter till June 21st, 1677. In his answer he explains his method of drawing tangents to curves, which he says proceeds not by fluxions of lines but by the differences of numbers, and he introduces his notation of dx and dy for the infinitesimal differences between the coordinates of two consecutive points on a curve. He also gives a solution of the problem to find a curve whose subtangent is constant, which shows that he could integrate. In 1679, Hooke, at the request of the Royal Society, wrote to Newton expressing a hope that he would make further communications to the Society and informing him of various facts then recently discovered. Newton replied, saying that he had abandoned the study of philosophy, but he added that the earth's diurnal motion might be proved by the experiment of observing the deviation from the perpendicular of a stone dropped from a height to the ground, an experiment which was subsequently made by the Society and succeeded. Hooke, in his letter, mentioned Picard's geodetical researches. In these, Picard used a value of the radius of the earth which is substantially correct. This led Newton to repeat with Picard's data his calculations of 1666 on the lunar orbit, and he found the verification of his view was complete. He then proceeded to the general theory of motion under a centripetal force, and demonstrated 1. The equitable description of areas, 2. That if an ellipse were described about a focus under a centripetal force, then the law was that of the inverse square of the distance. 3. And conversely, that of the orbit of a particle projected under the influence of such a force was a conic, or it may be, he thought, only an ellipse. Obeying his rule to publish nothing which could land him in scientific controversy, these results were locked up in his notebooks, and it was only a specific question addressed to him 5 years later that led to their publication. The Universal Arithmetic, which is on algebra, theory of equations, and miscellaneous problems, contains the substance of Newton's lectures during the years 1673 to 1683. His manuscript of it is still extant. Whiston extracted somewhat reluctant permission from Newton to print it, and it was published in 1707. Amongst several new theorems on various points in algebra and the theory of equations, Newton here enunciated the following important results. He explained that the equations whose roots are the solution of a given problem will have as many roots as there are different possible cases, and he considered how it happened that the equation to which a problem led might contain roots which did not satisfy the original question. He extended Descartes' rule of signs to give limits to the number of imaginary roots. He used the principle of continuity to explain how two real and unequal roots might become imaginary in passing through equality, and illustrated this by geometrical considerations. Thence he shewed that imaginary roots must occur in pairs. Newton also here gave rules to find a superior limit to the positive roots of a numerical equation, and to determine the approximate values of the numerical roots. He further enunciated the theorem known by his name for finding the sum of the nth powers of the roots of an equation, and laid the foundation of the theory of symmetrical functions of the roots of an equation. The most interesting theorem contained in the work is his attempt to find a rule analogous to that of Descartes for real roots, by which the number of imaginary roots of an equation can be determined. He knew that the result which he obtained was not universally true, but he gave no proof and did not explain what were the exceptions to the rule. His theorem was as follows. Suppose the equation to be of the nth degree arranged in descending powers of x, the coefficient of x to the n being positive, and suppose the n plus 1 fractions 1, n over n plus 1 multiplied by 2 over 1, n minus 1 over n minus 2 multiplied by 3 over 2, and so on. And then the middle term of the series would be n minus p plus 1 all divided by n minus p, that fraction multiplied by p plus 1 over p, and so on, and the second last term being 2 over 1 multiplied by the fraction n over n minus 1, and finally the final term 1. To be formed and written below the corresponding terms of the equation, then, if the square of any term when multiplied by the corresponding fraction be greater than the product of the terms on each side of it, put a plus sign above it, otherwise put a minus sign above it, and put a plus sign above the first and last terms. Now consider any two consecutive terms in the original equation and the two symbols written above them. Then we may have any one of the four following cases. Alpha, the terms of the same sign and the symbols of the same sign. Beta, the terms of the same sign and the symbols of the opposite signs. Gamma, the terms of opposite signs and the symbols of the same sign. Delta, the terms of the opposite signs and the symbols of the opposite signs. Then it has been shewn that the number of negative roots will not exceed the number of cases, alpha, and the number of positive roots will not exceed the number of cases, gamma, and therefore the number of imaginary roots is not less than the number of cases, beta and delta. In other words, the number of changes of signs in the row of symbols written above the equation is an inferior limit to the number of imaginary roots. Newton, however, asserted that you may also know how many roots are impossible by counting the changes of sign in the series of symbols formed as above. That is to say, he thought that in general the actual number of positive, negative, and imaginary roots could be got only by the rule, and not merely superior or inferior to the limits of these numbers. But though he knew that the rule was not universal, he could not find what were the exceptions to it. This theorem was subsequently discussed by Campbell, Maclaurin, Euler, and other writers. At last, in 1865, Sylvester succeeded in proving the general result. In August 1684, Halley came to Cambridge in order to consult Newton about the law of gravitation. Hooke, Huygens, Halley, and Wren had all conjectured that the force of the attraction of the sun or earth on an external particle varied inversely as the square of the distance. These writers seem to have independently shewn that if Kepler's conclusion were rigorously true, as to which they were not quite certain, the law of attraction must be that of the inverse square, but they could not deduce from the law of the orbits of the planets. Halley explained that their investigations were stopped by their inability to solve this problem, and asked Newton if he could find out what the orbit of a planet would be if the law of attraction were that of an inverse square. Newton immediately replied that it was an ellipse, and promised to send or write out afresh the demonstration of it which he had found in 1679. This was sent in November of 1684. End of section 24, chapter 16, part 1. Recording by Paul King, pjk.scripps.mit.edu/pkj. Chapter 16, Part 2 of A Short Account of the History of Mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripps.mit.edu/pkj. A Short Account of the History of Mathematics by W. W. Rouse, Chapter 16, The Life and Works of Newton, Part 2. Instigated by Halley, Newton now returned to the problem of gravitation, and before the autumn of 1684 he had worked out the substance of propositions 1 through 19, 21, 30, 32 through 35 in the first book of the Principia. These, together with the notes on the laws of motion and various lemmas, were read for his lectures in the Michaelmas term 1684. In November, Halley received Newton's promised communication, which probably consisted of the substance of propositions 1, 11, and either 17 or corollaries 1 of 13, and thereupon he again went to Cambridge, where he saw a curious treatise, De Motu, drawn up since August. Most likely this contained Newton's manuscript notes of the lectures above alluded to. These notes are now in the university library and are headed De Motu Corporum. Halley begged that the results might be published, and finally secured a promise that they should be sent to the Royal Society. They were accordingly communicated to the Society not later than February 1685 in the paper De Motu, which contained the substance of the following propositions in the Principia, Book 1. Propositions 1, 4, 6, 7, 10, 11, 15, 17, 32, and Book 2, Propositions 2, 3, and 4. It seems also to have been due to the influence and tact of Halley at this visit in November 1684 that Newton undertook to attack the whole problem of gravitation and practically pledged himself to publish his results. As yet Newton had not determined the attraction of a spherical body on an external point, nor had he calculated the details of the planetary motions, even if the members of the solar system could be regarded as points. The first problem was solved in 1685, probably either in January or February. No sooner, to quote from Dr. Galishier's address on the bicentenary of the publication of the Principia, had Newton proved the superb theorem, and we know from his own words that he had no expectation of so beautiful a result till it emerged from his mathematical investigation, that all the mechanism of the universe at once lay spread before him. When he discovered the theorems that from the first 3 sections of Book 1, when he gave them in his lectures of 1684, he was unaware that the sun and earth exerted their attractions as if they were but points. How different must these propositions have seemed to Newton's eyes when he realized that these results, which he had believed to be only approximately true when applied to the solar system, were really exact. Hitherto they had been only true in so far as he could regard the sun as a point compared to the distance of the planets, or the earth as a point compared to the distance of the moon, a distance amounting to only about 60 times the earth's radius, but now they were mathematically true, excepting only for the slight deviation from a perfectly spherical form of the sun, earth, and planets. We can imagine the effect of this sudden transition from approximation to exactitude in stimulating Newton's mind to still greater efforts. It was now in his power to apply the mathematical analysis with absolute precision to the actual problems of astronomy. Of the 3 fundamental principles applied in the Principia, we may say that the idea that every particle attracts every other particle in the universe was formed at least as early as 1666. The law of equable distribution of areas, its consequences, and the fact that if the law of attraction were that of the inverse square of the orbit of a particle about a center of force, would be a conic, were proved in 1679, and lastly, the discovery that a sphere, whose density at any point depends only on the distance from the center, attracts an external point as if the whole mass were collected at its center, were made in 1685. It was this last discovery that enabled him to apply the first 2 principles to the phenomenon of bodies of finite size. The draft of the first book of the Principia was finished before the summer of 1685, but the corrections and additions took some time, and the book was not presented to the Royal Society until April 28, 1686. This book is given up to the consideration of the motion of particles or bodies in free space, either in known orbits, or under the action of known forces, or under their mutual attraction. In it, Newton generalizes the law of attraction into a statement that every particle of matter in the universe attracts every other particle with a force which varies directly as the product of their masses and inversely as the square of the distance between them, and he thence deduces the law of attraction for spherical shells of constant density. The book is prefaced by an introduction on the science of dynamics. The second book of the Principia was completed by the summer of 1686. This book treats of motion in a resting medium and of hydrostatics and hydrodynamics, with a special application to waves, tides, and acoustics. He concludes it by shewing that the Cartesian theory of vortices is inconsistent both with the known facts and with the laws of motion. The next 9 or 10 months were devoted to the third book. Probably for this he had originally no materials ready. In it, the theorems obtained in the first book are applied to the chief phenomenon of the solar system, the masses and distances of the planets, and, wherever sufficient data existed, of their satellites are determined. In particular, the motion of the moon, the various inequalities therein, and the theory of the tides are worked out in detail. He also investigates the theory of comets, shews that they belong to the solar system, explains how from 3 observations the orbit can be determined, and illustrates his results by considering certain special comets. The third book, as we have it, is but little more than a sketch of what Newton had finally proposed to himself to accomplish. His original scheme is among the Portsmouth Papers, and his notes shew that he continued to work at it for some years after the publication of the first edition of the Principia. The most interesting of his memoranda are those in which, by means of fluxions, he has carried out his results beyond the point at which he was able to translate them into geometry. Footnote: I take this opportunity of saying that I hope shortly to publish a memoir on the history and compilation of the Principia. The following brief summary of the contents of the work will give the reader a general idea of its arrangement. The Principia is preceded by a preface in which Newton says that his object is to apply mathematics to the phenomena of nature. Among these phenomena, motion is one of the most important. Now, motion is the effect of force, and though he does not know what is the nature or origin of force, still many of its effects can be measured, and it is these that form the subject matter of the work. The work begins, therefore, naturally with an introduction on dynamics or the science of motion. This commences with the 8 definitions of the various terms, such as mass, momentum, and so on. Newton then lays down 3 laws of motion which are incapable of exact proof, but are confirmed partly by direct experiments, partly by the agreement with observation of the deductions from them. From these he deduces 6 fundamental principles of mechanics, and adds an appendix on the motion of falling bodies, projectiles, oscillations, impact, and the mutual attractions of 2 bodies. The most important deduction is that of the parallelogram of velocities, accelerations, and forces. The first book of the Principia is on the motion of bodies in free space and is divided into 14 sections. The first section consists of 11 preliminary lemmas treated by the method of prime and ultimate ratios, and not by that of indivisibles. The second section commences by shewing that if a body, such as a planet, revolve in an orbit subject to a force tending to a fixed point, such as the sun, the areas swept out by radii drawn from the body to the point are in one plane and are proportional to the times of describing them. And conversely, if the areas be proportional to the times, the force acting on the body must be directed to the point. Newton then shews how, if the orbit be known and the centre of force be given, the law of force can be determined, and he finds the law for various curves. In the third section he applies these propositions to a body which describes a conic section about a focus, and proves that the force must vary inversely as the square of the distance, and that Kepler's third law would necessarily be true of such a system. Conversely, he proves that if a body were projected in any way and subject to a central force which varied according to this law, then it must move in a conic section having the centre of force in a focus. He concludes, proposition 17, corollaries 3 and 4, with a suggestion as to how the effects of distributing forces should be calculated. This was first done by the brilliant investigations of Laplace and Lagrange. And Laplace says that Lagrange's paper in the Berlin Memoirs for 1786, on which the modern treatment of the subject is founded, was suggested by these remarks of Newton. The fourth and fifth sections are devoted to the geometry of conic sections, especially to the construction of conics, which satisfy 5 conditions.
In section 4, one of the conditions is that the focus is given.
This includes the problem of finding the path of a comet from 3 observations which Newton says he found the most difficult problem of any which he had to solve. Curiously enough, he gave a second solution of the problem in Book 3, Proposition 41, in which he recommended as more simple but which is inapplicable in practice. The sixth section is devoted to determining what at any given time is the velocity and what is the position of a body which is describing a given conic about a center of attraction in a focus, together with various converse problems. To effect this, Newton had to find the area of a sector of a conic. This is easily done for the parabola. He then endeavours to shew that the exact quadrature of any closed oval curve having no infinite branches, such as the ellipse, is impossible. The proof is not correct as it stands, since the result is not true for ovals of the form
y to the power of 2m equals the quantity a to the power of 2n minus x to the power of 2n, all multiplied by 2 to the power of 2m times n to the power of 2m multiplied by x to the power of 2m times 2n minus 1,
where m and n are positive integers.
Newton seems himself to have felt some doubt about inserting it,
though he believed the result to be true. An exact quadrature being impossible, he proceeds to give 3 ways, 2 arithmetical and 1 geometrical, of approximating to the sectorial area of an ellipse as closely as is desired. The seventh section is given up to the discussion of motion in a straight line under a force which varies inversely as the square of the distance, and its comparison with the motion in a conic under the same force. He concludes by giving a general solution for all the problems considered in this section for any law of force. He here determines geometrically what is equivalent to finding the integral of x divided by the square root of the quantity ax minus x squared. The eighth section contains a general solutions for any orbit described under any central force of some of the problems previously considered. In Proposition 40 he states that the kinetic energy acquired by a body in moving from one point to another is equal to the total work done by the force between those 2 points. In the ninth section he discusses the case where the orbit is in motion in its own plane round the center of force and treats in detail of the motion of the apse line and the forces by which a given motion would be produced. Newton applied this reasoning, Proposition 45 Corollary 2, to the case of the moon. But the resulting motion of the apses only came out about 1/2 of the actual amount. The approximation was in fact not carried to a sufficiently high order. Newton was aware of the discrepancy, and as he explained the similar difficulty in the case of the nodes it had been long suspected. Goldfray's Lunar Theory, 2nd edition, article 68, that the scholium of the first edition to Book 3, Proposition 35, meant that he had found the explanation. Nowhere in the Principia does he, however, give any hint as to how this was effected, and that the true explanation of a difference which had long formed an obstacle to the universal acceptance of the Newtonian system was first given by Clairaut in 1752. The Portsmouth Papers contain Newton's original work and shew that he had obtained the true value by carrying the approximation to a sufficiently high order. It also seems clear from these papers that Newton gave the corollary to Book 1, Proposition 45, as a mere illustration to the motion of the apses and orbits which are nearly circular, and did not mean it to apply to the moon. But by an inadvertence in the second and third editions a reference to it as an authenticity for a result connected with the moon was added, which would naturally deceive any reader. Newton left most of the revision to the second edition to Cotes, and it is probable that the mistake is due to a blunder of the editor. Other questions connected with lunar and planetary irregularities are also discussed in this proposition, but the extreme conclusions of Newton misled all the early commentators, and even Laplace in his Système du Monde, published in 1796, speaks of Newton as having only roughly sketched out this part of the subject, leaving it to be completed when the calculus should be further perfected. But in the last volume of his Mécanique Céleste, published in 1825, he says that on more careful reading he has no hesitation in regarding it as among the most profound parts of the work. The 10th section is devoted to the consideration of motion of bodies along given surfaces, but not in planes passing through the center of force, with special reference to the vibration of pendulums and the determination of the accelerating effect of gravity. In connection with the latter problem, Newton investigates the chief geometrical properties of cycloids, epicycloids, and hypocycloids. In the 11th section are considered the problems connected with motions in orbits where the center of force is disturbed, or where the moving body is disturbed by other forces. Until calculus of variations was invented by Lagrange in 1755, it was impossible to do more than sketch out the principles on which the problem should be solved, and Laplace in his Mécanique Céleste was the first to work out most of the questions in any detail. Newton commences by considering the disturbance produced by the mutual action of two bodies revolving around one another. He then proceeds to consider the problem of three or more bodies which mutually attract one another. He first solves the question completely if the force of attraction varies directly as the distance. He next takes the case of the three bodies moving under their mutual attractions as in nature.
This problem has not been yet solved generally, but in Newton's day it was beyond any analysis of which he had the command. He contrived, however, to work out roughly the chief effects of the disturbing action of the sun on the motion of the moon, proposition 66. This proposition was singled out by Lagrange as the most striking single illustration of the genius of Newton.
To this proposition 22 corollaries are appended in which it is applied to determine the motion in longitude, in latitude, the annual equation, the motion of the apse line and of the nodes, the evection, the change in inclination of the plane of the lunar orbit, the precession of the equinoxes, and the theory of the tides. The greater part of the third book consists of the numerical application of these principles to the case of the moon and the earth. Lastly, Newton shewed how from the motion of the nodes of the interior constitution of the body could be roughly determined. Up to this point Newton had generally treated the bodies with which he dealt as if they were particles. He now proceeds in section 12 to consider the attraction of spherical masses which are either of uniform density or whose density at any point is a single valued function of the distance of the point from the center of the sphere. These are worked out for any law of attraction. In section 13, he gives some general theorems on the theory of attractions and on some propositions dealing with the attractions of solids of revolution. But these problems are almost insoluble without the aid of the infinitesimal calculus, and the Newtonian account of them is incomplete. The 14th section contains a statement of some theories and experiments in physical optics, and a solution by geometry of some problems in geometrical optics, particularly on the form of aplanatic refracting surfaces of revolution. The second book of the Principia is concerned with hydromechanics, and especially with motion in a resisting medium. These questions are not worked out so completely as those treated in the first book, and though this book provided the basis on which much of the subsequent work of Daniel Bernoulli, Clairaut, D'Alembert, Euler, and Laplace were erected, it is not of the same epoch-making character as the first book. This book is divided into 9 sections. The motion of bodies in a medium where the resistance varies directly as the velocity is considered in the first section. The motions where resistance varies as the square of the velocity is discussed in the second section. The motion where the resistance can be expressed as a sum of 2 terms, one of which varies as the velocity and the other as the square of the velocity, is dealt with in the third section. The second section contains proposition 25, a construction for the shape of the solid of least resistance. No proof is given, and it had been long somewhat of a mystery to know how Newton had contrived to solve the problem without the use of calculus of variations. Newton's demonstrations, there are 2 of them, have been recently discovered in the Portsmouth collection. The fourth section is devoted to a spiral motion in a resisting medium. The fifth to the theory of hydrostatics and elastic fluids. The sixth to the motion of pendulums in a resisting medium. The seventh to hydrodynamics, especially to the motion of projectiles in air and other fluids. The eighth to the theory of waves, including the principles from which the chief effects of the wave hypotheses in light and sound are calculated, and in particular the velocity of sound is determined. In the 9th section, Newton discusses the Cartesian theory of vortices. He begins by shewing that if there were no internal friction, the motion would be impossible. He must therefore assume some law of friction, and as a working hypothesis he supposes that the resistance arising from want of lubricity in the parts of a fluid is caetis paribus, proportional to the velocity of which the parts of the fluid are separated from each other. This hypothesis, as he himself remarks, is probably not altogether correct, but he thinks that it will give a general idea of the motion. He next proves that on this hypothesis that the motion would be unstable. He must therefore suppose that some constraining force prevents this catastrophe, and he then shews that in that case Kepler's third law could not be true. Lastly, he shews by independent reasoning that the hypothesis must lead to results which are inconsistent with Kepler's other 2 laws, and that both the vortices and the motion of the planets would necessarily be unstable. Several continental mathematicians made attempts to modify the Cartesian hypothesis so as to avoid these conclusions, but they could never explain one phenomenon without introducing fresh difficulties. It may be taken that by 1750 the Cartesian theory was finally abandoned. The third book is headed on the system of the world, and is concerned chiefly with the application of the results of the first book to the solar system. It is introduced by certain rules of philosophizing, and as a list of certain data obtained from astronomical observations. The rules are: 1. We may only assume as the possible causes of phenomenon such causes as are sufficient to explain them and are also verae causae. A verae causa being one which is capable of detection and such that its connection with the phenomenon can be ultimately shewn by independent evidence. 2. Effects of a similar kind must have similar causes. 3. Whatever properties of bodies are found by experience to be invariable should be assumed to be so in places where direct experiments cannot be made. Newton commences by illustrating the universality of the law of gravitation, and sketches out the principles which lead him to think that the solar system is necessarily stable. He determines that the mass of the moon, the masses of the planets, their distances from the sun, and their figures. In the first edition he estimated, proposition 37, that the ratio of the mass of the moon to that of the earth was approximately that of 1 to 26. In the second and third editions this was altered to a ratio which is nearly that of 1 in 40. But except for the mass of the moon, he approximates to the results now known with astonishing closeness. He finds the disturbing force exerted by the sun and the moon, and considers the 5 chief irregularities in the orbit of the moon. He next discusses the solar and lunar tides, determines the precession of the equinoxes, and finally shews how the elements of a comet can be determined by these observations, and applies his results to certain comets. Before this time it had been commonly believed that the comets had nothing to do with the solar system, though in 1681 Dorfel had shewn that the path of the great comet of 1680 was a parabola having the sun at its focus. Lastly, the Principia is concluded by a general scholium containing the reflection on the constitution of the universe and on the eternal, the infinite, and perfect being by whom it is governed. The chief alterations in the second edition, published in 1713, were the substitutions of simpler proofs for some of the propositions in the second edition of the first book, a more full and accurate investigation found on some fresh experiments made by Newton about the year 1690, and the resistance of fluids in the seventh section of the second book, and the addition of a detailed examination of the causes of the precession of the equinoxes and the theory of comets in the third book. The chief alterations in the third edition, published in 1726, were in the scholium on fluxions, and the addition of a new scholium on the motion of the moon's nodes, Book 3, Proposition 53. End of footnote. The demonstrations throughout the work are geometrical, but to readers of ordinary ability are rendered unnecessarily difficult by the absence of illustrations and explanations, and by the fact that no clue is given to the method by which Newton arrived at his results. The reason why it was presented in a geometrical form appears to have been that the infinitesimal calculus was then unknown,
and had Newton used it to determine the results which were in themselves opposed to the prevalent philosophy of the time, the controversy as to the truth of his results would have been hampered by a dispute concerning the validity of the methods used in proving them.
He therefore cast the whole reasoning into a geometrical shape, which, if somewhat longer, can at any rate be made intelligible to all mathematical students. So closely did he follow the lines of Greek geometry that he constantly used graphical methods, and represented forces, velocities, and other magnitude in the Euclidean way, by straight lines, Book 1, Lemma 10, and not by certain number of units. The latter and modern method had been introduced by Wallis and must have been familiar to Newton. The effect of his confining himself rigorously to classical geometry is that the Principia is written in a language which is archaic even if not unfamiliar.
The adoption of geometrical methods in the Principia for purposes of demonstration does not indicate a preference on Newton's part for geometry over analysis as an instrument of research, for it is known now that Newton used the fluxional calculus in the first instance in finding some of the theorems, especially those towards the end of Book 1. And in Book 2, and in fact one of the most important uses of that calculus is stated in Book 2, Lemma 2.
But it is only just to remark that, at the time of its publication and for nearly a century afterwards, the differential and fluxional calculus were not fully developed, and did not possess the same superiority over the method he adopted by which they do now. And it is a matter of astonishment that when Newton did employ the calculus, he was able to use it to so good an effect. The ability shewn in the translation in a few months of theorems so numerous and of so great complexity into the language of the geometry of Archimedes and Apollonius is, I suppose, unparalleled in the history of mathematics. The printing of the work was slow, and it was not finally published till the summer of 1687. The whole cost was borne by Halley, who also corrected the proofs and even put his own researches on one side to press the printing forward. The conciseness, absence of illustrations, and synthetical character of the book restricted the numbers of those who were able to appreciate its value, and though nearly all competent critics admitted the validity of the conclusions, some little time elapsed before it affected the current beliefs of educated men. I should be inclined to say, but on this point opinions differ widely, that within 10 years of its publication it was generally accepted in Britain as giving a correct account of the laws of the universe. It was similarly accepted within about 20 years on the continent, except in France, where the Cartesian hypothesis held its ground until Voltaire in 1738 took up the advocacy of the Newtonian theory. The manuscript of the Principia was finished by 1686. Newton devoted the remainder of that year to his paper on physical optics, the greater part of which is given up to the subject of diffraction. In 1687, James II, having tried to force the university to admit as a Master of Arts a Roman Catholic priest who refused to take oaths of supremacy and allegiance, Newton took a prominent part in resisting the illegal interference of the king, and was one of the deputation sent to London to protect the rights of the university. The active part taken by Newton in this affair led to his being, in 1689, elected member for the university. This parliament only lasted 13 months, and on its dissolution he gave up his seat. He was subsequently returned in 1701, but he never took any prominent part in politics. On his coming back to Cambridge in 1690, he resumed his mathematical studies and correspondence. If he lectured at this time, which is doubtful, it was on the subject matter of the Principia. The 2 letters to Wallis, which he explained his methods of fluxions and fluents, which were written in 1692 and published in 1693. Towards the close of 1692, and throughout the 2 following years, Newton had a long illness, suffering from insomnia and general nervous irritability. Perhaps he never quite regained his elasticity of mind, and, though after his recovery he shewed the same power in solving any question propounded to him, he ceased thenceforward to do original work of his own initiative, and it was somewhat difficult to stir him to activity in new subjects. In 1694, Newton began to collect data connected with the irregularities of the moon's motion, with the view of revising the part of the Principia which dealt with that subject. To render the observations more accurate, he forwarded to Flamsteed a table of corrections for refraction which he had previously made. This was not published till 1721, when Halley communicated it to the Royal Society. The original calculations of Newton and the papers connected with it are in the Portsmouth collection, and shew that Newton attained it by finding the path of a ray by means of quadratures in a manner equivalent to the solution of a differential equation. As an illustration of Newton's genius, I may mention that even as late as 1754 Euler failed to solve the same problem. In 1782, Laplace gave a rule for constructing such a table, and his results agree substantially with those of Newton. I do not suppose that Newton would in any case have produced much more original work after his illness, but his appointment in 1696 as warden and his promotion in 1699 to the mastership of the Mint at a salary of £1,500 a year brought his scientific investigations to an end, though it was only after this that many of his previous investigations were published in the form of books. In 1696 he moved to London. In 1701 he resigned the Lacazian chair, and in 1703 he was elected president of the Royal Society. End of section 25. Recording by Paul King, Oakville, Ontario. pjk.scripts.mit.edu/pkj. Chapter 16, Part 3 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This reading is by Paul King, pjk.scripts.mit.edu/pkj. A Short Account of the History of Mathematics by W. Rouse Ball. Chapter 16. The Life and Works of Newton, Part 3. In 1704 Newton published his Optics, which contains the results of papers already mentioned. The first edition of this book were appended to two minor works which have no special connection with optics, one being on cubic curves, the other on the quadrature of curves and on fluxions. Both of them were old manuscripts with which his friends and pupils were familiar, but they were here published urbi et orbi for the first time. The first of these appendices is entitled Enumeratio Linearum Tertii Ordinis. The object seems to be to illustrate the use of analytical geometry, and as the application to conics was well known, Newton selected the theory of cubics. He begins with some general theorems, and classifies curves according as to whether their equations are algebraical or transcendental, the former being cut by a straight line in a number of points, real or imaginary, equal to the degree of the curve, the latter being cut by a straight line in an infinite number of points. Newton then shews that many of the most important properties of conics have their analogues in the theory of cubics, and he discusses the theory of asymptotes in curvilinear diameters. After these general theorems he commences his detailed examination of cubics by pointing out that a cubic must have at least one real point at infinity. If the asymptote or tangent at this point be a finite distance, it may be taken for the axis of y. This asymptote will cut the curve in 3 points altogether, of which at least 2 are at infinity. If the third point be a finite distance, then, by one of his general theorems on asymptotes, the equation can be written in the form of xy squared plus hy equals ax cubed plus bx squared plus cx plus d, where the axes of x and y are the asymptotes of the hyperbola, which is the locus of the middle points of all chords drawn parallel to the axis of y, while if on the third point in which this asymptote cuts the curve be also at infinity, the equation can be written in the form xy equals ax cubed plus bx squared plus cx plus d. Next, he takes the case where the tangent at the real point at infinity is not at a finite distance. A line parallel to the direction in which the curve goes to infinity may be taken as the axis of y. Any such line will cut the curve in 3 points altogether, of which one is by hypothesis at infinity, and one is necessarily at a finite distance. He then shews that if the remaining point in which this line cuts the curve be at a finite distance, the equation can be written in the form y squared equals ax cubed plus bx squared plus cx plus d, while if it be at an infinite distance, the equation can be written in the form y equals ax cubed plus bx squared plus cx plus d. Any cubic is therefore reducible to one of the 4 characteristic forms. Each of these forms is then discussed in detail, and the possibility of the existence of double points, isolated ovals, etc. is worked out. The final result is that in all there are 78 possible forms which a cubic may take. Of these, Newton enumerated only 72. 4 of the remainder were mentioned by Stirling in 1717, and one by Nicole in 1731, and one by Nicholas Bernoulli at about the same time. In the course of the work Newton states the remarkable theorem that just as the shadow of a circle cast by a luminous point on a plane gives rise to all the conics, so the shadows of the curves represented by the equation y squared equals ax cubed plus bx squared plus cx plus d give rise to all the cubics. This remained an unsolved puzzle until 1731, when Nicole and Clairaut gave demonstrations of it. A better proof is that given by Murdoch in 1740, which depends on the classification of these curves into 5 species according to as to whether their points of intersection with the axis of x are real and unequal, real and 2 of them equal, 2 cases, real and all equal, or finally 2 imaginary and 1 real. In this tract, Newton also discusses double points in the plane and at infinity, and the description of curves satisfying given conditions, and the graphical solution of problems by the use of curves. The second appendix to the Optics is entitled De Quadratura Curvarum. Most of it had been communicated to Barrow in 1668 or 1669, and probably was familiar to Newton's pupils and friends from that time onwards. It consists of 2 parts. The bulk of the first part is a statement of Newton's method of effecting the quadrature and the rectification of curves by means of infinite series. It is noticeable as containing the earliest use in print of literal indices and also the first printed statement of the binomial theorem. But these are introduced only incidentally. The main object is to give rules for developing a function of x in a series of ascending powers of x, so as to enable mathematicians to effect the quadrature of any curve in which the ordinate y can be expressed as an explicit algebraical function of the abscissa x. Wallis had shewn how this quadrature could be found when y was given as a sum of a number of multiples of powers of x, and Newton's rules of expansion here established rendered possible the similar quadrature of any curve whose ordinate can be expressed as a sum of an infinite number of such terms. In this way he effects the quadrature of the curves y equals a squared divided by the quantity b plus x, y equals the square root of a squared plus or minus x squared, or y equals the square root of x minus x squared, or y equals the square root of 1 minus ax squared divided by the square root of 1 minus bx squared. But the results are of course expressed as infinite series. He then proceeds to curves whose ordinate is given as an implicit function of the abscissa, and he gives a method by which y can be expressed as an infinite series in ascending powers of x, but the application of the rule to any curve demands in general such complicated numerical calculations as to render it of little value. He concludes this part by shewing that the rectification of a curve can be effected in a somewhat similar way. His process is equivalent to finding the integral with regard to x of the square root of 1 plus y squared in the form of an infinite series. I should add that Newton indicates the importance of determining whether the series are convergent, an observation far in advance of his time, but he knew of no general test for the purpose, and in fact it was not until Gauss and Cauchy took up the question that the necessity of such limitations were commonly recognized. The part of the appendix which I have just described is practically the same as Newton's manuscript De Analysi per Equationes Numero Terminorum Infinitas, which was subsequently printed in 1711. It is said that this was originally intended to form an appendix to Kinckhuysen's Algebra. The substance of it was communicated to Barrow and by him to Collins in letters of July 31st and August 12, 1669, and a summary of part of it was included in a letter of October 24, 1676, sent to Leibniz. It should be read in connection with Newton's Methodus Differentialis published in 1736. Some additional theorems are there given, and he discusses his method of interpolation, which had been briefly described in the letter of October 24, 1676. The principle is this: if y equals phi of x be a function of x, and if when x is successively put equal to a1, a2, and so on, the values of y be known, and be b1, b2, and so on, then a parabola whose equation is y equals p plus qx plus rx squared plus so on can be drawn through the points a1, b1,
a2, b2,
and so on, and the ordinate of this parabola may be taken as an approximation to the ordinate of the curve. The degree of the parabola will of course be one less than the number of the given points. Newton points out that in this way the areas of any curves can be approximately determined. The second part of this appendix to the optics contained in a description of Newton's method is fluxions. This is best considered in connection with Newton's manuscript on the same subject, which was published by John Coulson in 1736, and of which it is a summary. The fluxional calculus is one form of the infinitesimal calculus expressed in a certain notation, just as the differential calculus is another aspect of the same calculus expressed in a different notation. Newton assumed that all geometrical magnitudes must be conceived as generated by continuous motion. Thus a line may be considered as generated by the motion of a point, a surface by that of a line, a solid by that of a surface, a plane angle by the rotation of a line, and so on. The quantity thus generated was defined by him as the fluent or flowing quantity. The velocity of the moving magnitude was defined as the fluxion of the fluent. This seems to be the earliest definite recognition of the idea of a continuous function, though it had been foreshadowed in some of Napier's papers. The following is a summary of Newton's treatment of fluxions. There are two kinds of problems. The object of the first is to find the fluxion of a given quantity, or more generally, the relation of the fluents being given, to find the relation of their fluxions. This is equivalent to differentiation. The object of the second or inverse method of fluxions is from the fluxion or some relations involving it to determine the fluent, or more generally an equation being proposed exhibiting the relation of the fluxions of quantities to find the relations of those quantities or fluents to one another. This is equivalent either to integration, which Newton termed the method of quadrature, or to the solution of a differential equation, which was called by Newton the inverse method of tangents. The methods for solving these problems are discussed at considerable length. Newton then went on to apply these results to questions connected with the maxima and minima of quantities, the method of drawing tangents to curves, and the curvature of curves, namely, the determination of the center of curvature, the radius of curvature, and the rate at which the radius of curvature increases. He next considered the quadrature of curves and the rectification of curves. In finding the maximum and minimum of functions of one variable, we regard the change of sign of the difference between two consecutive values of the function as the true criterion. But his argument is that when a quantity increasing has attained its maximum, it can have no further increment, or when decreasing it has attained its minimum and can have no further decrement. Consequently, the fluxion must be equal to nothing. It has been remarked that neither Newton nor Leibniz produced a calculus, that is, a classified collection of rules, and that the problems they discussed were treated from first principles. That, no doubt, is the usual sequence in the history of such discoveries, though the fact is frequently forgotten by subsequent writers. In this case, I think the statement so far as Newton's treatment of the differential or fluxional part of the calculus is concerned is incorrect, as the foregoing account sufficiently shews. If a flowing quantity or fluent were represented by x, Newton denoted its fluxion by x dot, and the fluxions of x dot, or second function of x, by x dot dot, and so on. Similarly, the fluent of x was denoted by x written in a box, or sometimes by x prime, or x inside square brackets. The infinitely small part by which a fluent such as x increased in a small interval of time measured by omicron was called the moment of the fluent, and its value was shown to be x dot omicron. Newton adds the important remark that thus we may in any problem neglect the terms multiplied by the second and higher powers of omicron, and we can always find an equation between the coordinates of x, y of a point on a curve and their fluxions x dot, y dot. It is an application of this principle which constitutes one of the chief values of calculus. For if we desire to find the effect produced by several causes of a system, then if we can find the effect produced by each cause when acting alone in a very small time, the total effect produced in that time will be equal to the sum of the separate effects. I should here note the fact that Vince and other English writers in the 18th century used x dot to denote the increment of x and not the velocity with which it increased. That is, x dot in their writing stands for what Newton would have expressed by x dot omicron, and what Leibniz would have written as dx. I need not discuss in detail the manner in which Newton treated the problem above mentioned. I will only add that in spite of the form of his definition, the introduction into geometry of the idea of time was evaded by supposing that some quantity, e.g. the abscissa of a point on a curve, increased equably, and the required results then depend on the rate at which other quantities, e.g. the ordinate or the radius of curvature, increased relatively to the one so chosen. The fluent so chosen is what we now call the independent variable. Its fluxion was termed the principal fluxion, and of course if it were denoted by x, then x dot was constant, and consequently x dot dot equaled 0. There is no question that Newton used the method of fluxions in 1666, and it is practically certain that accounts of it were communicated in manuscript to friends and pupils from and after 1669. The manuscript, from which most of the above summary has been taken, is believed to have been written between 1671 and 1677, and to have been in circulation at Cambridge from that time onward. It was unfortunate that it was not published at once. Strangers at a distance naturally judged of the method by the letter to Wallis in 1692 or by the Tractatus de Quadratura Curvarum, and were not aware that it had been so completely developed at an earlier date. This was the cause of numerous misunderstandings. At the same time it must be added that all mathematical analysis was leading up to the idea and methods of the infinitesimal calculus. Foreshadowings of the principles and even of the language of that calculus can be found in the writings of Napier, Kepler, Cavalieri, Pascal, Fermat, Wallis, and Barrow. It was Newton's good luck to come at a time when everything was ripe for the discovery, and his ability enabled him to construct almost at once a complete calculus. The notation of the fluxional calculus is for most purposes less convenient than that of the differential calculus. The latter was invented by Leibniz in 1675 and published in 1684, some 9 years before the earliest printed account of Newton's method of fluxions. But the question whether the general idea of the calculus expressed in that notation was obtained by Leibniz from Newton, or whether it was invented independently, gave rise to a long and bitter controversy. The leading facts are given in the next chapter. The question is one of considerable difficulty, but I will here only say that from what I have read of the voluminous literature on the question, I think on the whole it points to the fact that Leibniz obtained the idea of the differential calculus from a manuscript of Newton's which he saw in 1675. I believe, however, that the prevalent opinion is that the inventions were independent. The remaining events of Newton's life require little or no comment. In 1705 he was knighted. From this time onward he devoted much of his leisure to theology and wrote at great length on the prophecies and predictions, subjects which had always been of interest to him. His Universal Arithmetic was published by Whiston in 1707, and his Analysis by Infinite Series in 1711, but Newton had nothing to do with the preparation of either of these for the press. His evidence before the House of Commons in 1714 on the determination of longitude at sea marks an important epoch in the history of navigation. The dispute with Leibniz as to whether he had derived the ideas of the differential calculus from Newton or invented it independently originated about 1708 and occupied much of Newton's time, especially between the years 1709 and 1716. In 1709 Newton was persuaded to allow Cotes to prepare the long talked of second edition of the Principia. It was issued in March of 1713. A third edition was published in 1726 under the direction of Henry Pemberton. In 1725 Newton's health began to fail. He died on March 20th, 1727, and 8 days later was buried with great state in Westminster Abbey. His chief works, taking them in their order of publication, are the Principia, published in 1687, the Optics, with appendices on cubic curves, the quadrature and rectification of curves by use of the infinite series, and the method of fluxions, published in 1704, and the Universal Arithmetic, published in 1707, the Analysis per series, fluxions, etc., published in 1711, Lectiones Opticae, published in 1729, Method of Fluxions, etc., i.e. Newton's manuscript on fluxions, translated by J. Coulson and published in 1736, and the Methodes Differentiales, also published in 1736. In appearance Newton was short, and towards the close of his life rather stout, but well set, with a square lower jaw, brown eyes, and a very broad forehead, and a rather sharp features. His hair turned grey before he was 30, and remained thick and white and silver till his death. As to his manners, he dressed slovenly, was rather languid, and was often so absorbed in his own thoughts as to be anything but a lively companion. Many anecdotes of his extreme absence of mind when engaged in any investigation have been preserved. Thus, once when riding home from Grantham he dismounted to lead his horse up a steep hill. When he turned at the top to remount he found that he had the bridle in his hand while his horse had slipped it and gone away. Again, on the few occasions when he sacrificed his time to entertain his friends, if he left them to get more wine or for any similar reason, he would as often as not be found after the lapse of some time working out a problem, oblivious alike of his expectant guests and of his errand. He took no exercise, indulged in no amusements, and worked incessantly, often spending 18 or 19 hours out of the 24 in writing. In character he was religious and conscientious, with an exceptionally high standard of morality, having, as Bishop Brunet said, the whitest soul he ever knew. Newton was always perfectly straightforward and honest, but in his controversies with Leibniz, Hooke, and others, though scrupulously just, he was not generous, and it would seem that he had frequently took offence at a chance of expression when none was intended. He modestly attributed his discoveries largely to the admirable work done by his predecessors, and once explained that if he had seen farther than other men it was only because he stood on the shoulders of giants. He summed up his own estimate of his work in the sentence, "I do not know what I may appear to the world, but to myself I seem to have been only like a boy, playing on the seashore and diverting myself in now and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me." He was morbidly sensitive to being involved in any discussions. I believe that with the exception of his papers on optics, every one of his works was published only under pressure from his friends and against his own wishes. There are several instances of his communicating papers and results on condition that his name should not be published. Thus, when in 1669 he had, at Collier's request, solved some problems on the harmonic series and on annuities which had previously baffled investigation, he only gave permission that his results should be published, so it be, as he says, without my name to it, for I see not what there is desirable in public esteem. Were I able to acquire and maintain it, it would perhaps increase my acquaintance, the thing which I chiefly study to decline. In intellect he has never been surpassed and probably never been equalled. Of this his extant works are the only proper test. Perhaps the most wonderful single illustration of his powers was the composition in 7 months of the first book of the Principia. As specific illustrations of his ability I may mention his solutions of the problems of Pappus, of John Bernoulli's challenge, and of the question of orthogonal trajectories. The problem of Pappus is to find the locus of a point such that the rectangle under its distances from two given straight lines shall be in a given ratio to the rectangle under its distances from two other given straight lines. Many geometricians from the time of Apollonius had tried to find a geometrical solution and had failed, but what had proved insuperable to his predecessors seemed to have presented little difficulty to Newton, who gave an elegant demonstration as that the locus was a conic. Geometry, said Lagrange, was, when recommending the study of analysis to his pupils, is a strong bow, but it is one which only a Newton could fully utilize. As another example I may mention that in 1696 John Bernoulli challenged mathematicians 1. To determine the Brachistochrone, and 2. To find a curve such that if any line drawn from a fixed point O cut it in P and Q, then OP to the power n plus QOQ to the power n would be a constant. Leibniz solved the first of these questions after an interval of rather more than 6 months, and then suggested that they should be sent as a challenge to Newton and others. Newton received the problems on January 29, 1697, and the next day gave the complete solutions of both, at the same time generalizing the second question. An almost exactly similar case occurred in 1716 when Newton was asked to find the orthogonal trajectory of a family of curves. In 5 hours Newton solved the problem in the form in which it was propounded to him, and laid down in the principles for finding trajectories. It is almost impossible to describe the effect of Newton's writings without being suspected of exaggeration. But if the state of mathematical knowledge in 1669 or at the death of Pascal or Fermat be compared with what was known in 1687, it will be seen how immense was the advance. In fact, we may say that it took mathematicians half a century or more before they were able to assimilate the work which Newton produced in those 20 years. In pure geometry, Newton did not establish any new methods, but no modern writer has shewn the same power in using those of classical geometry. In algebra and the theory of equations, he introduced the system of literal indices, established the binomial theorem, created no inconsiderable part of the theory of equations. One rule which he enunciated in this subject remained, till a few years ago, an unsolved riddle, which had overtaxed the resources of succeeding mathematicians. In analytical geometry he introduced the modern classification of curves into the algebraical and transcendental, and established many of the fundamental properties of asymptotes, multiple points, and isolated loops, illustrated by a discussion of cubic curves. The fluxional or infinitesimal calculus was invented by Newton in or before the year 1666, and circulated in manuscripts amongst his friends in and after the year 1669, though no account of the method was printed till 1693. The fact that the results are nowadays expressed in a different notation has led to Newton's investigations on this subject being somewhat overlooked. Newton further was the first to place dynamics on a satisfactory basis, and from dynamics he deduced the theory of statics. This was in the introduction to the Principia published in 1687. The theory of attractions, the application of the principles of mechanics to the solar system, the creation of physical astronomy, and the establishment of the law of universal gravitation are wholly due to him and were first published in the same work. The particular questions connected with the motion of the earth and the moon were worked out as fully as was then possible. The theory of hydrodynamics was created in the second book of the Principia, and he added considerably to the theory of hydrostatics, which may be said to have been first discussed by Pascal. The theory of the propagation of waves, and in particular the application to determine the velocity of sound, is due to Newton and was published in 1687. In geometrical optics he explained amongst other things the decomposition of light and the theory of the rainbow. He invented the reflecting telescope, known by his name, and the sextant. In physical optics he suggested and elaborated the emission theory of light. The above list does not exhaust the subjects he investigated, but it will serve to illustrate how marked was his influence on the history of mathematics. On his writings and on their effects it will be enough to quote the remarks of two or three of those who were subsequently concerned with the subject matter of the Principia. Lagrange described the Principia as the greatest production of the human mind, and said that he felt dazed that such an illustration of what a man's intellect might be capable. In describing the effect of his own writings and those of Laplace, it was a favourite remark of his that Newton was not only the greatest genius that had ever existed, but he was also the most fortunate. For as there is but one universe, it can happen but to one man in the world's history to be the interpreter of its laws. Laplace, who is in general very sparing of his praise, makes of Newton the one exception, and the words in which he enumerates the causes which will always assure the Principia's a preeminence above all other productions of the human intellect have often been quoted. Not less remarkable is the homage rendered by Gauss. For other great mathematicians or philosophers he used the epithets Magnus or Clarus or Clarissimus. For Newton alone he kept the prefix summus. Finally, Biot, who had made a special study of Newton's works, sums up his remarks by saying, Comme géométrie et comme expérimentateur, Newton est sans égal. Par la réunion de ces deux genres de génie et leur plus haut degré, elle est sans exemple. End of section 26. Recording by Paul King, Oakville, Ontario. pjk.scripps.mit.edu/pkj. Chapter 17 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripps.mit.edu/pkj. A short account of the history of mathematics by W. W. Rouse Ball. Chapter 17. Leibniz and the mathematicians of the first half of the 18th century. Part 1. I have briefly traced in the last chapter the nature and extent of Newton's contributions to science. Modern analysis is however derived directly from the works of Leibniz and the elder Bernoullis, and it is immaterial to us whether the fundamental ideas of it were obtained by them from Newton or discovered independently. The English mathematicians of the years considered in this chapter continued to use the language and notation of Newton. They are thus somewhat distinct from their continental contemporaries, and I have therefore grouped them together in a section by themselves. Leibniz and the Bernoullis. Leibniz. Gottfried Wilhelm Leibniz was born at Leipzig on June 21st, 1646, and died at Hanover on November 14th, 1716. His father died before he was 6, and the teaching at the school to which he was then sent was inefficient, but his industry triumphed over all difficulties. By the time he was 12 he had taught himself to read Latin easily, and had begun Greek, and before he was 20 he had mastered the ordinary textbooks on mathematics, philosophy, theology, and law. Refused the degree of Doctor of Laws at Leipzig by those who were jealous of his youth and learning, he moved to Nuremberg. An essay which he there wrote on the study of law was dedicated to the Elector of Mainz, and led to his appointment by the Elector on a commission for the revision of some statutes, from which he was subsequently promoted to the diplomatic service. In the latter capacity he supported unsuccessfully the claims of the German candidate for the crown of Poland. The violent seizure of various small places in Alsace in 1670 excited universal alarm in Germany as to the designs of Louis XIV, and Leibniz drew up a scheme by which it was proposed to offer German cooperation if France liked to take Egypt and use the possession of that country as a basis for attack against Holland in Asia, on the condition that Germany was to be left undisturbed by France. This bears a curious resemblance to the similar plan by which Napoleon I proposed to attack England. In 1672 Leibniz went to Paris on the invitation of the French government to explain the details of the scheme, but nothing came of it. At Paris he met Huygens, who was then residing there, and their conversation led him to study geometry, which he described as opening a new world to him, though he had as a matter of fact previously written some tracts on various minor points in mathematics, the most important of them being a paper on combinations written in 1668, and a description of a new calculating machine. In January 1673 he was sent on a political mission to London, where he stopped some months and made the acquaintance of Oldenburg, Collins, and others. It was at this time that he communicated the memoir to the Royal Society, in which he was found to have been forestalled by Mouton. In 1673 the Elector of Mainz died, and in the following year Leibniz entered the service of the Brunswick family. In 1676 he again visited London, and then moved to Hanover, where till his death he occupied the well-paid post of librarian in the Ducal Library. His pen was thenceforth employed in all the political matters which affected the Hanoverian family, and his services were recognized by honours and distinctions of various kinds. His memoranda on the various political, historical, and theological questions which concerned the dynasty during the 40 years from 1673 to 1713 form a valuable contribution to the history of that time. His appointment in the Hanoverian service gave him an increased leisure for his favourite pursuits. Leibniz used to assert that as the first fruit of his increased leisure he invented the differential and integral calculus in 1674, but the earliest traces of the use of it in his extant notebooks do not occur till 1675, and it was not till 1677 that we find it developed into a consistent system. He was not published until 1684. Nearly all his mathematical papers were produced within the 10 years, from 1682 to 1692, most of them in a journal called the Acta Eruditorum, which he and Otto Menck had founded in 1682, and which had a wide circulation on the continent. Leibniz occupies at least as large a place in the history of philosophy as he does in the history of mathematics. Most of his philosophical writings were composed in the last 20 or 25 years of his life, and the point as to whether his views were original or whether they were appropriated from Spinoza, whom he visited in 1676, is still in question among philosophers, though the evidence seems to point to the originality of Leibniz. As to Leibniz's system of philosophy, it will be enough to say that he regarded the ultimate elements of the universe as individual percipient beings who he called monads. According to him, the monads are centers of force, and substance is force, while space, matter, and motion are merely phenomenal. Finally, the existence of God is inferred from the existing harmony among the monads. His services to literature were almost as considerable as those to philosophy. In particular, I may single out his overthrow of the then prevalent belief that Hebrew was the primeval language of the entire human race. In 1700, the Academy of Berlin was created on his advice, and he drew up the first body of statutes for it. On the accession in 1714 of his master George I to the throne of England, Leibniz was practically thrown aside as a useless tool. He was forbidden to come to England, and the last 2 years of his life were spent in neglect and dishonour. He died at Hanover in 1716. He was over fond of money and personal distinctions, was unscrupulous, as might be expected of a professional diplomat of that time, but possessed singularly attractive manners, and all who once came under the charm of his personal presence remained sincerely attached to him. His mathematical reputation was largely augmented by the eminent position that he occupied in diplomacy, philosophy, and literature, and the power thence derived was considerably increased by his influence in the management of the Acta Eruditorum, which I believe was the only private scientific journal of the time. The last years of his life, from 1709 to 1716, were embittered by the long controversy with John Keill, Newton, and others as to whether he had discovered the differential calculus independently of Newton's previous investigations, or whether he had derived the fundamental idea from Newton and merely invented another notation for it. The controversy occupies a place in the scientific history of the early years of the 18th century, quite disproportionate to its true importance, but it so materially affected the history of mathematics in Western Europe that I feel obliged to give the leading facts, though I am reluctant to take up so much space with questions of a personal character. The case in favour of the independent invention by Leibniz is stated in Gerhardt's Leibnizissimus Mathematische Schriften in Biot and Lefort's edition of the Commercium Epistocolum, Paris, 1856. The arguments on the other side are given in H. Sloman's Leibnizens Anspruch auf die Erfindung der Differentialrechnung, Leipzig, 1857. Of which an English translation with the additions by Dr. Sloman was published at Cambridge in 1860. The history of the invention of the calculus is given in an article of it in the 9th edition of the Encyclopaedia Britannica, and in P. Manson's Esquisse de l'histoire du calcul infinitésimal, Gand, 1887. End of footnote. The ideas of the infinitesimal calculus can be expressed either in the notation of fluxions or in that of differentials. The former was used by Newton in 1666 and communicated in manuscript to his friends and pupils from 1669 onwards, but no distinct account of it was printed until 1693. The earliest use of the latter in the notebooks of Leibniz is dated 1675 and was employed in the letters sent to Newton in 1677, and an account of it was printed in the memoir of 1684 described below. There is no question that the differential notation is due to Leibniz, and that the sole question is as to whether the general idea of the calculus was taken from Newton or discovered independently. The case in favour of the independent invention by Leibniz rests on the ground that he published a description of his method some years before Newton printed anything on fluxions, that he always alluded to the discovery as being his own invention, and that for many years this statement was unchallenged. Well, of course, there must be a strong presumption that he acted in good faith. To rebut this case, it is necessary to shew that 1. He saw some of Newton's papers on the subject in or before 1675 or at least 1677, and 2. That he thence derived the fundamental ideas of the calculus. The fact that his claim was unchallenged for some years, in my opinion, in the particular circumstances of the case is immaterial. That Leibniz saw some of Newton's manuscripts was always intrinsically probable, but when, in 1849, C.J. Gerhardt examined Leibniz's papers, he found among them a manuscript copy, the existence of which had been previously unsuspected, in Leibniz's handwriting, of extracts from Newton's De Analysi per Equationes Numero Terminorum Infinitas, which was printed in the De Quadratura Curvarum in 1704, together with notes on their expression in the differential notation. The question of the date at which these extracts were made is therefore all important. It is known that a copy of Newton's manuscript had been sent to Tschirnhausen in May 1675, and that in that year he and Leibniz were engaged together in a piece of work. It is not impossible that these extracts were made then. It is also possible that they may have been made in 1676, for Leibniz discussed the question of analysis by infinite series with Collins and Oldenburg in that year, and it is a priori probable that they would have then shewn him the manuscript of Newton on that subject, a copy of which was possessed by one or both of them. On the other hand, it may have been supposed that Leibniz made the extracts from the printed copy in or after 1704. Leibniz shortly before his death admitted in a letter to Conti that in 1676 Collins had shown him some Newtonian papers, but implied that they were of little or no value. Presumably he referred to Newton's letters of June 13th and October 24th, 1676, and to the letter of December 10th, 1672, on the method of tangents, extracts from which accompanied the letter of June 13th. But it was curious that on the receipt of these letters Leibniz should have made no further inquiries, unless he was already aware from other sources of the method followed by Newton. Whether Leibniz made no use of the manuscript from which he had copied extracts, or whether he had previously invented the calculus, are questions on which at this distance of time no direct evidence is available. It is, however, worth noting that the unpublished Portsmouth papers shew that when in 1711 Newton went carefully into the whole dispute, he picked out this manuscript as the one which had probably somehow fallen into the hands of Leibniz. At that time there was no direct evidence that Leibniz had seen this manuscript before it was printed in 1704, and accordingly Newton's conjecture was not published. But Gerhardt's discovery of the copy made by Leibniz tends to confirm the accuracy of Newton's judgment in the matter. It is said by some that to a man of Leibniz's ability the manuscript, especially if supplemented by the letter of December 10, 1672, would supply sufficient hints to give him a clue to the methods of the calculus, though as fluxional notation is not employed in it, anyone who used it would have to invent a notation, but this is denied by others. There was at first no reason to suspect the good faith of Leibniz, and it was not until the appearance in 1704 of an anonymous review of Newton's tract on quadrature, in which it was implied that Newton had borrowed the idea of the fluxional calculus from Leibniz, that any responsible mathematician questioned the statement that Leibniz had invented the calculus independently of Newton. It is universally admitted that there was no justification or authority for the statements made in this review, which was rightly attributed to Leibniz, but the subsequent discussion led to a critical examination of the whole question, and doubt was expressed as to whether Leibniz had not derived the fundamental idea from Newton. The case against Leibniz, as it appeared to Newton's friends, was summed up in the Commercium Epistolicolum issued in 1712. The evidence there collected may be inconclusive, but at any rate detailed references are given for all facts mentioned. No such summary with facts, dates, and references of the case for Leibniz was issued by his friends, but John Bernoulli attempted to indirectly weaken the evidence by attacking the personal character of Newton. This was in a letter dated June 7, 1713. The charges were false, and when pressed for an explanation of them, Bernoulli most solemnly denied having written the letter. In accepting the denial, Newton added in a private letter to him the following remarks, which are interesting as giving Newton's account of why he was last induced to take any part in the controversy. "I have never," said he, "grasped at the fame among foreign nations, but I am very desirous to preserve my character for honesty, for which the author of that epistle, as if by the authority of a great judge, has endeavoured to wrest from me. Now that I am old, I have little pleasure in mathematical studies, and I have never tried to propagate my opinions over the world, but I have rather taken care not to involve myself in disputes on account of them." Leibniz's defense or explanation of his silence is given in the following letter, dated April 19, 1716, from him to Conti. "Pour répondre de point à point à l'ouvrage publié contre moi, il falloit un autre ouvrage aussi grand pour le moi que celui-là. Il falloit entrer dans un grand détail des quantités de ministres passés il y a 30 et 40 ans, dont je ne me souviens guère. Il me falloit chercher mes vieilles lettres dont plusieurs se sont perdues. Outre que le plus souvent je n'ai point gardé les minutes miennes, et les autres sont salvées dans une grande tasse à papier que je ne peux voir débrouiller qu'avec du temps et de la patience, mais je n'en avoir guère le loisir, étant chargé présentement d'occupations d'une toute autre nature." The death of Leibniz in 1716 only put a temporary stop to the controversy which was bitterly debated for many years later. The question is one of great difficulty. The evidence is conflicting and circumstantial, and everyone must form for themselves the opinion which seems most probable. I think the majority of modern writers would accept the view that probably Leibniz's invention of the calculus was independent of that of Newton, and everyone will hope that they are right. For myself, I cannot however but think it probable that Leibniz read Newton's manuscript De Analysi before 1677 and was materially assisted by it. His unacknowledged possession of a copy of part of one of Newton's manuscripts may be explicable, but the admitted fact that on more than one occasion he deliberately altered or added to important documents before publishing them seems to me to make his own testimony of little value. In mitigation of his conduct I can only say that it must be recollected that what he is alleged to have received was rather a series of hints than an account of the calculus, and it seems to me that the facts that he did not publish his results of 1677 until 1684, and that the notation and subsequent development of it were all of his own invention, may have led him 30 years later to minimize any assistance which he obtained originally and finally consider that it was immaterial. If we must confine ourselves to one system of notation, then there can be no doubt that that which was invented by Leibniz is better fitted for most of the purposes to which the infinitesimal calculus is applied than that of fluxions, and for some, such as the calculus of variations, it is indeed almost essential. It should be remembered, however, that at the beginning of the 18th century the methods of the infinitesimal calculus had not been systematized, and either notation was equally good. The development of that calculus was the main work of the mathematician of the first half of the 18th century. The differential form was adopted by continental mathematicians. The application of it by Euler, Lagrange, and Laplace to the principles of mechanics laid down in the Principia was the great achievement of the last half of that century, and finally demonstrated the superiority of the differential to the fluxional calculus. The translation of the Principia into the language of modern analysis and the filling in of the details of the Newtonian theory by the aid of that analysis were effected by Laplace. The controversy with Leibniz was regarded in England as an attempt by foreigners to defraud Newton of the credit of his invention, and the question was complicated on both sides by national jealousies. It was therefore natural, though it was unfortunate, that in England the geometrical and fluxional methods as used by Newton were alone studied and employed. For more than a century the English school was thus out of touch with continental mathematicians. The consequence was that, in spite of the brilliant band of scholars formed by Newton, the improvements in the methods of analysis gradually effected on the continent were almost unknown in Britain. It was not until 1820 that the value of analytical methods was fully recognized in England, and that Newton's countrymen again took any large share in the development of mathematics. Leaving now this long controversy, I come to the discussion of the mathematical papers produced by Leibniz, all the more important of which were published in the Acta Eruditorum. They are mainly concerned with the applications of the infinitesimal calculus and with various questions on mechanics. The only papers of first-rate importance which he produced are those on the differential calculus. The earliest of these was one published in the Acta Eruditorum for October 1684, in which he enunciated a general method for finding maxima and minima, and for drawing tangents to curves. One inverse problem, namely to find the curve whose subtangent is constant, was also discussed. The notation is the same as that with which we are familiar, and the differential coefficients of x to the power n and of products and quotients are determined. In 1686 he wrote a paper on the principles of the new calculus. In both of these papers the principle of continuity is explicitly assumed, while his treatment of the subject is based on the use of infinitesimals and not on that of the limiting value of ratios. In answer to some objections which were raised in 1694 by Bernard Nieuwentyt, who asserted that dy by dx stood for an unmeaning quantity like 0 over 0, Leibniz explained, in the same way as Barrow had previously done, that the value of dy by dx in geometry could be expressed as the ratio of two finite quantities. I think Leibniz's statement of the objects and methods of the infinitesimal calculus as contained in these papers, which are the three most important memoirs on it that he had produced, is somewhat obscure, and his attempt to place the subject on a metaphysical basis did not tend to clearness. But the notation he introduced is superior to that of Newton, and the fact that all the results of modern mathematics are expressed in the language invented by Leibniz has proved to be the best monument of his work. In 1686 and 1692 he wrote papers on osculating curves. These, however, contained some bad blunders, as for example the assertion that an osculating circle will necessarily cut a curve in 4 consecutive points. This error was pointed out by John Bernoulli, but in his article of 1692 Leibniz defended his original assertion and insisted that a circle could never cross a curve it touched it. In 1692 Leibniz wrote a memoir in which he laid the foundation of the theory of envelopes. This was further developed in another paper in 1694, in which he introduced for the first time the terms coordinates and axes of coordinates. Leibniz also published a good many papers on mechanical subjects, but some of them contain mistakes which shew that he did not understand the principles of the subject. Thus, in 1685 he wrote a memoir to find the pressure exerted by a sphere of weight W placed between two inclined planes of complementary inclinations, placed so that the lines of the greatest slope are perpendicular to the line of the intersection of the planes. He asserted that the pressure on each plane must consist of two components, unum quo decliviter descendere tensit, alterum quo planum declive premit. He further said that for metaphysical reasons that the sum of the two pressures must be equal to W. Hence, if R and R prime be the required pressures and alpha and 1/2 prime minus alpha the inclination of the planes, he finds that R minus 1/2 W multiplied by the quantity 1 minus sine alpha plus cos alpha and R prime equals 1/2 W multiplied by 1 minus cos alpha plus sine alpha. The true values are R equals W cos alpha and R prime equals W sine alpha. Nevertheless, some of his papers on mechanics are valuable. Of these, the most important were two, in 1689 and 1694, in which he solved the problem of finding an isochronous curve, one in 1697 on the curve of quickest descent. This was the problem sent as a challenge to Newton, and two in 1691 and 1692, in which he stated the intrinsic equation of the curve assumed by a flexible rope suspended from 2 points, i.e. the catenary, but gave no proof. This last problem had been originally proposed by Galileo. In 1689, that is 2 years after the Principia has been published, he wrote on the movements of the planets, which he stated were produced by a motion of the ether. Not only were the equations of motion which he obtained wrong, but his deductions from them were not even in accordance with his own axioms. In another memoir in 1706, that is nearly 20 years after the Principia had been written, he admitted that he had made some mistakes in his former paper, but adhered to his previous conclusions, and summed the matter up by saying, "It is certain that gravitation generates a new force at each instant to the centre, but the centrifugal force also generates another away from the centre. The centrifugal force may be considered in two aspects according as the movement is treated as along the tangent to the curve or as along the arc of the circle itself." It seems clear from this paper that he did not really understand the manner in which Newton had reduced the dynamics to an exact science. It is hardly necessary to consider his work on dynamics in further detail. Much of it is vitiated by a constant confusion between momentum and kinetic energy. When the force is passive, he uses the first, which he calls his vis mortua, as the measure of force. When the force is active, he uses the latter, the double of which he calls the vis viva. The series quoted by Leibniz comprise those of e to the x and log of 1 plus x, sine of x, versine of x, and the arctangent of x. All of these have been previously published, and he rarely, if ever, added any demonstrations. Leibniz, like Newton, recognized the importance of James Gregory's remarks on the necessity of examining whether infinite series are convergent or divergent, and proposed a test to distinguish the series whose terms are alternatively positive and negative. In 1693 he explained the method of expansion by indeterminate coefficients, though his applications were not free from error. To sum the matter up briefly, it seems to me that Leibniz's work exhibits great skill in analysis, but much of it is unfinished, and when he leaves his symbols and attempts to interpret his results, he frequently commits blunders. No doubt the demands of politics, philosophy, and literature on his time may have prevented him from elaborating any scientific subject completely, or writing any systematic exposition of his views, though they are no excuse for the mistakes of principle which occur so frequently in his papers. Some of his memoirs contain suggestions of methods which have now become valuable means of analysis, such as the use of determinants and of indeterminate coefficients. But when a writer of manifold interests like Leibniz throws out innumerable suggestions, some of them are likely to turn out valuable, and to enumerate these, which he never worked out, without reckoning the others, which are wrong, gives a false impression of the value of his work. But in spite of this, his title to fame rests on a sure basis, for it was he who brought the differential calculus into general use, and his name is inseparably connected with one of the chief instruments of analysis, just as that of Descartes, another philosopher, is with analytical geometry. Leibniz was only one amongst several continental writers whose papers in the Acta Eruditorum familiarized mathematicians with the use of differential calculus. The most important of these were James and John Bernoulli, both of whom were farm friends and admirers of Leibniz, and to their devoted advocacy his reputation is largely due. Not only did they take a prominent part in nearly every mathematical question they discussed, but nearly all the leading mathematicians on the continent for the first half of the 18th century came directly or indirectly under the influence of one or both of them. The Bernoullis were a family of Dutch origin who were driven from Holland by the Spanish persecutions and finally settled at Bâle in Switzerland. The first member of the family who attained any marked distinction in mathematics was James. James Bernoulli. Jacob or James Bernoulli was born at Bâle in December 27, 1654. In 1687 he was appointed to a chair of mathematics in the university there and occupied it until his death on August 16, 1705. He was one of the earliest to realize how powerful as an instrument of analysis was the infinitesimal calculus, and he applied it to several problems. But he did not himself invent any new processes. His great influence was uniformly and successfully exerted in favor of the use of differential calculus, and his lessons on it, which were written in the form of 2 essays in 1691 and are published in Volume 2 of his works, shew how completely he had even then grasped the principles of the new analysis. These lectures, which contain the earliest use of the term integral, were the first published attempt to construct an integral calculus, for Leibniz had treated each problem by itself, and had not laid down any general rules on the subject. The most important discoveries of James Bernoulli were his solution of the problem to find an isochronous curve. His proof that the construction for the catenary which had been given by Leibniz was correct, and his extension of this to strings of variable density under a central force, his determination of the form had taken by an elastic rod fixed at one end and acted on by a given force in the other, the elastica, also of a flexible rectangular sheet with 2 sides fixed horizontally and filled with a heavy liquid, the lentiaria, and lastly of a sail filled with wind, the velaria. In 1696 he offered a reward for the general solution of isoperimetrical figures, i.e. the determination of a figure of a given species, which should include a maximum area, its perimeter being given. His own solution, published in 1701, is correct as far as it goes. In 1698 he published an essay on the differential calculus and its applications to geometry. He here investigated the chief properties of the equiangular spiral, and especially noticed the manner in which the various curves deduced from it reproduced the original curve. Struck by this fact, he begged that, in imitation of Archimedes, an equiangular spiral should be engraved on his tombstone with the inscription Eadem numero mutata resurgo. He also brought out in 1695 an edition of Descartes' Géométrie. In his Ars Conjectandi, published in 1713, he established the fundamental principles of the calculus of probabilities. In the course of the work he defined the numbers known by his name, and explained their use, and he also gave some theorems on finite differences. His higher lectures were mostly on the theory of series. These were published by Nicholas Bernoulli in 1713. John Bernoulli. Johann Bernoulli, the brother of James Bernoulli, was born at Bâle on August 7, 1667, and died there on January 1, 1748. He occupied the chair of mathematics at Groningen from 1695 to 1705, and at Bâle, where he succeeded his brother from 1705 to 1748. To all who did not acknowledge his merits in a manner commensurate with his own view of their importance, he behaved most unjustly. As an illustration of his character, it may be mentioned that he attempted to substitute for an incorrect solution of his own on isoperimetrical curves another stolen from his brother James, while he expelled his son Daniel from his house for obtaining a prize from the French Academy which he had expected to receive himself. After the deaths of Leibniz and L'Hopital, he claimed the merit of some of their discoveries. These claims are now known to be false. He was, however, the most successful teacher of his age, and had the faculty of inspiring his pupils with almost as passionate a zeal for mathematics as he felt for himself. The general adoption on the continent of the differential rather than the fluxional notation was largely due to his influence. Leaving out of account his innumerable controversies, the chief discoveries of John Bernoulli were the exponential calculus, the treatment of trigonometry as a branch of analysis, the conditions for a geodesic, the determination of orthogonal trajectories, the solution of the brachistochrone, and the statement that a ray of light traversed such a path that sigma mu ds was a minimum, and the enunciation of the principle of virtual work. I believe that he was the first to denote the accelerating effect of gravity by an algebraical sign g, and he thus arrived at the formula v squared equals 2gh. The same result would have been previously expressed by the proportion v1 squared is to v2 squared as h1 is to h2. The notation phi x to indicate a function of x was introduced by him in 1718 and displaced the notation chi or xi proposed by him in 1698, but the general adoption of symbols like little f, big F, phi, and psi to represent functions seemed to be mainly due to Euler and Lagrange. Several members of the same family but of a younger generation enriched mathematics by their teachings and writings. The most important of these were the three sons of John, namely Nicholas, Daniel, and John the Younger, and the two sons of John the Younger who bore the names of John and James. To make the account complete, I add here their respective dates. Nicholas Bernoulli, the eldest of the three sons of John, was born on January 27, 1695, and was drowned at St. Petersburg, where he was professor, on July 26, 1726. Daniel Bernoulli, the second son of John, was born on February 9, 1700, and died on March 17, 1782. He was professor first at St. Petersburg and afterwards at Bâle, and shares with Euler the unique distinction of having gained the prize proposed annually by the French Academy no less than 10 times. I refer to him again a few pages later. John Bernoulli the Younger, a brother of Nicholas and Daniel, was born on May 18, 1710, and died in 1790. He was also a professor at Bâle. He left two sons, John and James. Of these, the former, who was born on December 4, 1744, and died on July 10, 1807, was Astronomer Royal and Director of Mathematical Studies at Berlin, while the latter, who was born on October 17, 1759, and died in July 1789, was successively professor at Bâle, Verona, and St. Petersburg. End of section 27. Recording by Paul King. Oakville, Ontario. pjk.scripts.mit.edu/pkj. Chapter 17, Part 2 of A Short Account of the History of Mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripts.mit.edu/pkj. A Short Account of the History of Mathematics by W. W. Rouse Ball. Chapter 17. Leibniz and the Mathematicians of the First Half of the 18th Century, Part 2. The Development of Analysis on the Continent. Leaving for a moment the English mathematicians of the first half of the 18th century, we come to a number of continental writers who barely escape mediocrity, and to whom it will be necessary to devote but few words.
Their writings mark the steps by which analytical geometry and the differential and integral calculus were perfected and made familiar to mathematicians. Nearly all of them were pupils of one or other of the two elder Bernoullis, and they were so nearly contemporaries that it is difficult to arrange them chronologically. The most eminent of them are Cramer, Degois, de Montmort, Fagagnon, L'Hopital, Nicole, Perrin, Ricuti, Sarin, and Vergniaud. L'Hopital. Guillaume François Antoine L'Hopital Marquis de Saint-Mesme, born at Paris in 1661 and died there on February 2nd, 1704, was among the earliest pupils of John Bernoulli, who in 1691 spent some months at L'Hopital's house in Paris for the purpose of teaching him the new calculus. It seems strange, but it is substantially true that a knowledge of the infinitesimal calculus and the power of using it was then confined to Newton, Leibniz, and the two elder Bernoullis, and it will be noticed that they were the only mathematicians who solved the more difficult problems then proposed as challenges. There was at the time no textbook on the subject, and the credit of putting together the first treatise which explained the principles and use of the method is due to L'Hopital. It was published in 1696 under the title Analyse des infiniment petites. This contains a partial investigation of the limiting value of the ratio of functions which for a certain value of the variable take the indeterminate form 0 over 0. A problem solved by John Bernoulli in 1704. This work had a wide circulation. It brought the differential notation into universal use in France and helped to make it generally known in Europe. A supplement containing a similar treatment of the integral calculus together with the additions of the differential calculus which had been made in the following half-century was published at Paris, 1754 to 1756 by L. A. de Bougainville. L'Hopital took part in most of the challenges by Leibniz, the Bernoullis, and other continental mathematicians of the time. In particular, he gave a solution of the brachistochrone, and investigated the form of the solid of least resistance of which Newton in the Principia had stated the result. He also wrote a treatise on analytical conics which was published in 1707 and for nearly a century was deemed a standard work on the subject. Vergniaud. Pierre Vergniaud, born at Caen in 1654 and died in Paris on December 22, 1722, was an intimate friend of Newton, Leibniz, and the Bernoullis, and after L'Hopital was the earliest and most powerful advocate in France of the use of the differential calculus. He realized the necessity of obtaining a test for examining the convergency of series, but the analytical difficulties were beyond his powers. He simplified the proofs of many of the leading propositions in mechanics, and in 1687 recast the treatment of the subject, basing it on the composition of forces. His works were published at Paris in 1725. For further details, see the Éloge by B. de Fontenelle, Paris, 1766. De Montmort. Pierre Raymond de Montmort, born at Paris on October 27, 1678, and died there on October 7, 1719, was interested in the subject of finite differences. He determined in 1713 the sum of n terms of a finite series of the form n choose 1 times a plus n choose 2 times delta a plus n choose 3 times delta squared a, and so on. A theorem which seems to have been independently rediscovered by Christian Goldbach in 1718. Nicole. François Nicole, who was born at Paris on December 23, 1683, and died there on January 18, 1758, was the first to publish a systematic treatise on the finite differences. Taylor had regarded the differential coefficient as the ratio of two infinitesimal differences, as the limiting value of the ratio of two finite differences, a method which is still used by many English writers, though it has been generally abandoned on the continent, and thus had been led to give a sketch of the subject in his Methodist published in 1715. Nicole's Traité du calcul des différences finies was published in 1717. It is a well-arranged book and contains rules both for forming differences and for effecting the summation of given series. Besides this, in 1706 he wrote a book on roulettes, especially spherical epicycloids, and in 1729 and 1731 he published memoirs on Newton's essay on curves of the third degree. Perrin. Antoine Perrin, born at Paris on September 16, 1666, and died there on September 26, 1716, wrote in 1700 on analytical geometry of three dimensions. His works were collected and published in 3 volumes at Paris in 1713. Sarin. Joseph Sarin, born at Cortezan in 1659 and died at Paris on December 29, 1737, was the first to shew how the tangents at the multiple points of curves could be determined by analysis. Degois. Jean-Paul Degois d'Armaves was born at Carcassonne in 1713 and died at Paris on June 2, 1785. He published in 1740 a work on analytical geometry in which he applied it, without the aid of the differential calculus, to find the tangents, asymptotes, and various singular points of an algebraical curve, and he further shewed how singular points and isolated loops were affected by conical projection. He gave the proof of Descartes' rule of signs, which is to be found in most modern works. It is not clear whether Descartes ever proved it strictly, and Newton seems to have regarded it as obvious. Kramer. Gabriel Kramer, born at Geneva in 1704 and died at Bagnols in 1752, was professor at Geneva. The work by which he is best known is his treatise on algebraical curves, published in 1750, which, as far as it goes, is fairly complete. It contains the earliest demonstration that a curve of the nth degree is in general determined if 1/2 n times n plus 3 points on it be given. This work is still sometimes read. Besides this, he edited the works of the 2 elder Bernoullis, and wrote on the physical cause of the spheroidal shapes of the planets and the motion of their apses, 1730, and on Newton's treatment of cubic curves, 1746. Riccati. Jacopo Francesco Count Riccati, born at Venice on May 28, 1676, and died at Treves on April 15, 1754, did a great deal to disseminate a knowledge of the Newtonian philosophy in Italy. Besides the equation known by his name, certain cases of which he succeeded in integrating, he discussed the question of the possibility of lowering the order of a given differential equation. His works were published at Treves in 4 volumes in 1758. He had 2 sons who wrote on several minor points connected with the integral calculus and differential equations, and applied the calculus to several mechanical questions. These were Vincenzo, who was born in 1707 and died in 1775, and Giordano, who was born in 1709 and died in 1790. Fagnano. Giulio Carlo Count Fagnano and Marquise de Tosci, born at Senegaglia on December 6, 1682, and died on September 26, 1766, may be said to have been the first writer who directed attention to the theory of elliptic functions. Failing to rectify the ellipse or hyperbola, Fagnano attempted to determine arcs whose difference should be rectifiable. He also pointed out the remarkable analogy existing between the integrals which represent the arc of a circle and the arc of a lemniscate. Finally, he proved the formula pi equals 2 times I times the log of 1 minus I
divided by 1 plus I, where I stands for the square root of -1. His works were collected and published in 2 volumes in Persero in 1750. It was inevitable that some mathematicians should object to methods of analysis founded on the infinitesimal calculus. The most prominent of these were Viviani, de la Hire, and Rolle. Chronologically they come here, but they flourished half a century after the date to which their writings properly belong. Viviani. Vincenzo Viviani, a pupil of Galileo and Torricelli, born at Florence on April 5, 1622, and died there on September 22, 1703, brought out in 1659 a restoration of the lost book of Apollonius on conic sections, and in 1701 a restoration of the work of Aristeas. He explained in 1677 how an angle could be trisected by the aid of an equilateral hyperbola or the conchoid. In 1692 he proposed the problem to construct 4 windows in a hemispherical vault so that the remainder of the surface can be accurately determined, a celebrated problem of which analytical solutions were given by Wallis Leibniz, David Gregory, and James Bernoulli. De la Hire. Philippe de la Hire, or La Hire, born in Paris on March 18, 1640, and died there on April 21, 1719, wrote on graphical methods 1673, on the conic sections 1685, a treatise on epicycloids 1694, one on roulettes 1702, and lastly another on conchoids 1708. His works on conic sections and epicycloids were founded on the teaching of Desargues, whose favourite pupil he was. He also translated the essay of Moschopoulos on magic squares, and collected many of the theorems on them which were previously known. This was published in 1705. Rolle. Michel Rolle, born at Ambert on April 21, 1652, and died in Paris on November 8, 1719, wrote an algebra in 1689 which contains the theorem on the position of roots of an equation which is known by his name. He published in 1696 a treatise on the solution of equations, whether determinate or indeterminate, and he produced several other minor works. He taught that differential calculus was nothing but a collection of ingenious fallacies. So far, no one of the school of Leibniz and the 2 elder Bernoullis had shewn any exceptional ability, but by the action of a number of second-rate writers, the methods and language of analytical geometry and the differential calculus had become well known by about 1740. The close of this school is marked by the appearance of Clairaut, D'Alembert, and Daniel Bernoulli. Their lives overlap the period considered in the next chapter, but though it is difficult to draw a sharp dividing line which shall separate by a definite date the mathematicians there considered from those whose writings are discussed in this chapter, I think that on the whole the works of these 3 writers are best treated here. Clairaut. Alexis Claude Clairaut was born at Paris on May 13, 1713, and died there on May 17, 1765. He belongs to the small group of children who, though of exceptional precocity, survive and maintain their powers when grown up. As early as the age of 12 he wrote a memoir on 4 geometrical curves, but his first important work was a treatise on tortuous curves, published when he was 18, a work which first procured for him immediate admission to the French Academy. In 1731 he gave a demonstration of the fact noted by Newton that all curves of the 3rd order were projections of one of 5 parabolas. In 1741 Clairaut went on a scientific expedition to measure the length of a meridian degree on the earth's surface, and on his return in 1743 he published his Théorie de la figure de la Terre. This is founded on a paper by Maclaurin, where it has been shewn that a mass of homogeneous fluid set in rotation about a line through its centre of mass would, under the mutual attraction of its particles, take the form of a spheroid.
This work of Clairaut treated of heterogeneous spheroids and contains the proof of his formula for the accelerating effect of gravity in a place of latitude L, namely G equals big G multiplied by 1 plus 5 halves m minus epsilon multiplied by sine squared L, where G is the value of equatorial gravity, m the ratio of the centrifugal force to gravity at the equator, and epsilon the epicity of a meridian section of the Earth. In 1849, Professor Stokes showed that the same result was true whatever was the interior construction or density of the Earth, provided the surface was a spheroid of equilibrium of small ellipticity. Impressed by the power of geometry as shewn in the writing of Newton and Maclaurin, Clairaut abandoned analysis, and his next work, the Théorie de la Lune, published in 1752, is strictly Newtonian in character. This contains the explanation of the motion of the apse which had previously puzzled astronomers, and which Clairaut had at first deemed so inexplicable that he was on the point of publishing a new hypothesis as to the law of attraction when it occurred to him to carry the approximation to the third order, and he thereupon found that the result was in accordance with observations. This was followed in 1754 by some lunar tables. Clairaut subsequently wrote various papers on the orbit of the moon, and on the motion of the comets as affected by the perturbation of the planets, particularly on the path of Halley's comet. His growing popularity in society hindered his scientific work. Engagé, says Bossuet, à des soupers à dévier entraîné par un goût vif pour les femmes, voulant aller plaisir à ses travaux ordinaires, et perdre pour la santé enfin via l'âge de 52 ans. D'Alembert. Jean de Rond d'Alembert was born at Paris on November 16, 1717, and died there on October 29, 1713. He was the illegitimate child of the Chevalier d'Estouches. Being abandoned by his mother on the steps of the little church of Saint-Jean-le-Rond, which then nestled under the great porch of Notre-Dame, he was taken to the parish commissary, who, following the usual practice in such cases, gave him the Christian name of Jean Laurent. I do not know by what title he subsequently assumed the right to prefix de to his name. He was boarded out by the parish, with the wife of a glazier in a small way of business, who lived near the cathedral, and here he seems to have found a real home, though a very humble one. His father appears to have looked after him and paid for his going to a school where he obtained a fair mathematical education. An essay written in 1738 on the integral calculus, and another in 1740 on ducks and drakes, or ricochets, attracted some attention, and in the same year he was elected a member of the French Academy. This was probably due to the influence of his father. It is to his credit that he absolutely refused to leave his adopted mother, with whom he continued to live until her death in 1757. It cannot be said that she sympathized with his success, for, at the height of his fame, she remonstrated with him for wasting his talents on such work. Vous ne serez aimé qu'un philosophe, said she. Et qu'est-ce qu'un philosophe? C'est un fou qui se tourmente pendant sa vie, pour qu'on parle de lui lorsqu'il ne sera plus. Nearly all his mathematical works were produced within the years 1743 to 1754. The first of these was his Traité de dynamique, published in 1743, in which he enunciates the principle known by his name, namely that the internal forces of inertia, i.e. the forces which resist acceleration, must be equal and opposite to the forces which produce the acceleration. This is a particular case of Newton's second reading of his third law of motion, but the full consequence of it had not been realized previously. The application of this principle enables us to obtain the differential equations of motion of any rigid system.
In 1744, D'Alembert published his Traité de l'équilibre et du mouvement des fluides, in which he applies his principle to fluids. This led to partial differential equations which he was then unable to solve. In 1745 he developed that part of the subject which dealt with the motion of air in his Théorie générale des vents, and this again led him to partial differential equations. A second edition of this in 1746 was dedicated to Frederick the Great of Prussia, and procured an invitation to Berlin and the offer of a pension. He declined the former, but subsequently, after some pressing, pocketed his pride and the latter. In 1747 he applied the differential calculus to the problem of a vibrating string, and again arrived at a partial differential equation. His analysis had 3 times brought him to an equation of the form the second derivative of u with respect to t equals the second derivative of u with respect to x, and he now succeeded in shewing that it was satisfied by u equals phi of x plus t plus psi of x minus t, where phi and psi are arbitrary functions. It may be interesting to give his solution, which was published in the Transactions of the Berlin Academy for 1747. He begins by saying that if the partial derivative of u with respect to x be denoted by p and the partial derivative of u with respect to t by q, then du equals p dx plus q dt. But by the given equation, the partial derivative of q with respect to t equals the partial derivative of p with respect to x, and therefore p dt plus q dx is also an exact differential, denoted by dv. Therefore, dv equals p dt plus q dx. Hence, du plus dv equals p dx plus q dt plus p dt plus q dx equals p plus q multiplied by dx plus dt. And du minus dv equals p dx plus q dt minus the quantity p dt plus q dx equals the quantity p minus q multiplied by the quantity dx minus dt. Thus u plus v must be a function of x plus t, and u minus v must be a function of x minus t. We may therefore put u plus v equals 2 times phi of x plus t, and u minus v equals 2 psi of x minus t. Hence, u equals phi of x plus t plus psi of x minus t. D'Alembert added that the conditions of the physical problem of a vibrating string demand that when x equals 0, u should vanish for all values of t. Hence, identically, phi of t plus psi of negative t equals 0. Assuming that both functions can be expanded in integral powers of t, this requires that they should contain only odd powers. Hence, psi of negative t equals negative phi of t equals phi of negative t. Therefore, u equals phi of x plus t plus phi of x minus t. Euler now took the matter up and shewed that the equation of the form of the string was the second derivative of u with respect to t equals a squared multiplied by the second derivative of u with respect to x, and that the general integral was u equals phi of x minus at plus psi of x plus at, where phi and psi are arbitrary functions. The chief remaining contributions of D'Alembert to mathematics were on physical astronomy, especially on the precession of the equinoxes and on variations of the obliquity of the ecliptic. These were collected on his Système des Mondes, published in 3 volumes in 1754. During the latter part of his life, he was mainly occupied with the great French encyclopedia. For this he wrote the introduction, and numerous philosophical and mathematical articles. The best are those on geometry and on probabilities. His style is brilliant but not polished, and faithfully reflects his character, which was bold, honest, and frank. He defended a severe criticism which he had offered on some mediocre work by the remark, Je m'eussais in civil qu'ennuyé,
and with his dislike of sycophants and bores, it is not surprising that during his life he had more enemies than friends. End of section 28. Recording by Paul King, Oakville, Ontario. pjk.scripps.mit.edu/pkj.
Chapter 17, Part 3 of A Short Account of the History of Mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This reading is by Paul King, pjk.scripps.mit.edu/pkj. A Short Account of the History of Mathematics by W. W. Rouse Ball. Chapter 18, Leibniz and the Mathematicians of the First Half of the 18th Century. Daniel Bernoulli. Daniel Bernoulli, whose name I mentioned above, and who was by far the ablest of the younger Bernoullis, was a contemporary and intimate friend of Euler, whose works are mentioned in the next chapter. Daniel Bernoulli was born on February 9, 1700, and died at Bâle, where he was professor of natural philosophy, on March 17, 1782. He went to St. Petersburg in 1724 as professor of mathematics, but the roughness of the social life was distasteful to him, and he was not sorry when a temporary illness in 1733 allowed him to plead his health as an excuse for leaving. He then returned to Bâle, where he held successively chairs of medicine, metaphysics, and natural philosophy there. His earliest mathematical work was on the Excursiones, published in 1724. These contain a theory of the oscillations of rigid bodies, and a solution to the differential equations proposed by Riccati. 2 years later, he pointed out for the first time the frequent desirability of resolving a compound motion into motions of translation and motions of rotation. His chief work is his Hydrodynamique, published in 1738. It resembles Lagrange's Mécanique analytique in being arranged so that all the results are consequences of a single principle, namely, in this case, the conservation of energy. This was followed by a memoir on the theory of the tides, to which, conjointly with memoirs by Euler and Maclaurin, a prize was awarded by the French Academy. These 3 memoirs contain all that was done on the subject between publication of Newton's Principia and the investigations of Laplace. Bernoulli also wrote a large number of papers on various mechanical questions, especially on problems connected with vibrating strings, and the solutions given by Taylor and D'Alembert. He is the earliest writer who attempted to formulate a kinetic theory of gases, and he applied the idea to explain the law associated with the names of Boyle and Mariotte. The English mathematicians of the 18th century. I have reserved a notice of the English mathematicians who succeeded Newton in order that the members of the English school may all be treated together. It was almost a matter of course that the English should at least at first have adopted the notation of Newton in the infinitesimal calculus in preference to that of Leibniz, and the English school would consequently in any case have developed on somewhat different lines to that of the continent, where a knowledge of the infinitesimal calculus was derived solely from Leibniz and the Bernoullis. But this separation into 2 distinct schools became very marked owing to the action of Leibniz and John Bernoulli, which was naturally resented by Newton's friends, and so for 40 or 50 years, to the mutual disadvantage of both sides, the quarrel raged. The leading members of the English school were Cotes, Demoivre, Ditton, David Gregory, Halley, Maclaurin, Simpson, and Taylor. I may, however, again remind my readers that as we approach the modern times, the number of capable mathematicians in Britain, France, Germany, and Italy becomes very considerable, but that in a popular sketch like this book, it is only the leading men who I propose to mention. To David Gregory, Halley, and Ditton I need to devote but a few words. David Gregory. David Gregory, the nephew of James Gregory mentioned above in page 315, born at Aberdeen on June 24, 1661 and died at Maidenhead on October 10, 1708, was appointed professor at Edinburgh in 1684 and in 1691 was, on Newton's recommendation, elected Savilian professor at Oxford. His chief works are one on geometry, issued in 1684, one on optics, published in 1695, which contains the earliest suggestion of the possibility of making an achromatic combinations of lenses, and one on the Newtonian geometry, physics, and astronomy, issued in 1702. Halley. Edmund Halley, born in London in 1656 and died at Greenwich in 1742, was educated at St. Paul's School, London, and Queen's College, Oxford in 1703, succeeded Wallace as Savilian professor, and subsequently in 1720 was appointed Astronomer Royal in succession to Flamsteed, whose Historia Celestis Britannica he edited in 1712, first and imperfect edition. Halley's name will be recollected for the generous manner in which he secured the immediate publication of Newton's Principia in 1687. Most of his original work was on astronomy and allied subjects and lies outside the limits of this book. It may be, however, said that the work is of excellent quality, and both Lalande and Meran speak of it in the highest terms. Halley conjecturally restored the eighth and lost book of the Conics of Apollonius, and in 1710 brought out a magnificent edition of the whole work. He also edited the works of Serenus and those of Menelaus, and some of the minor works of Apollonius. He was in his turn succeeded at Greenwich as an Astronomer Royal by Bradley. Diton. Humphrey Diton, born at Salisbury on May 29, 1675, and died in London in 1715 at Christ's Hospital, where he was mathematical master. He does not seem to have paid much attention to mathematics until he came to London about 1705, and his early death was a distinct loss to English science. He published in 1706 a textbook on fluxions. This and another similar work by William Jones, which was issued in 1711, occupied in England much the same place as L'Hôpitel's treatise did in France. In 1709 Diton issued an algebra, and in 1712 a treatise on perspective. He also wrote numerous papers on the philosophical transactions. He was the earliest writer to attempt to explain the phenomenon of capillary on mathematical principles, and he invented a method of finding the longitude which has been since used on various occasions. Taylor. Brooke Taylor, born at Edmonton on August 18, 1685, and died in London on December 29, 1731, was educated at St. John's College, Cambridge, and was among the most enthusiastic of Newton's admirers. From the year 1712 onwards, he wrote numerous papers on philosophical transactions, in which, among other things, he discussed the motion of projectiles, the centre of oscillation, and the forms of liquids raised by capillarity. In 1719 he resigned the secretaryship of the Royal Society and abandoned the study of mathematics. His earliest work, that by which he is generally known, is his Methodus Incrementorum Directa et Inversa, published in London in 1715. This contains a proof of the well-known theorem f of x plus h equals f of x plus h f prime of x plus h squared over 2 factorial multiplied by f double prime of x plus and so on, by which any function of a single variable can be expanded in powers of it. He does not consider the convergency of the series, and the proof, which involves numerous assumptions, is not worth reproducing. The work also includes several theorems on interpolation. Taylor was the earliest writer to deal with theorems on the change of the independent variable. He was perhaps the first to realize the possibility of a calculus of operation, and just as he denotes the nth differential coefficient of y by y sub n, so he uses y sub -1 to represent the integral of y. Lastly, he is usually recognized as the creator of the theory of finite differences. The applications of the calculus to various questions given in the Methodists have hardly received that attention they deserve. The most important of them is the theory of the transverse vibration of strings, a problem which had baffled previous investigators. In this investigation, Taylor shews that the number of half vibrations executed in a second is pi multiplied by the square root of the quantity dp divided by ln, where L is the length of the string, n is its weight, p is the weight which stretches it, and d is the length of a second's pendulum. This is correct, but in arriving at it he assumes that every point on the string will pass through its position of equilibrium at the same instant, a restriction which Delabert subsequently shewed to be unnecessary. Taylor also found the form which the string assumes at any instant. This work also contains the earliest determination of the differential equation of the path of a ray of light when traversing a heterogeneous medium, and assuming that the density of the air depends only on its distance from the Earth's surface, Taylor obtained by means of quadratures the approximate form of the curve. The form of the catenary and the determination of the centers of oscillation and percussion are also discussed. A treatise on perspective, published in 1719, contains the earliest general enunciation of the principle of vanishing points. Though the idea of vanishing points for horizontal and parallel lines in a picture hung in a vertical plane had been enunciated by Guido Ubaldi in his Perspective Libri, Pisa, 1600. Coates. Roger Coates was born near Leicester on July 10, 1682, and died at Cambridge on June 5, 1716. He was educated at Trinity College, Cambridge, of which society he was a fellow, and in 1706 was elected to the newly created Plumian Chair of Astronomy in the University of Cambridge. From 1709 to 1713 his time was mainly occupied in editing the second edition of the Principia. The remark of Newton that if only Coates had lived we should have learnt something indicates the opinion of his abilities held by most of his contemporaries. Coates's writings were collected and published in 1722 under the titles Harmonia Mensurarum and Opera Miscellanea. His lectures on hydrostatics were published in 1738. A large part of the Harmonia Mensuratum was given up to the decomposition and integration of rational algebraical expressions. That part which deals with the theory of partial fractions was left unfinished, but was completed by Demoivre. Coates's theorem in trigonometry, which depends on forming the quadratic factors of x to the power n minus 1, is well known. The proposition that if from a fixed point O a line be drawn cutting a curve in q1, q2, and so on to qn, and a point P be taken on the line so that the reciprocal of OP is the arithmetic mean of the reciprocals of OQ1, OQ2, OQ3, and so on all the way to OQn, then the locus of P will be a straight line, is also due to Coates. The title of the book was derived from the latter theorem. The Opera Miscellanea contains a paper on the method for determining the most probable result from a number of observations. This was the earliest attempt to frame a theory of errors. It also contains essays on Newton's Methodus Differentialis, the construction of tables by the method of differences, on the descent of a body under gravity, on the cycloidal pendulum, and on projectiles. Demoivre. Abraham Demoivre, more correctly written Demoivre in 2 words, was born at Vitry in May 26, 1667, and died in London on November 27, 1754. His parents came to England when he was a boy, and his education and friends were alike English. His interest in the higher mathematics is said to have originated in his coming by chance across a copy of Newton's Principia. From the eloge on him delivered in 1754 before the French Academy, it would seem that as a young fellow his work as a teacher of mathematics had led him to the house of the Earl of Devonshire at the instant when Newton, who had asked permission to present a copy of his work to the Earl, was coming up. Taking up the book, and charmed by the far-reaching conclusions and the apparent simplicity of the reasoning, De Moivre thought nothing would be easier than to master the subject, but to his surprise found that to follow the argument overtaxed his powers. He however bought a copy, and as he had but little leisure, he tore out the pages in order to carry one or two of them loose in his pocket, so that he could study them in the intervals of his work as a teacher. Subsequently he joined the Royal Society, and he became intimately connected with Newton, Halley, and other mathematicians of the English school. The manner of his death has a curious interest for psychologists. Shortly before it, he declared that it was necessary for him to sleep some 10 minutes or a quarter of an hour longer each day than the preceding one. The day after he had thus reached a total of something over 23 hours, he slept up to the limit of 24 hours and then died in his sleep. He is best known for having, together with Lambert, created that part of trigonometry which deals with imaginary quantities. Two theorems on this part of the subject are still connected with his name, namely that which asserts that sin nx plus I cos nx is one of the values of the quantity sin x plus I cos x all to the power n, and that which gives the various quadratic factors of x to the power 2n minus 2 times px to the power n plus 1. His chief works, other than numerous papers in the Philosophical Transactions, were the Doctrine of Chances, published in 1718, and the Miscellanea Analytica, published in 1730. In the former, the theory of recurring series was first given, and the theory of partial fractions, which Coates's premature death had left unfinished, was completed, while the rule for finding the probability of a compound event was enunciated. The latter, besides the trigonometrical propositions mentioned above, contains some theorems in astronomy, but they are treated as problems in analysis. Maclaurin. Colin Maclaurin, who was born in Kilmodden in Argyllshire in February 1698 and died at York on June 14, 1746, was educated at the University of Glasgow. In 1717 he was elected, at the early age of 19, professor of mathematics at Aberdeen, and in 1725 he was appointed the deputy of the mathematical professor at Edinburgh, and ultimately succeeded him. There was some difficulty in securing a stipend for a deputy, and Newton privately wrote offering to bear the cost so as to enable the university to secure the services of Maclaurin. Maclaurin took an active part in opposing the advance of the young pretender in 1745. On the approach of the Highlanders he fled to York, but the exposure in the trenches at Edinburgh and the privations he endured in his escape proved fatal to him. His chief works are Geometria Organica, London 1719, his treatise on fluxions, Edinburgh 1742, his Algebra, London 1748, and his account of Newton's discoveries, London 1748. The Geometria Organica is on the extension of a theorem given by Newton. Newton had shewn that if two angles bounded by straight lines turn round their respective summits so that the point of intersection of two of these lines moves along a straight line, the other point of intersection will describe a conic, and if the first point move along a conic, the second will describe a quartic. Maclaurin gave an analytical discussion on the general theorem, and shewed by how this method various curves could be practically traced. This work contains an elaborate discussion on curves and their pedals, a branch of geometry which he had created in two papers published in the Philosophical Transactions for 1718 and 1719. In the following year, 1720, Maclaurin issued a supplement which is practically the same as his De Linearum Geometricarum Proprietatibus. It is divided into three sections and an appendix. The first section contains a proof of Cotes' theorem as alluded to, and also the analogous theorem discovered by himself that if a straight line OP1P2 is drawn through a fixed point O, cut a curve of the nth degree in n points P1, P2, and so on, and if the tangents at P1, P2 cut in a fixed line OX in points A1, A2, and so on, then the sum of the reciprocals of the distances OA1, OA2, and so forth is constant for all positions of the line OP1, P2, and so on. These two theorems are generalizations of those given by Newton on diameters and asymptotes. Either is deducible from the other. In the second section, these theorems are applied to conics. Most of these harmonic properties connected with an inscribed quadrilateral are determined, and in particular the theorem on an inscribed hexagon, which is known by the name of Pascal, is deduced. Pascal's essay was not published until 1779, and the earliest printed enunciation of his theorem was that given by Maclaurin. In the third section, these theorems are applied to cubic curves. Amongst other propositions, he shews that if a quadrilateral be inscribed in a cubic, and if the points of intersection of the opposite sides also lie on the curve, then the tangents to the cubic at any two opposite angles of the quadrilateral will meet on the curve. The appendix contains some general theorems. One of these, which includes Pascal's as a particular case, is that if a polygon be deformed so that while each of its sides passes through a fixed point, its angles save one describe respectively curves of the mth, nth, pth, and so forth degrees, then shall the remaining angle describe a curve of the degree 2 mnp. But if the given points be collinear, the resulting curve will be only of the degree mnp. This essay was reprinted with additions on the Philosophical Transactions for 1735. The Treatise of Fluxions, published in 1742, was the first logical and systematic exposition of the method of fluxions. The cause of its publication was an attack by Berkeley on the principles of the infinitesimal calculus. In it, Article 751, page 610, Maclaurin gave a proof of the theorem that f of x equals f of 0 plus xf prime of 0 plus x squared over 2 factorial f double prime of 0 plus so on and so forth. This was obtained in the manner given in many modern textbooks by assuming that f of x can be expanded in a form like f of x equals a0 plus a1x plus a2x squared plus and so on and so on. Then on differentiating and putting x equals 0 in the successive results, the values of a0, a1, and so on are obtained. But he did not investigate the convergency of the series. The result had been previously given in 1730 by James Stirling in his Methodes Differentiales, and of course is at once deducible from Taylor's theorem, on which the proofs by Stirling and Maclaurin are admittedly founded. Maclaurin also here enunciated, Article 350, page 289, the important theorem that if phi x be positive and decrease as x increases from x equals a to x equals infinity, then the series phi of a plus 1 plus phi of a plus 2 and so on is convergent or divergent, as the integral going from a to infinity of phi of x dx is finite or infinite. He also gives the correct theory of maxima and minima, and rules for finding and discriminating multiple points. This treatise is, however, especially valuable for the solutions it contains of numerous problems in geometry, statics, the theory of attractions, and astronomy. To solve these, he reverted to classical methods, and so powerful did these processes seem, when used by him, that Clairaut, after reading the work, abandoned analysis, and attacked the problem of the figure of the earth again by pure geometry. At a later time this part of the book was described by Lagrange as the chef d'œuvre de géométrie qu'on peut comparer à tout ce qu'Archimède nous a laissé de plus beau et de plus ingénieux. Maclaurin also determined the attraction of a homogeneous ellipsoid at an internal point, and gave some theorems on its attraction at an external point. In effecting this, he introduced the conception of level surfaces, i.e. surfaces at every point of which the resultant attraction is perpendicular to the surface. No further advances in the theory of attractions was made until Lagrange in 1773 introduced the idea of the potential, see below. Maclaurin also shewed that a spheroid was a possible form of equilibrium of a mass of homogeneous liquid rotating about an axis passing through its centre of mass. Finally, he discussed the tides. This part had been previously published in 1740 and had received a prize from the French Academy. Among Maclaurin's minor works is his Algebra, published in 1748 and founded on Newton's universal arithmetic. It contains the results of some early papers of Maclaurin, notably of two, written in 1726 and 1729, on the number of imaginary roots of an equation, suggested by Newton's theorem, see above, and of one written in 1729 containing the well-known rule for finding equal roots by means of the derived equation. To this a treatise entitled De Linearum Geometricarum Propertatibus Generalibus was added as an appendix. Besides the paper of 1720 above alluded to, it contains some additional and elegant theorems. Maclaurin also produced in 1728 an exposition of the Newtonian philosophy, in which is incorporated in the posthumous work printed in 1748. Almost the last paper he wrote was one printed in the Philosophical Transactions in 1743, in which he discussed from a mathematical point of view the form of a bee's cell. Maclaurin was succeeded in his chair at Edinburgh by pupil Matthew Stewart, born at Rothesay in 1717 and died in Edinburgh on January 23, 1785, a mathematician of considerable power, to whom I allude in passing for his theorems on the problem of three bodies and for his discussion treated by transversals and involution of the properties of the circle and straight line. Maclaurin was one of the most able mathematicians of the 18th century, but his influence on the progress of British mathematics was on the whole unfortunate. By himself abandoning the use of both analysis and of the infinitesimal calculus, he induced Newton's countrymen to confine themselves to Newton's methods, and I remarked before it was not until about 1820, when the differential calculus was introduced into the Cambridge curriculum, that English mathematicians made any general use of the more powerful methods of modern analysis. Simpson. The last member of the English school whom I need mention here is Thomas Simpson, who was born in Leicestershire on August 20th, 1710, and died on May 14th, 1761. His father was a weaver, and he owed his education to his own efforts. His mathematical interests were first aroused by the solar eclipse which took place in 1724, and with the aid of a fortune-telling peddler he mastered the Cocker's arithmetic and the elements of algebra. He then gave up his weaving and became an usher at a school, and by constant and laborious efforts improved his mathematical education, so that by 1735 he was able to solve several questions involving the infinitesimal calculus, which had been recently proposed. He next moved to London, and in 1743 was appointed professor of mathematics at Woolwich, a post which he continued to occupy till his death. The works published by Simpson prove him to have been a man of extraordinary natural genius and extreme industry. The most important of them are his Fluxions, 1737 and 1750, with numerous applications to physics and astronomy; his Laws of Chance and his Essays, 1740, and his Theory of Annuities and Reversions, a branch of mathematics that is due to James Dodson, 1597 to 1657, who was a master at Christ's Hospital, London; with Tables of the Value of Lives, 1742, his Dissertations, 1743, in which the figure of the earth, the force of attraction at the surface of a nearly spherical body, the theory of the tides, and the law of astronomical refraction are discussed; his Algebra, 1745, his Geometry, 1747, his Trigonometry, 1748, in which he introduced the current abbreviations for the trigonometrical functions; his Select Exercises, 1752, containing the solutions of numerous problems and a theory of gunnery; and lastly his Miscellaneous Tracts, 1754. The last consists of 8 memoirs, and these contain his best known investigations. The first 3 papers are on various problems in astronomy; the fourth is on the theory of mean observations; the fifth and sixth on problems in fluxions and algebra; the seventh contain a general solution of the isoperimetrical problem; the eighth contains a discussion of the third and ninth sections of the Principia and their application to the lunar orbit. In this last memoir Simpson attained a differential equation for the motion of the apse of the lunar orbit similar to that arrived at by Clairaut, but instead of solving it by successive approximations he deduced a general solution by indeterminate coefficients. The result agrees with that given by Clairaut. Simpson first solved this problem in 1747, 2 years later than the publication of Clairaut's memoir, but the solution was discovered independently of Clairaut's researches, of which Simpson first heard in 1748. End of section 29. Recording by Paul King, Oakville, Ontario. pjk.scripps.mit.edu/pkj. Chapter 18, Part 1 of A Short Account of the History of Mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This reading is by Paul King, pjk.scripps.mit.edu/pkj. A Short Account of the History of Mathematics by W. W. Rouse. Chapter 18. Lagrange, Laplace, and their contemporaries, circa 1740 to 1830. The last chapter contains the history of 2 separate schools, the continental and the British. In the early years of the 18th century the English school appeared vigorous and fruitful, but decadence rapidly set in, and after the deaths of Maclaurin and Simpson no British mathematician appeared who is at all comparable to the continental mathematicians of the latter half of the 18th century. This fact is partly explicable by the isolation of the school, partly by its tendency to rely too exclusively on geometrical and fluxional methods. Some attention was however given to practical science, but except for a few remarks on English physicists I do not think it necessary to discuss English mathematicians further until about 1820, when analytical methods again come into vogue. On the continent, under the influence of John Bernoulli, the calculus had become an instrument of great analytical power expressed in an admirable notation, and for practical applications it is impossible to overestimate the value of a good notation. The subject of mechanics remained however in much the condition in which Newton had left it, until D'Alembert, in putting Newton's results into the language of the differential calculus, did something to extend it. Universal gravitation, as enunciated in the Principia, was accepted as an established fact, but the geometrical methods adopted in proving it were difficult to follow or to use in analogous problems. Maclaurin, Simpson, and Clairaut may be regarded as the last mathematicians of distinction who employed them. Lastly, the Newtonian theory of light was generally received as correct. The leading mathematicians of the era of which we are now entering are Euler, Lagrange, Laplace, and Legendre. Briefly, we may say that Euler extended, summed up, and completed the work of his predecessors, while Lagrange, with almost unrivalled skill, developed the infinitesimal calculus and theoretical mechanics into the form in which we now know them. At the same time, Laplace made some additions to the infinitesimal calculus and applied that calculus to the theory of universal gravitation. He also created a calculus of probabilities. Legendre invented spherical harmonic analysis and elliptic integrals and added to the theory of numbers. The works of these writers are still standard authorities and are hardly yet the subject matter of history. I shall therefore content myself with a mere sketch of their discoveries, referring anyone who wishes to know more to the works themselves. Lagrange, Laplace, and Legendre created a French school of mathematics, of which the younger members are divided into two groups, including Poisson and Fourier, began to apply the mathematical analysis to physics, and the other, including Monge, Carnot, and Poncelet, created modern geometry. Strictly speaking, some of the great mathematicians of recent times, such as Gauss and Abel, were contemporaries of the mathematicians last named, but except for this remark, I think it convenient to defer any consideration of them to the next chapter. The development of analysis and mathematics. Euler. Leonhard Euler was born in Bâle on April 15th, 1707 and died at St. Petersburg on September 7th, 1783. He was a son of a Lutheran minister who had settled at Bâle and was educated in his native town under the direction of John Bernoulli, with whose sons Daniel and Nicholas he formed a lifelong friendship. When in 1725 the younger Bernoullis went to Russia on the invitation of the Empress, they procured a place there for Euler, which in 1733 he exchanged for the chair of mathematics then vacated by Daniel Bernoulli. The severity of the climate affected his eyesight, and in 1735 he lost the use of one eye completely. In 1741 he moved to Berlin at the request, or rather command, of Frederick the Great. Here he stayed till 1766, when he returned to Russia, and was succeeded at Berlin by Lagrange. Within 2 or 3 years of his going back to St. Petersburg he became blind, but in spite of this, and although his house together with many of his papers were burnt in 1771, he recast and improved most of his earlier works. He died of apoplexy in 1783. He was married twice. I think we may sum up Euler's work by saying that he created analysis and revised almost all the branches of pure mathematics which were then known, filling up the details, adding proofs, and arranging the whole in consistent form. Such work is very important, and it is fortunate for science when it falls into the hands as competent as those of Euler. Euler wrote an immense number of memoirs on all kinds of mathematical subjects. His chief work, in which many of the results of earlier memoirs are embodied, are as follows. In the first place, he wrote in 1748 in his Introductio in Analysum Infinitorum, which was intended to serve as an introduction to pure analytical mechanics. This is divided into 2 parts. The first part of the Analysis Infinitorum contains the bulk of the matter which is to be found in the modern textbooks on algebra, theory of equations, and trigonometry. In the algebra, he paid particular attention to the expansion of various functions in series, and to the summation of given series, and pointed out explicitly that an infinite series cannot be safely employed unless it is convergent. In the trigonometry, much of which is founded on F. C. Mayer's Arithmetic of Sines, which has been published in 1727, Euler developed the idea of John Bernoulli that the subject was a branch of analysis and not a mere appendage of astronomy or geometry. He also introduced, contemporaneously with Simpson, the current abbreviations for the trigonometrical functions, and shewed that the trigonometrical and exponential functions were connected by the relation cosine theta plus I sine theta equals e to the power of I times theta. Here too we meet the symbol e, used to denote the base of the Napierian logarithms, namely the incommensurable number 2.71828, and the symbol pi, used to denote the incommensurable number 3.14159. The use of a single symbol to denote the number 2.71828 seems to be due to Cotes, who denoted it by m. Newton was, as far as I know, the first to employ the literal exponential notation, and Euler, using the form a to the z, has taken a as the base of any system of logarithms. It is probable that the choice of e for a particular base was determined by its being the vowel consecutive to a. The use of a single symbol to denote the number 3.14159 appears to have been introduced by John Bernoulli, who represented it by c. Euler in 1734 denoted it by p, and in a letter of 1736 in which he enunciated the theorem that the sum of the squares of the reciprocals of the natural numbers is 1 over 6 times pi squared, he used the letter c. Christian Goldbach in 1742 used the Greek letter pi, and after the publication of Euler's analysis the symbol pi was generally employed. The numbers e and pi would enter into the mathematical analysis from whatever side the subject was approached. The latter represents, among other things, the ratio of the circumference of a circle to the diameter, but it is a mere accident that it is taken for its definition. De Morgan, in the Budget of Paradoxes, tells an anecdote which illustrates how little the usual definition suggests its real use. He was explaining to an actuary what was the chance that at the end of a given time a certain proportion of some group of people would be alive, and quoted the actuarial formula involving pi, which in answer to a question he explained stood for the ratio of the circumference of a circle to its diameter. His acquaintance, who so far listened to the explanation with interest, interrupted him and explained, "My dear friend, that must be a delusion. What can a circle have to do with the number of people alive at the end of a given time?" The second part of the Analysis Infinitorum is on analytical geometry. Euler commenced this part by dividing curves into algebraical and transcendental, and established a variety of propositions which are true for all algebraical curves. He then applied these to the general equations of the second degree in 2 dimensions, shewed that it represents the various conic sections, and deduced most of their properties from the general equation. He also considered the classification of cubic, quartic, and other algebraical curves. He next discussed the question as to what surfaces are represented by the general equation of the second degree in 3 dimensions, and how they may be discriminated one from the other. Some of these surfaces had not been previously investigated. In the course of this analysis he laid down the rules for the transformation of coordinates in space. Here also we find the earliest attempt to bring the curvature of surfaces within the domain of mathematics, and the first complete discussion of tortuous curves. The Analysis Infinitorum was followed in 1755 by the Institutiones Calculi Differentialis, to which it was intended as an introduction. This was the first textbook on the differential calculus which has any claim to be regarded as complete, and it may be said that most modern treatises on the subject are based on it. At the same time it should be added that the exposition of the principles of the subject is often prolix and obscure, and sometimes not altogether accurate. This series of works was completed by the publication in 3 volumes, in 1768 to 1770, of the Institutiones Calculi Integralis, in which the results of several of Euler's earlier memoirs on the same subject and on differential equations are included. This, like the similar treatise on the differential calculus, summed up what was then known on the subject, but many of the theorems were recast and the proofs improved. The beta and gamma functions were invented by Euler and discussed here, but only as illustrations of the methods of reduction and integration. His treatment of elliptical integrals is superficial. It was due to a theorem given by John Landon, a writer who was suggestive rather than powerful, in the Philosophical Transactions for 1755, connecting the arcs of a hyperbola and an ellipse. Euler's works that form this trilogy have gone through numerous subsequent editions. The classic problems on isoperimetrical curves, the brachistochrone in a resulting medium, and the theory of geodesics, all of which had been suggested by his master John Bernoulli, had engaged Euler's attention at an early date, and in solving them he was led to the calculus of variations. The general idea of this was laid down in his Curvarum Maximae Minive Proprietate Gaudentium Inventio Nova ac Facilis, published in 1744, but the complete development of the new calculus was first effected by Lagrange in 1759. The method used by Lagrange is described in Euler's integral calculus and is the same as that given in most modern textbooks on the subject. In 1770 Euler published the Analyse zur Algebra in 2 volumes. The first volume treats of determinate algebra. This contains one of the earliest attempts to place the fundamental process on a scientific basis. The same subject had attracted D'Alembert's attention. This work also includes the proof of the binomial theorem for an unrestricted index, which is still known by Euler's name. The proof is founded on the principle of the permanence of equivalent forms, but Euler made no attempt to investigate the convergency of the series. That he should have omitted this essential step is the more curious, as he had himself recognized the necessity of considering the convergency of the infinite series. The second volume treats of the indeterminate or Diophantine algebra. This contains a solution of some of the problems proposed by Fermat, which had hitherto remained unsolved. A French translation of the algebra, with numerous and valuable additions by Lagrange, was brought out in 1794, and a treatise on arithmetic by Euler was appended to it. These 4 works comprise most of what Euler produced in pure mathematics. He also wrote numerous memoirs on nearly all subjects of applied mathematics and mathematical physics then studied. The chief results in them are as follows. In the mechanics of a grid system he determined the general equation of a motion of a body about a fixed point, which are ordinarily written of the form a multiplied by d omega 1 by dt minus in brackets b minus c close bracket times omega 2 times omega 3 equals L. And he gave the general equation of the motion of a free body, which are usually presented in the form d by dt times mu minus mv theta 3 plus mw theta 2 equals x, and dh1 prime by dt equals h2 prime theta 3 plus h3 prime theta 2 equals L. He also defended and elaborated the theory of least action, which had been propounded by Maupertuis in 1751 in his Essai de cosmologie. In hydrodynamics, Euler established the general equations of motion, which are commonly expressed in the form 1 over rho d rho by dx equals x minus du by dt minus u times du by dx minus v times du by dy minus w times du by dz. At the time of his death he was engaged in writing a treatise on hydromechanics in which the treatment of the subject would have been completely recast. His most important works on astronomy are his Theoria Mortuum Planetarum et Cometarum, published in 1744, his Theoria Motus Lunaris, published in 1753, and his Theoria Motuum Lunae, published in 1772. In these he attacked the problem of three bodies. He supposed the body considered, e.g. the moon, to carry three rectangular axes with it in its motion, the axes moving parallel to themselves, and to these axes all the motions were referred. This method is not convenient, but it was from Euler's results that Mayer constructed the lunar tables, from which his widow in 1770 received £5,000, being the prize offered by the English Parliament, and in recognition of Euler's services a sum of £300 was voted as an honorarium to him. Euler was much interested in optics. In 1746 he discussed the relative merits of the emission and undulatory theories of light. He, on the whole, preferred the latter. In 1770 to 1771 he published his optical researches in 3 volumes under the title Dioptrica. He also wrote an elementary work on physics and fundamental principles of mathematical philosophy. This originated from an invitation he received when he first went to Berlin to give the lessons on physics to the Princess of Anhalt-Dessau. These lectures were published in 1768 to 1772 in 3 volumes under the title Lettres sur quelques sujets de physique, and for half a century remained a standard treatise on the subject. Of course, Euler's magnificent works were not the only textbooks containing original matter produced at this time. Amongst numerous writers I would specially single out Daniel Bernoulli, Simpson, Lambert, Bézout, Tremblay, and Arbogast as having influenced the development of mathematics. To the first 2 mentioned I have already alluded in the last chapter. End of section 30. Recording by Paul King, Oakville, Ontario, pjk.scripps.mit.edu/pkj.
Chapter 18, Part 2 of A Short Account of the History of Mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripps.mit.edu/pkj. A Short Account of the History of Mathematics by W. W. Rouse Ball. Chapter 18, Leibniz and the Mathematicians of the First Half of the 18th Century, Part 2. Lambert. Johann Heinrich Lambert was born at Mühlhausen on August 28, 1728, and died at Berlin on September 25, 1777. He was the son of a small tailor, and had to rely on his own efforts for his education. From a clerk in some ironworks, he got a place in a newspaper office, and subsequently, on the recommendation of the editor, he was appointed tutor in a private family which secured him the use of a good library, and sufficient leisure to use it. In 1759 he settled in Augsburg, and in 1733 removed to Berlin, where he was given a small pension, and finally made editor of the Prussian Astronomical Almanac. Lambert's most important work were one on optics, issued in 1759, which suggested to Arago the lines of investigation he subsequently pursued, a treatise on perspective published in 1759, to which in 1768 an appendix giving practical applications was added, and a treatise on comets printed in 1761, containing the well-known expression for the area of a focal sector of a conic in terms of the chord and the bounding radii.
Besides these, he communicated numerous papers to the Berlin Academy. Of the most important are his memoir in 1768 on transcendental magnitudes, in which he proved that pi is incommensurable. The proof is given in Legendre's Géométrie, and is there extended to pi squared. His paper on trigonometry, read in 1768, in which he developed de Moivre's theorems on the trigonometry of complex variables, and introduced the hyperbolic sine and cosine denoted by the symbols sin hx, cos hx. His essay entitled The Analytical Observations, published in 1771, which is the earliest attempt to form the functional equations by expressing the given properties in the language of the differential calculus, and then integrating. Lastly, his paper on vis viva, published in 1783, in which for the first time he expressed Newton's second law of motion in the notation of the differential calculus. Of the other mathematicians above mentioned, I here add a few words. Etienne Bezout, born in Namur on March 31st, 1730, and died on September 27th, 1783, besides numerous minor works, wrote a Théorie générale des équations algébriques, published at Paris in 1779, which in particular contained much new and valuable matter on the theory of elimination and symmetrical functions of the roots of an equation. He used as determinants in a paper in the Histoire de l'Académie Royale, 1764, but did not treat of the general theory. Jean Tremblay, born at Geneva in 1749 and died at September 18, 1811, contributed to the development of differential equations, finite differences, and the calculus of probabilities. Louis-François d'Antoine Arbogast, born at Alsace on October 4, 1759, and died at Strasbourg, where he was professor, on April 8, 1803, wrote on series and the derivatives known by his name. He was the first writer to separate the symbols of operation from those of quantity. I do not wish to crowd my pages with an account of those who have not distinctly advanced the subject, but I have mentioned the above writers because their names are still well known. We may however say that the discoveries of Euler and Lagrange in the subjects which they treated were so complete and far-reaching that what their less gifted contemporaries added is not of sufficient importance to require mention in a book of this nature. Lagrange. Joseph Louis Lagrange, the greatest mathematician of the 18th century, was born at Turin on January 25, 1736, and died at Paris on April 10, 1813. His father, who had the charge of the Sardinian military chest, was of good social position and wealthy, but before his son grew up he had lost most of his property in speculations, and young Lagrange had to rely for his position on his own abilities. He was educated at the College of Turin, but it was not until he was 17 that he shewed any taste for mathematics, his interest in the subject being first excited by a memoir by Halley, across which he came by accident. Alone and unaided, he threw himself into mathematical studies, and at the end of a year's incessant toil he was already an accomplished mathematician, and was made a lecturer in the artillery school. The first of these labours was his letter, written when he was still only 19, to Euler, in which he solved the isoperimetrical problem which for more than half a century had been the subject of discussion. To effect a solution in which he sought to determine the form of a function so that a formula in which it entered should satisfy a certain condition, he enunciated the principles of the calculus of variations. Euler recognized the generality of the method adopted and its superiority to that used by himself, and with rare courtesy he withheld a paper that he had previously written which covered some of the same ground, in order that the young Italian might have time to complete his work and claim the undisputed invention of the new calculus. The name of this branch of analysis was suggested by Euler. This memoir at once placed Lagrange in the front rank of mathematicians then living. In 1758 Lagrange established with the aid of his pupils a society which was subsequently incorporated as the Turin Academy, and in the 5 volumes of its Transactions, usually known as the Miscellanea Turinensia, most of his early writings are to be found. Many of these are elaborate works. The first volume contains a memoir of the theory of the propagation of sound, and in this he indicates a mistake made by Newton, obtains a general differential equation for the motion, and integrates it for motion in a straight line. This volume also contains the complete solution of the problem of a string vibrating transversely. In this paper he points out a lack of generality in the solutions previously given by Taylor, D'Alembert, and Euler, and arrives at the conclusion that form of a curve at any time t is given by the equation y equals a sine mx sine nt. The article concludes with a masterly discussion of echoes, beats, and compound sounds. Other articles in this volume are on recurring series, probabilities, and the calculus of variations. The second volume, containing a long paper embodying the results of several memoirs in the first volume on the theory and notation of the calculus of variations, and he illustrates its use by deducing the principle of least action and also by solutions of various problems in dynamics. The third volume includes a solution of several dynamical problems by means of the calculus of variations, some papers on the integral calculus, a solution of Fermat's problem mentioned above, and on the general differential equations of motion for 3 bodies moving under their mutual attractions. In 1761 Lagrange stood without a rival as the foremost mathematician living, but the unceasing labour of the preceding 9 years had seriously affected his health, and the doctors refused to be responsible for his reason or life unless he would take rest and exercise. Although his health was temporarily restored, his nervous system never quite recovered its tone, and henceforth he constantly suffered from attacks of profound melancholy. The next work he produced was in 1764 on the libration of the moon, and an explanation as to why the same face was always turned to the earth, a problem which he treated by aid of virtual work. His solution is especially interesting as containing the germ of the idea of generalized equations of motion, equations which he first formally proved in 1780. He now started to go on a visit to London, but on the way fell ill at Paris. There he was received with the most marked honour, and it was with regret that he left the brilliant society of that city to return to his provincial life at Turin. His further stay in Piedmont was however short. In 1766 Euler left Berlin, and Frederick the Great immediately wrote expressing the wish of the greatest king in Europe to have the greatest mathematician in Europe resident in his court. Lagrange accepted the offer and spent the next 20 years at Prussia, where he produced not only the long series of memoirs published at the Berlin and Turin Transactions, but his monumental work Mécanique analytique. His residence at Berlin commenced with an unfortunate mistake. Finding most of his colleagues married, and assured by their wives that it was the only way to be happy, he married. His wife soon died, but the union was not a happy one. Lagrange was a favourite of the king, who used frequently to discourse to him on the advantage of perfect regularity of life. The lesson went home, and thenceforth Lagrange studied his mind and body as though they were machines, and found by experiment the exact amount of work which he was able to do without breaking down. Every night he set himself a definite task for the next day, and on completing any branch of a subject he wrote a short analysis to see what points in the demonstrations or in the subject matter were capable of improvement. He always thought out the subject of his papers before he began to compose them, and usually wrote them straight off without a single erasure or correction. His mental activity during these 20 years was amazing. Not only did he produce his splendid Mécanique analytique, but he contributed between 1 and 200 papers to the academies of Berlin, Turin, and Paris. Some of these are complete treatises, and all without exception are of a high order of excellence, except for a short time when he was ill and produced on an average about one memoir a month. Of these I note the following as among the most important. First, his contributions to the fourth and fifth volumes, 1766 to 1773, of the Miscellanea Taurinensia, of which the most important was the one in 1771, in which he discussed how numerous astronomical observations should be combined so as to give the most probable result. And later his contributions to the first two volumes, 1784 to 1785, of the Transactions of the Turin Academy, to the first of which he contributed a paper on the pressure exerted by fluids in motion, and to the second an article on integration by infinite series, and the kind of problems for which it is suitable. Most of the memoirs sent to Paris were on astronomical questions, and among these I ought particularly to mention his memoir on the Jovian system in 1766, his essay on the problem of the three bodies in 1772, his work on the secular equation of the moon in 1773, and his treatise on cometary perturbations in 1778. These were all written on subjects proposed by the French Academy, and in each case the prize was awarded to him. The greater number of his papers during the same time were, however, contributed to the Berlin Academy. Several of them deal with questions on algebra. In particular I may mention 1. His discussion of the solution of indeterminate equations on integers in 1770, with special notice of indeterminate quadratics in 1769. 2. His tract on the theory of elimination, 1770. 3. His memoirs on the general process for solving an algebraical equations of any degree, 1770 and 1771. This method fails for equations of an order above the fourth, because then it involves the solution of an equation of higher dimensions than the one proposed, but it gives all the solutions of his predecessors as modifications of a single principle. He found, however, the complete solution of a binomial equations of any degree. And fourth, lastly, in 1773 he treated of determinants of the second and third order. Several of his early papers also deal with questions connected with the neglected but singularly fascinating subject of the theory of numbers. Among these are 1. His proof of the theorem that every integer which is not a square can be expressed as a sum of either 2, 3, or 4 integral squares, 1770. His proof of Wilson's theorem that if n be prime, then n minus 1 factorial plus 1 is always a multiple of n, 1771. 3. His memoirs of 1773, 1775, and 1777, which give the demonstrations of several results enunciated by Fermat and not previously proved. 4. And lastly, his method for determining the factors of numbers of the form x squared plus ay squared. There are also numerous articles on various points of analytical geometry. In 2 of them, in 1792 and 1793, he reduced the equations of the quadrics or conicoids to their canonical forms. During the years from 1772 to 1785 he contributed a long series of memoirs which created the science of differential equations, at any rate as far as partial differential equations are concerned. I do not think that any previous writer had done anything beyond considering equations of some particular form. A large part of these results were collected in the second edition of Euler's integral calculus, which was published in 1794. His papers on mechanics require no separate mention here, as the results arrived at are embodied in the Mécanique analytique, which is described below. Lastly, there are numerous memoirs on problems in astronomy.
Of these, the most important are the following. 1. The attraction of ellipsoids, 1773. This is founded on Maclaurin's work. 2. On the secular equation of the moon, 1773. Also noticeable for the earliest introduction of the idea of the potential. The potential of a body at any point is the sum of the mass of every element of the body when divided by its distance from the point. Lagrange showed that if the potential of a body at an external point were known, the attraction in any direction could be at once found. The theory of the potential was elaborated in a paper sent to Berlin in 1777. 3. On the motion of the nodes of a planet's orbit, 1774. 4. On the stability of planetary orbits, 1776. 5. Two memoirs in which the method of determining the orbit of a comet from 3 observations is completely worked out, 1778 and 1783. This is not indeed proved practically available, but his system of calculating the perturbations by means of mechanical quadratures has formed the basis of most subsequent researches on the subject. 6. His determination of the secular and periodic variations of the elements of the planet, 1781 to 1784. The upper limits assigned for these agree closely with those obtained later by Leverrier, and he proceeded as far as the knowledge then possessed of the masses of the planets permitted. 7. 3 memoirs on the method of interpolation, 1783, 1792, and 1793. The part of finite differences dealing therewith is now in the same stage as that in which Lagrange left it. Over and above these various papers, he composed his great treatise Mécanique analytique. In this he lays down the law of virtual work, and from that one fundamental principle by the aid of the calculus of variations he deduces the whole of mechanics, both of solids and fluids. The object of the book is to shew that the subject is implicitly included in a single principle, and to give the general formulae from which any particular result can be obtained. The method of generalized coordinates by which he obtained this result is perhaps the most brilliant result of his analysis. Instead of following the motion of each individual part of a material system, as D'Alembert and Euler had done, he shewed that if we determine its configuration by a sufficient number of variables, whose number is the same as that of the degrees of freedom possessed by the system, then the kinetic and potential energies of the system can be expressed in terms of these, and the differential equations of motions then deduced by simple differentiation. For example, in dynamics of a rigid system, he replaces the consideration of the particular problem by the general equation, which is now usually written in the form of d by dt times the partial derivative of capital T with respect to theta minus the partial derivative of capital T with respect to theta plus the partial derivative of v with respect to theta equals 0. Amongst other minor theorems here given, I may mention the proposition that the kinetic energy imparted by given impulses to a material system under given constraints is a maximum, and the principle of least action. All the analysis is so elegant that Sir William Rowan Hamilton said the work could be only described as a scientific poem. It may be interesting to note that Lagrange remarked that the mechanics was really a branch of pure mathematics analogous to a geometry of 4 dimensions, namely the time and the 3 coordinates of the point in space, and it is said that he prided himself that from the beginning to the end of the work there was not a single diagram. At first no printer could be found who would publish the book, but Legendre at last persuaded a Paris firm to undertake it, and it was issued under his supervision in 1788. In 1787 Frederick died, and Lagrange, who had found the climate of Berlin trying, gladly accepted the offer of Louis XVI to migrate to Paris. He received similar invitations from Spain and Naples. In France he was received with every mark of distinction, and special apartments in the Louvre were prepared for his reception. For the first 2 years of his residence Here he was seized with an attack of melancholy, and even the printed copy of his Mécanique, on which he had worked for a quarter of a century, lay for more than 2 years unopened on his desk. Curiosity as to the results of the French Revolution first stirred him out of his lethargy, a curiosity which soon turned to alarm as the Revolution developed. It was about the same time, 1792, that the unaccountable sadness of his life and timidity moved the compassion of a young girl who insisted on marrying him, and proved a devoted wife to whom he became warmly attached. Although the decree of October 1793, which ordered all foreigners to leave France, specially exempted him by name, he was preparing to escape when he was offered the presidency of the Commission for the Reform of Weights and Measures. The choice of the units finally selected was largely due to him, and it was mainly owing to his influence that the decimal subdivision was accepted by the Commission of 1799. The general idea of the decimal system was taken from a work by Thomas Williams entitled Method for Fixing a Universal Standard for Weights and Measures, published in London in 1788. This almost unknown writer has hardly received the credit due to his suggestion. Though Lagrange had determined to escape from France while there was yet time, he was never in any danger, and the different revolutionary governments, and at a later time Napoleon, loaded him with honours and distinctions. A striking testimony to the respect in which he was held was shewn in 1796 when the French commissary in Italy ordered to attend in full state on Lagrange's father and tender the congratulations of the Republic on the achievements of his son, who had done honour to all mankind by his genius, and whom it was the special glory of Piedmont to have produced. In 1795 Lagrange was appointed to a mathematical chair at the newly established École Normale, which only enjoyed a brief existence of 4 months. His lectures here were quite elementary, and contained nothing of any special importance, but they were published because the professors had to pledge themselves to the representatives of the people and to each other neither to read nor to repeat from memory, and the discourses were ordered to be taken down in shorthand in order to enable the deputies to see how the professors acquitted themselves. On the establishment of the École Polytechnique in 1797, Lagrange was made a professor, and his lectures there are described by mathematicians who had the good fortune to be able to attend them as almost perfect both in form and matter. Beginning with the merest elements, he led his hearers on until, almost unknown to themselves, they were themselves extending the bounds of the subject. Above all, he impressed on his pupils the advantage of always using general methods expressed in a symmetrical notation. His lectures on the differential calculus form the basis of his Théorie des fonctions analytiques, which was published in 1797. This work is the extension of an idea contained in a paper he had sent to the Berlin Memoirs in 1772, and its object is to substitute for the differential calculus as a group of theorems based on the development of algebraic functions in series. A somewhat similar method had been previously used by John Landon in his residual analysis, published in London in 1758. Lagrange believed that he could thus get rid of those difficulties connected with the use of infinitely large or infinitely small quantities which philosophers professed to see in the usual treatment of the differential calculus. The book is divided into 3 parts. Of these, the first treats of the general theory of functions, and gives an algebraic proof of Taylor's theorem, the validity of which is, however, to open the question. The second deals with applications to geometry, and the third with applications to mechanics. Another treatise on the same lines was his Leçons sur le calcul des fonctions, issued in 1804. These works may be considered as the starting point for the researches of Cauchy and Jacobi. At a later period, Lagrange reverted to the use of infinitesimals in preference to founding the differential calculus on a study of algebraic forms, and in the preface to the second edition of the Mécanique, which was issued in 1811, he justifies their use and concludes by saying that when we have grasped the spirit of the infinitesimal method and have verified the exactness of its results either by the geometrical method of prime and ultimate ratios or by the analytical method of derived functions, we may employ infinitely small quantities as a sure and valuable means of shortening and simplifying our proofs. His Résolution des équations numériques, published in 1798, was also the fruit of his lectures at the Polytechnic. In this he gives the method of approximating to the real roots of an equation by means of continued fractions, and enunciates several other theorems. In a note at the end he shews how Fermat's theorem that a to the power of p minus 1 is defined as 0 mod p, where p is prime and a is prime to p, combined with a certain suggestion due to Gauss, may be applied to give the complete algebraical solution of any binomial equation. He also here explains how the equation whose roots are the squares of the differences of the roots of the original equation may be used so as to give considerable information so as to the position and nature of those roots. The theory of the planetary motions had formed the subject of some of the most remarkable of Lagrange's Berlin papers. In 1806 the subject was reopened by Poisson, who, in a paper read before the French Academy, shewed that Lagrange's formula led to certain limits for the stability of the orbits. Lagrange, who was present, now discussed the whole subject afresh, and in a memoir communicated to the Academy in 1808, explained how by the variation of arbitrary constants the periodical and secular inequalities of any system of mutually interacting bodies could be determined. In 1810 Lagrange commenced a thorough revision of the Mécanique analytique, but he was able to complete only about two-thirds of it before his death. In appearance he was of medium height and slightly formed, with pale blue eyes and a colourless complexion. In character he was nervous and timid. He detested controversy, and to avoid it willingly allowed others to take the credit for what he had himself done. Lagrange was above all a student of pure mathematics. He sought and obtained far-reaching abstract results, and was content to leave the applications to others. Indeed, no considerable part of the discoveries of his great contemporary Laplace consists of the applications of the Lagrangian formulae to the facts of nature. For example, Laplace's conclusions on the velocity of sound and the secular acceleration of the moon are implicitly involved in Lagrange's results. The only difficulty in understanding Lagrange is that of the subject matter and of the extreme generality of his processes, but his analysis is as lucid and luminous as it is symmetrical and ingenious. A recent writer speaking of Lagrange says truly that he took a prominent part in the advancement of almost every branch of pure mathematics. Like Diophantus and Fermat, he proposed a special genius for the theory of numbers, and in this subject he gave solutions of most of the problems which had been proposed by Fermat, and added some theorems of his own. He created the calculus of variations. To him too the theory of differential equations is indebted for its position as a science rather than as a collection of ingenious artifices for the solution of particular problems. To the calculus of finite differences he contributed the formula of interpolation which bears his name. But above all he impressed on mechanics, which it will be remembered he considered a part of pure mathematics, that generality and completeness towards which his labours invariably tended. End of section 31. Recording by Paul King, Oakville, Ontario. pjk.scripps.mit.edu/pkj. Chapter 18, Part 2 of A Short Account of the History of Mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain.
For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripts.mit.edu/pkj. A short account of the history of mathematics by W. Rouse. Chapter 18. Leibniz and the mathematicians of the first half of the 18th century, Part 3. Laplace. Pierre-Simon Laplace was born at Beaumont-en-Auge in Normandy on March 23, 1749, and died at Paris on March 5, 1827. He was the son of a small cottager or perhaps a farm labourer, and owed his education to the interest excited in some wealthy neighbours by his abilities and engaging presence. Very little is known of his early years, for when he became distinguished he held himself aloof from both his relatives and from those who had assisted him. A similar pettiness of character marked many of his actions. It would seem that from a pupil he became an usher in the school at Beaumont, but having procured a letter of introduction to D'Alembert, he went to Paris to push his fortune. A paper on the principles of mechanics excited D'Alembert's interest, and on his recommendations a place in the military school was offered to Laplace. Secure of a competency, Laplace now threw himself onto the original research, and in the next 17 years, 1771 to 1787, he produced much of his original work in astronomy. This commenced with a memoir read before the French Academy in 1773, which he shewed that the planetary motions were stable, and carried the proof as far as the cubes of the eccentricities and inclinations. This was followed by several papers on points in the integral calculus, finite differences, differential equations, and astronomy. During the years 1784 to 1787 he produced some memoirs of exceptional power. Prominent among those is one read in 1784 and reprinted in the third volume of the Mécanique Céleste, in which he completely determined the attraction of a spheroid on a particle outside it. This is memorable for the introduction into an analysis of spherical harmonics or Laplace's coefficients, and also for the development of the use of potential, a name first given by Green in 1828. If the coordinates of 2 points be r mu omega and r prime mu prime omega prime, and r prime is not less than r, the reciprocal of the distance between them can be expanded in powers of r divided by r prime, and the respective coefficients are Laplace coefficients. Their utility arises from the fact that every function of the coordinates of a point on a sphere can be expanded in a series of them. It should be stated that the similar coefficients for space of 2 dimensions, together with some of their properties, had previously been given by Legendre in a paper sent to the French Academy in 1783. Legendre had good reason to complain of the way in which he was treated in this manner. This paper is also remarkable for the development of the idea of the potential, which was appropriated from Lagrange, who had used it in his memoirs of 1773, 1777, and 1780. Laplace shewed that the potential always satisfies the differential equation del squared v equals the second partial derivative of the voltage with respect to x plus the second partial derivative of the voltage with respect to y plus the second partial derivative of the voltage with respect to z equals 0, and on this result his subsequent work on attractions was based. The quantity del squared v had been termed the concentration of v, and its value at any point indicates the excess of the value of v over its mean value in the neighbourhood of the point. Laplace's equation, or the more general form del squared v equals negative 4 pi rho, appears in all branches of mathematical physics. According to some writers, this follows at once from the fact that del squared is a scalar operator, or the equation may represent analytically some general law of nature which has not yet been reduced to words, or possibly, I have sometimes thought, it might be regarded by a Kantian as the outward sign of one of the necessary forms through which all phenomena are perceived. This memoir was followed by another on planetary inequalities, which was presented in 3 sections in 1784, 1785, and 1786. This deals mainly with the explanation of the great inequality of Jupiter and Saturn. Laplace shewed by general considerations that the mutual action of two planets could never largely affect the eccentricities and inclinations of their orbits, and that the peculiarities of the Jovian system were due to the near approach to commensurability of the mean motions of Jupiter and Saturn. Further developments of these theorems on planetary motion were given in his 2 memoirs of 1788 and 1789. It was on these data that Delambre computed his astronomical tables. The year 1787 was rendered memorable by Laplace's explanation and analysis of the relation between the lunar acceleration and the secular changes in the eccentricity of the Earth's orbit. This investigation completed the proof of the stability of the whole solar system on the assumption that it consists of a collection of rigid bodies. All the memoirs above alluded to were presented to the French Academy, and they are printed in the Mémoires présentés par divers savants. Laplace now set himself the task to write a work which should offer a complete solution of the great mechanical problem presented by the solar system, and bring theory to coincide so closely with observation that empirical equations should no longer find a place in astronomical tables. The result is embodied in the Exposition du Système du Monde and the Mécanique Céleste. The former was published in 1796 and gives a general explanation of the phenomena with a summary of the history of astronomy, but omits all details. The nebular hypothesis was here enunciated. According to this hypothesis, the solar system has been evolved from a globular mass of incandescent gas rotating around an axis through its center of mass. As it cooled, this mass contracted and successive rings broke off from its outer edge. These rings in their turn cooled and finally condensed into the planets, while the Sun represents the central core which was still left. Certain corrections required by modern science were added by M. Roche, and recently the theory has been discussed critically by R. Wolf. The arguments against the hypothesis are summed up in Fay's Origine du Monde, Paris, 1884. Where an ingenious modification of the hypothesis is proposed, by which the author attempts to explain the peculiarities of the axial rotation of Neptune and Uranus, and the retrograde motion of the satellites of the latter planet. Perhaps modern opinion is inclined to attribute the separation of the various members of the planetary system to tidal friction rather than to the successive separation and condensation of nebular rings. But the subject is one of great difficulty. According to the rule published by Titus of Wittenberg in 1766, but generally known as Bode's law, from the fact that attention was called to it by Johann Ellet Bode in 1778, the distances of the planets from the Sun are nearly in the ratio of the numbers 0 plus 4, 3 plus 4, 6 plus 4, 12 plus 4, etc., and the n minus 2th term being 2 to the power n times 3 with 4 added. It would be an interesting fact if this could be deduced from either the nebular or the tidal hypothesis, but so far as I am aware, only one serious attempt to do so has been made, and the conclusion was that the law was not sufficiently exact to be more than a convenient means of remembering the general result. The substance of Laplace's hypothesis had been published by Kant in 1755 in his Allgemeine Naturgeschichte, but it is probable that Laplace was not aware of this. This historical summary procured for its author the honour of admission to the 40 of the French Academy. It is commonly esteemed one of the masterpieces of French literature, though it is not altogether reliable for the later periods of which it treats. The full analytical discussion of the solar system is given in the Mécanique Céleste, published in 5 volumes, volumes 1 and 2 in 1799, volume 3 in 1802, volume 4 in 1805, and volume 5 in 1825. An analysis of the contents is given in the English Cyclopedia. The first 2 volumes contain methods for calculating the motions of the planets, determining their figures, and resolving tidal problems. The 3rd and 4th volumes contain the application of these methods and also several astronomical tables. The 5th volume is mainly historical, but it gives as appendices the results of Laplace's latest researches. Laplace's own investigations embodied in it are so numerous and valuable that it is regrettable to have to add that many results are appropriated from writers with scanty or no acknowledgment, and the conclusions, which have been described as the organized result of a century of patent toil, are generally mentioned as if they were due to Laplace, and it is said, for I have not looked up into the matter myself, that the praise which he lavishes on Newton and Clairaut is only the cloak under which he appropriates the work of other less known writers. The Mécanique Céleste is by no means easy reading. Biot, who assisted Laplace in revising it for the press, says that Laplace himself was frequently unable to recover the details in the chain of reasoning, and, if satisfied that the conclusions were correct, he was content to insert the constantly recurring formula "il était à voir." The best tribute to the excellency of the work is that it left very little for his successors to add. It is not only the translation of the Principia into the language of the differential calculus, but it also completes part of which Newton had been unable to fill in the details. M. Tisserand's recent work may be considered as a continuation of Laplace's treatise. Laplace went in state to beg Napoleon to accept a copy of his work, and the following account of the interview is well authenticated, and so characteristic of all parties concerned that I quote it in full. Someone had told Napoleon that the book contained no mention of the name of God. Napoleon, who was fond of putting embarrassing questions, received it with the remark, "Monsieur Laplace, they tell me you have written this large book on the system of the universe, and have never even mentioned its creator." Laplace, who, though most supple of politicians, was as stiff as a martyr on every point of his philosophy, drew himself up and answered bluntly, "Je n'avais pas besoin de cette hypothèse-là." Napoleon, greatly amused, told this reply to Lagrange, who exclaimed, "Ah, c'est une belle hypothèse! Ça explique beaucoup de choses." In 1812 Laplace issued his Théorie analytique des probabilités. The theory is stated to be only common sense expressed in mathematical language. The method of estimating the ratio of the number of favourable cases to the whole number of possible cases has been indicated by Laplace in a paper written in 1779. It consists in treating the successive values of any function as the coefficients in the expansion of another function with reference to a different variable. The latter is therefore called the generating function of the former. Laplace then shews how by means of interpolation these coefficients may be determined from the generating function. Next he attacks the converse problem, and from the coefficients he finds the generating function. This is offered by the solution of an equation in finite differences. The method is cumbersome, and in consequence of the increased power of analysis is now rarely used. A summary of Laplace's reasoning is given in the article on probability in his Encyclopaedia Metropolitana. This treatise includes an exposition of the method of least squares, which is a remarkable testimony to Laplace's command over the process of analysis. The method of least squares for the combination of numerous observations had been given empirically by Gauss and Legendre, but the 4th chapter of this work contains a formal proof of it, on which the whole of the theory of errors has been since based. This was effected only by a most intricate analysis, specially invented for the purpose, but the form in which it is presented is so meagre and unsatisfactory that in spite of the uniform accuracy of the results, it was at one time questioned whether Laplace had actually gone through the difficult work he so briefly and often incorrectly indicates. In 1819, Laplace published a popular account of his work on probability. This book bears the same relation to his Théorie des probabilités that the Système du monde does to the Mécanique céleste. Amongst the minor discoveries of Laplace in pure mathematics, I may mention his discussion simultaneously with Vandermonde of the general theory of determinants in 1772, his proof that every equation of an even degree must have at least one real quadratic factor, his reduction of the solution of linear differential equations to definite integrals, and his solution to the linear partial equation of the second order. He was also the first to consider the difficult problems involved in the equations of mixed differences, and to prove that the solution of an equation in finite differences of the first degree and the second order might always be obtained in the form of a continued fraction. Besides these original discoveries, he determined in his theory of probabilities the values of a number of the more common definite integrals, and in the same book gave the general proof of the theorem enunciated by Lagrange for the development of any implicit function in a series by means of differential coefficients. In theoretical physics, the theory of capillary attraction is due to Laplace, who accepted the idea propounded by Hauksbee in the Philosophical Transactions for 1709, that the phenomenon was due to a force of attraction which was insensible at sensible distances. The part which deals with the action of a solid on a liquid and the mutual actions of two liquids was not worked out thoroughly, but ultimately was completed by Gauss. Newman later filled in a few details. In 1862, Lord Kelvin, Sir William Thomson, shewed that if we assume the molecular constitution of matter, the laws of capillary attraction can be deduced from the Newtonian law of gravitation. Laplace in 1816 was the first to point out explicitly why Newton's theory of vibratory motion gave an incorrect value for the velocity of sound. The actual velocity is greater than that calculated by Newton in consequence of the heat developed by the sudden compression of air, which increases the elasticity and therefore the velocity of sound transmitted. Laplace's investigations in practical physics were confined to those carried on by him jointly with Lavoisier in the years 1782 and 1784 on the specific heat of various bodies. Laplace seems to have regarded analysis as merely a means of attacking physical problems, though the ability with which he invented the necessary analysis is almost phenomenal. As long as his results were true, he took but little trouble to explain the steps by which he arrived at them. He never studied elegance or symmetry in his processes, and it was sufficient for him if he could by any means solve the particular question he was discussing. In these respects he stands in marked contrast to his great contemporary Lagrange. It would have been well for Laplace's reputation if he had been content with his scientific work, but above all things he coveted social fame. The skill and rapidity with which he managed to change his politics as occasion required would be amusing if they had not been so servile. As Napoleon's power increased, Laplace abandoned his republican principles, which, since they had faithfully reflected the opinions of the party in power, had themselves gone through numerous changes, and begged for the First Consul to give him the post of Minister of the Interior. Napoleon, who desired the support of men of science, accepted the offer, but a little less than 6 weeks saw the close of Laplace's political career. Napoleon's memorandum on the subject is as follows.
Géomètre de premier rang, Laplace ne tarda à se montrer administrateur plus que médiocre. Dès son premier travail, nous reconnûmes que nous étions trompés. Laplace ne cessant aucune question sous son véritable point de vue. Il cherchait des subtilités partout, n'avait que des idées problématiques.
portait enfant l'esprit des infiniment petits jusque dans l'administration. Although Laplace was expelled from office, it was desirable to retain his allegiance. He was accordingly raised to the Senate, and to the third volume of the Mécanique Céleste he prefixed a note that of all the truths therein contained, the most precious to the author was the declaration he thus made of his devotion toward the peacemaker of Europe. In copies sold after the Restoration, this was struck out. In 1814 it was evident that the empire was falling. Laplace hastened to tender his services to the Bourbons, and on the Restoration was rewarded with the title of Marquis. The contempt that his more honest colleagues felt for his conduct in the matter may be read in the pages of Paul Louis Courier. His knowledge was useful on the numerous scientific commissions on which he served, and probably accounts for the manner in which his political insincerity was overlooked. But the pettiness of his character must not make us forget how great were his services to science. That Laplace was vain and selfish is not denied by his warmest admirers. His conduct to the benefactors of his youth and his political friends was ungrateful and contemptible, while his appropriation of the results of those who were comparatively unknown seems to be well established and is absolutely indefensible. Of those whom he thus treated, three subsequently rose to distinction, Legendre and Fourier in France and Young in England, and never forgot the injustice of which they had been the victims. On the other side, it may be said that on some questions he shewed independence of character, and he never concealed his views on religion, philosophy, or science, however distasteful they might be to the authorities in power. It should be also added that towards the close of his life, and especially to the work of his pupils, Laplace was both generous and appreciative, and in one case suppressed a paper of his own in order that a pupil might have the sole credit of the discovery. Legendre. Adrien Marie Legendre was born at Toulouse on September 18, 1752, and died at Paris on January 10, 1833. The leading events of his life are very simple and may be summed up briefly. He was educated at the Mazarin College in Paris, appointed the professor at the military school in Paris in 1777, was a member of the Anglo-French Commission of 1787 to connect Greenwich and Paris geodetically, served on several of the public commissions from 1792 to 1810, was made a professor at the Normal School in 1795, and subsequently held a few minor government appointments. The influence of Laplace was steadily exerted against his obtaining office or public recognition, and Legendre, who was a timid student, accepted the obscurity to which the hostility of his colleague condemned him. Legendre's analysis is of a high order of excellence, and is second only to that produced by Lagrange and Laplace, though it is not so original. His chief works are his Géométrie, his Théorie des Nombres, and his Calcul Intégral, and his Fonctions Elliptiques. These include the results of his various papers on these subjects. Besides these he wrote a treatise which gave the rule for the method of least squares, and two groups of memoirs, one on the theory of attractions and the other on geodetical operations. The memoirs on attractions are analyzed and discussed in Todhunter's History of the Theory of Attraction. The earliest of these memoirs, presented in 1783, was on the attraction of spheroids. This contained the introduction of Legendre's coefficients, which are sometimes called circular or zonal harmonics, and which are particular cases of Laplace's coefficients. It also includes the solution of a problem in which the potential is used. The second memoir was communicated in 1784, and is of the form of equilibrium of a mass of rotating liquid, which is approximately spherical. The third, written in 1786, is on the attraction of confocal ellipsoids. The fourth is on the figure which a fluid planet would assume, and its law of density. His papers on geodesy are 3 in number and were presented to the Academy in 1787 and 1788. The most important result is that by which a spherical triangle may be treated as a plane, provided certain corrections are applied to the angles. In connection with this subject he paid considerable attention to geodesics. The method of least squares was enunciated in his Nouvelle Méthode, published in 1806. To which supplements were added in 1810 and 1820. Gauss independently had arrived at the same result and had used it in 1795 and published it and the law of facility in 1809. Laplace was the earlier writer to give a proof of it. This was in 1812. On the other books produced by Legendre, the one most widely known is his Éléments de géométrie, which was published in 1794 and was generally adopted on the continent as a substitute for Euclid. The later editions contain the elements of trigonometry and proofs of the irrationality of pi and pi squared. An appendix on the difficult question of the theory of parallel lines was issued in 1803 and is bound up with most of the subsequent editions. His Théorie des Nombres was published in 1798 and appendices were added in 1816 and 1825. The third edition, issued in 2 volumes in 1830, includes the results of his various later papers and still remains a standard work on the subject. It may be said that he here carried the subject as far as was possible by the application of ordinary algebra, but he did not realize that it might be regarded as a higher arithmetic and so form a distinctive subject in mathematics. The law of quadratic reciprocity, which connects any 2 odd primes, is first proved in this book, but the result had been enunciated in a memoir of 1785. Gauss called the proposition the gem of arithmetic, and no less than 6 separate proofs are to be found in his works. The theorem is as follows. If p be a prime and n be a prime to p, then we know that the remainder when the square root of n to the power of p minus 1 is divided by p is either plus 1 or minus 1. Legendre denoted this remainder by n over p. When the remainder is plus 1, it is possible to find a square number which, when divided by p, leaves a remainder n, that is, n is a quadratic residue of p. When the remainder is minus 1, there exists no such square number, and n is a non-residue of p. The law of quadratic reciprocity is expressed by the theorem that if a and b be any odd primes, then the Legendre symbol a over b times the Legendre symbol b over a is the fourth root of minus 1 to the power of a minus 1 times b minus 1. Thus, if b is a residue of a, then a is also a residue of b, unless both the primes of a and b are of the form 4 times m plus 3. In other words, if a and b be odd primes, then we know that the square root of a to the power of b minus 1 is defined as plus or minus 1 mod b, and the square root of b to the power of a minus 1 is defined as plus or minus 1 mod a. But Legendre's law and the 2 ambiguities will be either both positive or both negative unless a and b are both of the form 4m plus 3. Thus, if one odd prime be a non-residue of another, then the latter will be a non-residue of the former. Gauss and Kummer have subsequently proved similar laws of cubic and biquadratic reciprocity, and an important branch of the theory of numbers has been based on these researches. This work also contains the useful theorem by which, when it is possible, an indeterminate equation of the second degree can be reduced to the form ax squared plus by squared plus cz squared equals 0. Legendre too here discussed the forms of numbers which can be expressed as the sums of 3 squares, and he proved, article 404, that the number of primes less than n is very approximately n divided by the quantity log n minus 1.08366. The Exercice de calcul intégral was published in 3 volumes, 1811, 1817, and 1826. Of these, the third and most of the first were devoted to elliptic functions, the bulk of this being ultimately included in the Fonctions elliptiques. The contents of the remainder of the treatise are of a miscellaneous character. They include integration by series, definite integrals, and in particular an elaborate discussion of the beta and the gamma functions. The Traité des Fonctions elliptiques was issued in 2 volumes in 1825 and 1826 and is the most important of Legendre's works. A third volume was added a few weeks before his death, and contains 3 memoirs of the researches of Abel and Jacobi. Legendre's investigations have commenced with a paper written in 1786 on elliptic arcs, but here and in his other papers he treated the subject merely as a branch of the integral calculus. Tables of the elliptic integrals were constructed by him. The modern treatment of the subject is founded on that of Abel and Jacobi. The superiority of their methods was at once recognized by Legendre, and almost the last act of his life was to recommend those discoveries which he knew would consign his own labours to comparative oblivion. This may serve to remind us of a fact which I wish to specially emphasize, namely, that Gauss, Abel, Jacobi, and some others of the mathematicians alluded to in the next chapter were contemporaries of the members of the French school. Pfaff. I may here mention another writer who also made a special study of the integral calculus. This was Johann Friedrich Pfaff, born in Stuttgart on December 22, 1765, and died at Halle on April 21, 1825, who was described by Laplace as the most eminent mathematician in Germany at the beginning of this century, a description which, had it not been for Gauss's existence, would have been true enough. Pfaff was the precursor of the German school, which under Gauss and his followers has largely determined the lines on which mathematics have developed during this century. He was an intimate friend of Gauss, and in fact the two mathematicians lived together at Helmstadt for the year after Gauss finished his university course in 1798. Pfaff's chief work was his unfinished Disquisitions analyticae on the integral calculus, published in 1797, and his most important memoirs were either on the calculus or on differential equations. On the latter subject, his paper read before the Berlin Academy in 1814 is still a standard authority. The creation of modern geometry. While Euler, Lagrange, Laplace, and Legendre were perfecting analysis, the members of another group of the French mathematicians were extending the range of geometry by methods similar to those previously used by Desargues and Pascal. The most eminent of those who created modern synthetic geometry was Poncelet, but the subject is also associated with the names of Monge and L. Carnot. Its development in more recent times is largely due to Steiner, von Staudt, and Cremona. Monge. Gaspard Monge was born at Bonn on May 10th, 1746, and died at Paris on July 28, 1818. He was a son of a small peddler, and was educated in the schools of the Oratorians, one of which he subsequently became an usher. A plan of Bonn which he had made fell into the hands of an officer who recommended the military authorities to admit him to their training school at Mézières. His birth, however, precluded his receiving commission in the army, but his attendance at an annex of the school where surveying and drawing were taught was tolerated, though he was told that he was not sufficiently well born to be allowed to attempt problems which required calculation. At last his opportunity came. A plan of a fortress having to be drawn from data supplied by certain observations, he did it by a geometrical construction. At first the officer in charge refused to receive it because etiquette required that not less than a certain time should be used in making such drawings, but the superiority of the method over that then taught was so obvious that it was accepted. and in 1768 Monge was made professor, on the understanding that the results of his descriptive geometry were to be a military secret confined to the officers above a certain rank. In 1780 he was appointed to a chair of mathematics in Paris, and this with several provincial appointments which he held gave him a comfortable income. The earliest paper of any special importance which he communicated to the French Academy was one in 1781 in which he discussed the lines of curvature drawn on a surface. These had been first considered by Euler in 1760 and defined as those normal sections whose curvature was a maximum or a minimum. Monge treated them as the locus of those points on the surface as which successive normals intersect, and thus obtained the general differential equation. He applied his results to the central quadrics in 1795. In 1786 he published his well-known work on statics. Monge eagerly embraced the doctrines of the Revolution. In 1792 he became Minister of the Marine and assisted the Committee of the Public Safety in utilizing science for the defense of the Republic. When the terrorists obtained power he was denounced and only escaped the guillotine by a hasty flight. On his return in 1794 he was made professor at the short-lived Normal School, where he gave lectures on descriptive geometry. The notes of these were published under a regulation alluded to above. In 1796 he went to Italy on the roving commission which was sent with orders to compel the various Italian towns to offer any pictures, sculpture, or other works of art that they might possess as a present or in lieu of contributions to the French Republic for removal to Paris. In 1798 he accepted a mission to Rome, and after executing it joined Napoleon in Egypt. Thence, after the naval and military victories at England, he escaped to France. He was then made professor at the Polytechnic School, where he gave lectures on descriptive geometry. These were published in 1800 in the form of a textbook entitled Géométrie descriptive. This work contains prepositions on the form and relative position of geometrical figures deduced by the use of transversals. The theory of perspective is considered, and this includes the art of representing in 2 dimensions geometrical objects which are of 3 dimensions, a problem which Monge usually solved by the aid of 2 diagrams, one being the plan and the other being the elevation. Monge also discussed the question as to whether, if in solving a problem certain subsidiary quantities introduced to facilitate the solution become imaginary, the validity of the solution is thereby impaired, and he shewed that the result would not be affected. On the Restoration he was deprived of his offices and honours, a degradation which preyed on his mind and which he did not long survive. Most of his miscellaneous papers are embodied in his works Application de l'algèbre à la géométrie, published in 1805, and Application de l'analyse à la géométrie, the 4th edition of which, published in 1819, was revised by him just before his death. It contains, among other results, his solution of a partial differential equation of the 2nd order. Carnot. Lazare Nicolas Marie Carnot, born at Nolay on May 13, 1753, and died at Magdeburg on August 22, 1823, was educated at Burgundy and obtained a commission at the Engineer Corps of Condé. Although in the army, he continued his mathematical studies which he felt great interest. His first work, published in 1784, was on machines. It contained a statement which foreshadows the principle of energy as applied to a falling weight, and the earliest proof of the fact that kinetic energy is lost in the collision of bodies. In the outbreak of the Revolution in 1789 he threw himself into politics. In 1793 he was elected on the Committee of Public Safety, and the victories of the French army were largely due to his powers of organization and enforcing discipline. He continued to occupy a prominent place in every successive form of government till 1796, when, having opposed to Napoleon's coup d'etat, he had to fly from France. He He took refuge in Geneva, and there in 1797 issued La Métaphysique de Calcul Infinitesimal. In 1802 he assisted Napoleon, but his sincere republican convictions were inconsistent with the retention of office. In 1803 he produces Géométrie des positions. This work deals with projective rather than descriptive geometry. It also contains an elaborate discussion of the geometrical meaning of negative roots of an algebraical equation. In 1814 he offered his services to fight for France, though not for the empire, and on the Restoration he was exiled. Poncelet. Jean-Victor Poncelet, born at Metz in July 1st, 1788, and died at Paris on December 22nd, 1867, held a commission in the French engineers. Having been made a prisoner in the French retreat from Moscow in 1812, he occupied his enforced leisure by writing the Traité des propriétés projections des figures, published in 1822, which was long one of the best-known textbooks on modern geometry. By means of projection, reciprocation, and homologous figures, he established all the chief properties of conics and quadrics. He also treated the theory of polygons. His treatise on the practical mechanics in 1828, his memoir on water mills in 1826, and his report on the English machinery and tools exhibited at the International Exhibition held in London in 1851 deserve mention. He contributed numerous articles to Crell's journal. The most valuable of these deal with the explanation of imaginary solutions and geometrical problems by the aid of the doctrine of continuity. The development of mathematical physics. It will be noticed that Lagrange, Laplace, and Legendre mostly occupied themselves with analysis, geometry, and astronomy. I am inclined to regard Cauchy and the French mathematicians of the present day as belonging to a different school of thought to that considered in this chapter, and I place them amongst modern mathematicians. But I think that Fourier, Poisson, and the majority of their contemporaries are the lineal successors of Lagrange and Laplace. If this view is correct, it would seem that the latter members of the French school devoted themselves mainly to the application of mathematical analysis to physics. Before considering these mathematicians, I may mention the distinguished English experimental physicists who were their contemporaries and whose merits have only recently received an adequate recognition. Chief among these are Cavendish and Young. Cavendish. The Honourable Henry Cavendish, born at Nice on October 10, 1731, and died at London on February 24, 1810. His tastes for scientific research and mathematics were formed at Cambridge, where he resided from 1749 to 1753. He created experimental electricity and was one of the earliest writers to treat chemistry as an exact science. I mention him here on account of his experiment in 1798 to determine the density of the earth by estimating its attraction as compared with that of two given lead balls. The result is that the mean density of the earth is about 5.5 times that of water. This experiment was carried out in accordance with a suggestion which had been first made by John Mitchell, a fellow of Queen's College, Cambridge, who had died before he was able to carry it into effect. End of Part 32. Recording by Paul King, Oakville, Ontario. http pjk.scripts.mit.edu/pkj. Chapter 18, Part 4 of A Short Account of the History of Mathematics by W. W. Rouse Ball. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripts.mit.edu/pjk. A Short Account of the History of Mathematics by W. W. Rouse Ball.
Chapter 18. Leibniz and the Mathematicians of the First Half of the 18th Century, Part 4. Cavendish. The Honourable Henry Cavendish was born at Nice on October 10, 1731, and died in London on February 24, 1810. His tastes for scientific research and mathematics were formed at Cambridge, where he resided from 1749 to 1753. He created experimental electricity and was one of the earliest writers to treat chemistry as an exact science. I mention him here on account of his experiment in 1798 to determine the density of the earth by estimating its attraction as compared with that of two given lead balls. The result is that the mean density of the earth is about 5.5 times that of water. This experiment was carried out in accordance with a suggestion which had been first made by John Michell, a fellow of Queen's College, Cambridge, who had died before he was able to carry it into effect. Rumford. Sir Benjamin Thompson, Count Rumford, born at Concord on March 26, 1753, and died at Auteuil on August 21, 1815, was of English descent and fought on the side of the Loyalists in the American War of Secession. On the conclusion of peace he settled in England, but subsequently entered the service of Bavaria, where his military and civil powers of organization proved of great value. At a later period he again resided in England, and when there he founded the Royal Institution. The majority of his papers were communicated to the Royal Society of London. Of these the most important is his memoir, in which he shewed that heat and work are mutually convertible. Young. Among the most eminent physicists of his time was Thomas Young, who was born in Milverton on June 13, 1773, and died in London on May 10, 1829. He seems as a boy to have been somewhat of a prodigy, being well read in modern languages and literature as well as in science. He always kept up his literary tastes, and it was he who first furnished the key to decipher the Egyptian hieroglyphics. He was destined to be a doctor, and after attending lectures at Edinburgh and Göttingen, entered Emmanuel College, Cambridge, from which he took his degree in 1799, and to his stay at the university he attributed much of his future distinction. His medical career was not particularly successful, and his favourable maxim that a medical diagnosis is only a balance of probabilities was not appreciated by his patients, who looked for certainty in return for their fee. Fortunately, his private means were ample. Several papers contributed to various learned societies from 1798 onwards prove him to have been a mathematician of considerable power. But the researches which have immortalized his name are those by which he laid down the laws of interference of waves in light, and was thus able to suggest the means by which the chief difficulties in the way of acceptance of the undulatory theory of light could be overcome. Wollaston. Another experimental physicist of the same time and school was William Hyde Wollaston, who was born at Dereham on August 6, 1766, and died in London on December 22, 1828. He was educated at Caius College, Cambridge, of which society he was a fellow. Besides his well-known chemical experiments, he is celebrated for his researches on experimental optics and for the improvements which he effected in astronomical instruments. Dalton. Another distinguished writer of the same period was John Dalton, who was born in Cumberland on September 5, 1766, and died at Manchester on July 27, 1844. Dalton investigated the tension of vapours and the law of the expansion of a gas under changes of temperature. He also found the atomic theory in chemistry. It will be gathered from these notes that the English school of physicists at the beginning of this century were mostly concerned with the experimental side of the subject, but in fact no satisfactory theory could be formed without some similar careful determination of the facts.
The most eminent French physicists of the same time were Fourier, Poisson, Ampère, and Fresnel. Their method of treating the subject is more mathematical than that of their English contemporaries, and the two first named were distinguished for general mathematical ability. Fourier. The first of these French physicists was Jean-Baptiste Joseph Fourier, who was born at Auxerre on March 21, 1768, and died at Paris on May 16, 1830. He was the son of a tailor and was educated by the Benedictines. The commissions in the scientific corps of the army was, as still the case in Russia, reserved for those of good birth, and being thus ineligible, he accepted a military lectureship on mathematics. He took a prominent part in his own district in promoting the revolution, and was rewarded by an appointment in 1795 in the Normal School, and subsequently by a chair at the Polytechnic School. He went with Napoleon on his eastern expedition in 1798, and was made governor of Lower Egypt. Cut off from France by the English fleet, he organized the workshops on which the French army had to rely for their munitions of war. He also contributed several mathematical papers to the Egyptian Institute, which Napoleon founded at Cairo, with a view of weakening English influence in the East. After the British victories and the capitulation of the French under General Menon in 1801, he returned to France and was made prefect of Grenoble, and it was while there that he made his experiments on the propagation of heat. He moved to Paris in 1816. In 1822 he published his Théorie analytique de la chaleur, in which he bases his reasoning on Newton's law of cooling, namely that the flow of heat between two adjacent molecules is proportional to the infinitely small difference of their temperatures. He states that the theory demands that the temperatures of stellar space should be between -50 degrees Celsius and -60 degrees Celsius, a conclusion which it has been as yet impossible to prove or disprove. In this work he shews that any function of a variable, whether continuous or discontinuous, can be expanded in a series of sines of multiples of the variable, a result which is constantly used in modern analysis. Lagrange had given particular cases of the theorem and had implied that the method was general, but he had not pursued the subject. Fourier left an unfinished work on determinate equations, which was edited by Navier and published in 1831. This contains much original matter. In particular, there is a demonstration of Fourier's theorem on the position of the roots of an algebraic equation. Lagrange had shewn how the roots of an algebraical equation might be separated by means of another equation whose roots were the squares of the differences of the roots of the original equation. Boudin in 1807 and 1811 had enunciated the theorem generally known by the name of Fourier, but the demonstration was clumsy and not altogether satisfactory. Fourier's proof is the same as that usually given in textbooks on the theory of equations. The final solution of the problem was given in 1829 by Jacques-Charles-François Sturm.
Sadi Carnot. Among Fourier's contemporaries who were interested in the theory of heat, the most eminent was Sadi Carnot, son of the eminent geometrician mentioned previously. Sadi Carnot was born at Paris in 1796 and died there of cholera in August 1832. He was an officer in the French army. In 1824 he issued a short work entitled Réflexions sur les puissances motrices du feu, in which he attempted to determine in what way heat produced its mechanical effect. He made the mistake of assuming that heat was material, but his essay was the commencement of the modern theory of thermodynamics. Poisson. Siméon Denis Poisson, born at Pithiviers on June 21, 1781, and died at Paris on April 25, 1840, is almost equally distinguished for his application of mathematics to mechanics and to physics. His father had been a common soldier, and on his retirement was given some small administrative post in his native village. When the revolution broke out, he appears to have assumed the government of the place, and, being left undisturbed, became a person of some local importance. The boy was put out to nurse, and he used to tell how one day his father, coming to see him, found that the nurse had gone out on pleasure bent, while she had left him suspended by a small cord to a nail fixed in the wall. This, she explained, was a necessary precaution to prevent him from perishing under the teeth of the various animals and animalcula that roamed on the floor. Poussin used to add that his gymnastic efforts carried him incessantly from one side to the other, and it was thus in his tenderest infancy that he commenced those studies on the pendulum that were there to occupy so large a part of his mature age. He was educated by his father, and destined much against his will to be a doctor. His uncle offered to teach him the art, and began by making him prick the veins of cabbage leaves with a lancet. When perfect in this, he was allowed to put on blisters, but in almost the first case he did this by himself. The patient died in a few hours, and though all the medical practitioners of the place assured him that the event was a very common one, he vowed he would have nothing more to do with the profession. Returning home, he found amongst the official papers sent to his father a copy of the questions set at the Polytechnic school, and at once found his career. At the age of 17 he entered the Polytechnic, and his abilities excited the interest of Lagrange and Laplace, whose friendship he retained to the end of their lives. A memoir on finite differences, which he wrote when only 18, was reported on so favourably by Legendre that it was ordered to be published in the Recueil des Savants Étrangers. Directly he had finished the course, he was made a lecturer at the school, and he continued through his life to hold various government scientific posts and professorships. He was somewhat of a socialist, and remained a rigid republican till 1815, with a view to making another empire impossible. He joined the Legitimists. He took, however, no active part in politics, and made the study of mathematics his amusement as well as his business. His works and memoirs are between 300 and 400 in number. The chief treatises which he wrote were his Traité de mécanique, 2 volumes, 1811 and 1833, which was long, a standard work; his Théorie nouvelle de l'action capillaire in 1831, his Théorie mathématique de la chaleur in 1835, to which a supplement was added in 1837, and his Recherches sur la probabilité des jugements in 1837. He had intended, if he had lived, to write a work which should cover all mathematical physics, and in which these would have been incorporated. Of his memoirs on the subject of pure mathematics, the most important are those on definite integrals, and the Fourier's series. These are to be found on the Journal Polytechnique from 1813 to 1823, and in the Mémoires de l'Académie for 1823. Their application to physical problems constituting one of his chief claims to distinction, his essay on the calculus of variations, Mémoires de l'Académie, 1833, and his papers on the probability of the mean results of observations, Connaissance des temps, 1827, and following years. Most of his memoirs were published in the 3 periodicals here mentioned. Perhaps the most remarkable of his memoirs on applied mathematics are those on the theory of electrostatics and magnetism, which originated a new branch of mathematical physics. He supposed that the results were due to the attractions and repulsions of imponderable particles. The most important of those on physical astronomy are the 2 read in 1806, printed in 1809, on the secular inequalities of the mean motions of the planets, and on the variations of arbitrary constants introduced into the solutions of questions on mechanics. In those, Poisson discusses the question of the stability of the planetary orbits, which Legendre had already proved to the first degree of approximation for the distributing forces, and shews that the result can be extended to the third order of small quantities. These were the memoirs which led to Lagrange's famous memoir of 1808. Poisson also published a paper in 1821 on the libration of the moon, and another in 1827 on the motion of the earth about its centre of gravity. His most important memoirs on the theory of attraction are one in 1829 on the attraction of spheroids, and another in 1835 on the attraction of a homogeneous ellipsoid. The substitution of the correct equation involving the potential, namely grad squared v equals -4 pi rho, for Laplace's form of it, pi squared v equals 0, was first published in 1813 in the Bulletin des Sciences of the Société Philomatique. Lastly, I may mention his memoir in 1825 on the theory of waves.
Ampère. André-Marie Ampère was born at Lyon in January 22, 1775, and died at Marseille on June 10, 1836. He was widely read in all branches of learning and lectured and wrote on many of them, but after the year 1809, when he was made professor of analysis at the Polytechnic School in Paris, he confined himself almost entirely to mathematics and science. His papers on the connection between electricity and magnetism were written in 1820. According to his theory, propounded in 1826, a molecule of matter which can be magnetized is traversed by a cloud of electric current, and a magnetization is produced by any cause which makes the direction of these currents in the different molecules of the body approach parallelism. Fresnel. Augustin Jean Fresnel, born at Broglie on May 10, 1788, and died at Ville d'Avray on July 14, 1827, was a civil engineer by profession, but he devoted his leisure to the study of physical optics. The undulatory theory of light, which Hooke, Huygens, and Euler had supported on a priori grounds, had been based on experiment by the researches of Young. Fresnel deduced the mathematical consequences of these experiments and explained the phenomenon of the interference of both ordinary and polarized light. Biot. Fresnel's friend and contemporary Jean-Baptiste Biot, who was born at Paris on April 21, 1774, and died there in 1862, requires a word or two in passing. Most of his mathematical work was in connection with the subject of optics, and especially with the polarization of light. His systematic works were produced within the years 1805 and 1817. A selection of his more valuable memoirs was published in Paris in 1858. Arago. François-Jean Dominique Arago was born at Estangel in the Pyrenees on February 26, 1786, and died in Paris on October 2, 1853. He was educated at the Polytechnic School, Paris, and we gather from his autobiography that however distinguished were the professors of that institution, they were remarkably incapable of imparting their knowledge or maintaining discipline. In 1804 he was made secretary to the observatory, and then from 1806 to 1809 he was engaged in measuring a meridian arc in order to determine the exact length of a meter. He was then made one of the astronomers at Paris, given a residence there, and made a professor at the Polytechnic School, where he enjoyed a marked success as a lecturer. He subsequently gave popular lectures on astronomy, which were both lucid and accurate, a combination of qualities which was rarer then than now. He reorganized the National Observatory, the management of which had long been inefficient, but in doing this he shewed himself dictatorial and passionate, and the same defects of character revealed themselves in many of the events of his life. He remained to the end a consistent republican, and after the coup d'état of 1852, though half blind and dying, he resigned his post as an astronomer rather than take the oath of allegiance. It is to the credit of Napoleon III that he gave directions that the old man should be in no way disturbed, and that he should be left free to say and do what he liked. His earliest physical researches were on the pressure of steam at different temperatures and the velocity of sound (1818 to 1822). His magnetic observations mostly took place from 1823 to 1826. He discovered what had been called rotary magnetism, and the fact that most bodies could be magnetized. These discoveries were completed and explained by Faraday. He warmly supported Fresnel's optical theories, and the two philosophers conducted together those experiments on the polarization of light which led to the inference that the vibrations of the luminiferous ether were transverse to the direction of motion, and that the polarization consisted in a resolution of rectilinear motion into components at right angles to each other. The subsequent invention of the polariscope and the discovery of rotatory polarization are due to Arago. The general idea of the experimental determination of the velocity of light in the manner subsequently effected by Fizeau and Foucault was suggested by him in 1838, but his failing eyesight prevented his arranging the details or making the experiments. It will be noticed that some of the last members of the French school were alive at a comparatively recent date, but nearly all mathematical work was done before the year 1830. They are the direct successors of the French writers who flourished at the commencement of this century, and seem to have been out of touch with the great German mathematicians of the early part of it, on whose researches much of the best work of this century is based. They are thus placed here, though their writings are in some cases of a later date than those of Gauss, Abel, Jacobi, and other mathematicians of recent times. The introduction of analysis into England. The complete isolation of the English school and its devotion to geometrical methods are the most marked features in its history during the latter half of the 18th century, and the absence of any considerable and valuable contributions to the advancement of mathematical science was a natural consequence. One result of this was that the energy of the English men of science was largely devoted to practical physics and practical astronomy, which were in consequence studied in Britain perhaps more than elsewhere. Almost the only English mathematician at the beginning of this century who used analytical methods and whose work requires mention here is Ivory, to whom the celebrated theorem of attractions is due. James Ivory was born in Dundee in 1765 and died at Douglastown on September 21, 1845. After graduating at St Andrews, he became the managing partner in a flax spinning company in Forfarshire, but continued to devote most of his leisure to mathematics. In 1804 he was made professor at the Royal Military College at Marlow, which is now moved to Sandhurst. He contributed numerous papers to the Philosophical Transactions, the most remarkable being those on attractions. In one of these, in 1809, he shewed how the attraction of a homogeneous ellipsoid on an external point is a multiple of that of another ellipsoid on an internal point. The latter can be easily obtained. He criticized Laplace's solution of the method of least squares with unnecessary bitterness, and in terms which proved his incompetence to understand it. The Cambridge Analytical School. Toward the close of the last century, the more thoughtful members of the Cambridge School of Mathematics began to recognize that their isolation from the continental contemporaries was a serious evil. The earliest attempt in England to explain the notation and methods of the calculus as used on the continent was due to Woodhouse, who stands out as the apostle of the new movement. It is doubtful if he could have brought the analytical methods into vogue by himself, but his views were enthusiastically adopted by three undergraduates, Babbage, Peacock, and Herschel, who succeeded in carrying out reforms that he had suggested. In a book which will fall into the hands of few but English readers, I may be pardoned for making space for a few remarks on these four mathematicians. The original stimulus came from French sources, and I therefore place these remarks at the close of my account of the French school. But I should add that the English mathematicians of this century at once struck out a line independent of their French contemporaries. Woodhouse. Robert Woodhouse was born at Norwich on April 28, 1773, was educated at Caius College, Cambridge, of which society he was subsequently a fellow, was Plumian Professor in the university, and continued to live at Cambridge till his death on December 23, 1827. His earliest work, entitled The Principles of Analytical Calculation, was published at Cambridge in 1803. In this he explained the differential notation and strongly pressed the employment of it, but he severely criticized the methods used by continental writers and their constant assumption of non-evident principles. This was followed in 1809 by a trigonometry, plane and spherical, and in 1810 by a historical treatise on the calculus of variations and isoperimetrical problems. He next produced an astronomy, the first volume, usually bound in two, on practical and descriptive astronomy, being issued in 1812, the second volume, containing an account of the treatment of physical astronomy by Laplace and other continental writers, being issued in 1818. All these works deal critically with the scientific foundation of the subjects considered, a point which is not unfrequently neglected in modern textbooks. A man like Woodhouse, of scrupulous honour, universally respected, a trained logician, and with a caustic wit, was well fitted to introduce a new system. And the fact that when he first called attention to the continental analysis, he exposed the unsoundness of some of the usual methods of establishing it, more like an opponent than a partisan, and was politic as it was honest. Woodhouse did not exercise much influence on the majority of his contemporaries, and the movement might have died away for the time being had it not been for the advocacy of Peacock, Herschel, and Babbage, who formed an analytical society with the object of advocating the general use in the university of analytical methods and of the differential notation. Peacock. George Peacock, who was the most influential of the early members of the new school, was born at Denton on April 9, 1791. He was educated at Trinity College, Cambridge, of which society he was subsequently a fellow and tutor. The establishment of the University Observatory was mainly due to his efforts, and in 1836 he was appointed to the Lowndean Professorship of Astronomy and Geometry. In 1839 he was made Dean of Ely, and resided there until his death on November 8, 1858. Although Peacock's influence on English mathematicians was considerable, he has left but few memorials to his work. But I may note that his report on recent progress and analysis 1833 commenced those valuable summaries of scientific progress which enrich many of the annual volumes of the Transactions of the British Association. Babbage. Another important member of the Analytical Society was Charles Babbage, who was born at Totnes in December 26, 1792. He entered Trinity College, Cambridge in 1810, subsequently became Lucasian Professor in the university, and died in London on October 18, 1871. It was he who gave the name to the Analytical Society, which he stated was formed to advocate the principles of pure deism as opposed to the dotage of the university. In 1820 the Astronomical Society was founded mainly through his efforts, and at a later time, 1830 to 1832, he took a prominent part in the foundation of the British Association. He will be remembered for his mathematical memoirs on the calculus of functions, and in the invention of analytical machines, which could not only perform ordinary processes of arithmetic, but could tabulate the values of any functions and print the results. Herschel. The third of those who helped bring analytical methods into general use in England was the son of Sir William Herschel, 1738 to 1822. The most illustrious astronomer of the latter half of the last century, and the creator, it may be fairly said, of stellar astronomy. Sir John Frederick William Herschel was born on March 7th, 1792, and educated at St. John's College, Cambridge, and died on May 11th, 1871. His earliest original work was a paper on Coates's theorem, and it was followed by others on mathematical analysis, but his desire to complete his father's work led ultimately to his taking up astronomy. His papers on light and astronomy contain a clear exposition of the principles which underlie the mathematical treatment of those subjects. In 1813 the Analytical Society published a volume of memoirs, of which the preface and the first paper on continued products are due to Babbage, and 3 years later they issued a translation of Lacroix' Traité des élémentaires du calcul différentiel et du calcul intégral. In 1817 and again in 1819 the differential notation was used in the university examinations, and after 1820 its use was well established. The Analytical Society followed up this rapid victory by the issue in 1820 of 2 volumes of examples illustrative of the new method, one by Peacock on the differential and integral calculus, and the other by Herschel on the calculus of finite differences. Since then, English works on the infinitesimal calculus have abandoned the exclusive use of the fluxional notation. It should be noticed in passing that Lagrange and Laplace, like the majority of other modern writers, employ both the fluxional and the differential notation. It was the exclusive adoption of the former that was so hampering. Amongst those who materially assisted in extending the use of the new analysis were William Whewell, 1794 to 1866, and George Bedell Airy, 1801 to 1892, both fellows at Trinity College, Cambridge. The former issued in 1819 a work on mechanics, and the latter, who was a pupil of Peacock, published in 1826 in his tracts, in which the new method was applied with great success to various physical problems. The efforts of the Society were supplemented by the rapid publication of good textbooks in which analysis was freely used. The employment of analytical methods spread from Cambridge over the rest of Britain, and by 1830 those methods have come into general use there. End of section 32. Recording by Paul King, Mississauga, Ontario. http pjk.scripts.mit.edu/pkj. Chapter 19, Part 1 of A Short Account of the History of Mathematics by W. W. Rouse Ball. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripts.mit.edu/pkj. A Short Account of the History of Mathematics by W. W. Rouse Ball, Chapter 19, Mathematicians of Recent Times. It is evidently impossible for me to discuss adequately the mathematicians of the age in which we live, especially as I purposefully exclude from this work and any detailed reference to living writers. I make therefore no attempt to give a complete history of this period, but as a sort of appendix to their preceding chapters I add a few notes on some of the more striking features in the history during this century of pure mathematics, in which I include theoretical dynamics and astronomy. But except for a few allusions, I shall not discuss the applications of mathematics to physics. These notes are brief, and in many cases consist merely of a list of the names of some of those to whom the development of any branch of the subject is chiefly due, and an indication of that part of it to which they have directed most attention.
I would refer anyone who wishes for more details to the invaluable catalogue which has been compiled by the Royal Society of London, and which contains a list under the names of the authors of all the scientific papers contributed during this century to journals and learned societies. In only a few cases do I add any account of the life and works of the mathematicians mentioned. Even with these limitations, it has been very difficult to put together a connected account of the mathematicians of recent times, and I wish to repeat explicitly that I do not suggest, nor do I wish my readers to suppose, that my notes on a subject give the names of all the chief writers who have studied it. In fact, the quality of matter produced has been so enormous that no one can expect to do more than make himself acquainted with the work in some small department. As an illustration of this remark, I must say that I have reason to believe that something like 15,000 separate scientific memoirs are now published every year by the different societies and journals of Europe and America. Most of the treatises on the history of mathematics omit all references to the work produced during this century. The chief exceptions which I am acquainted are a short dissertation by H. Hankel entitled Die Entwicklung der Mathematik in den letzten Jahrhunderten in Tübingen, 1885, the 11th and 12th volumes of Marie's Histoire des Sciences, in which there are notes on mathematicians who were born in the last century, Gerhardt's Geschichte der Mathematik in Deutschland, published in Munich, 1877, and a discours on the professors at the Sorbonne by Hermite in the Bulletin des Sciences Mathématiques in 1890, pages 6 to 36. A few histories of the development of a particular subjects have been written, such as those by the late Isaac Todd Hunter on the theories of attraction and the calculus of probabilities, while annual volumes of the British Association contain a number of reports on the progress in several different branches of modern mathematics. A few similar reports, and notably one in 1857 by J. Bertrand on the development of mathematical analysis, have been presented by the French Academy. I have found these authorities and these reports useful, but I have derived most assistance in writing this chapter from the obituary notices in the proceedings of various learned societies, foreign as well as British. I am also indebted to information kindly furnished me by various friends, and if I do not further dwell on this, it is only that I would not seem to make them responsible for errors and omissions which they would have avoided in their own works. A period of exceptional intellectual activity in any subject is usually followed by one of comparative stagnation, and after the deaths of Lagrange, Laplace, Legendre, and Poisson of the French school, which had occupied so prominent a position at the beginning of this century, ceased for some years to produce much new work. Some of the mathematicians whom I intend first to mention, Gauss, Abel, and Jacobi, were contemporaries of the later years of the French mathematicians just named, but their writings appear to me to belong to a different school, and thus are properly placed at the beginning of a fresh chapter. There is no mathematician of this century whose writings have had a greater effect than those of Gauss. Nor is it on only one branch of the science that his influence has left a permanent mark. I cannot therefore commence my account of the mathematicians of recent times better than by describing very briefly his more important researches. Gauss. Carl Friedrich Gauss, born at Brunswick on April 23, 1777, and died in Göttingen on February 23, 1855. His father was a bricklayer, and Gauss was indebted for liberal education, much against the will of his parents, who wished to profit by his wages as a labourer, to the notice which his talents procured from the reigning duke. In 1792 he was sent to the Caroline College, and by 1795 professors and pupils alike admitted that he knew all of the former could teach him. It was while there that he investigated the method of least squares, and proved by induction the law of quadratic reciprocity. Thence he went to Göttingen, where he studied under Kastner.
Many of his discoveries in the theory of numbers were made while a student there. In 1798 he returned to Brunswick, where he earned a somewhat precarious livelihood by private tuition. In 1799 Gauss published his demonstration that every algebraical equation has a root of the form a plus bi, a theorem of which altogether he gave three distinct proofs. In 1801 this was followed by Disquisitiones Arithmeticae, which is printed as the first volume of his collected works. The greater part of it has been sent to the French Academy in the preceding year, and has been rejected with a sneer, which, even if the book had been as worthless as the referees believed, would have been unjustifiable. Gauss was deeply hurt, and his reluctance to publish his investigations may be partly attributable to this unfortunate incident. The next discovery Gauss was in a totally different department of mathematics. The absence of any planet in the space between Mars and Jupiter, where Bode's law would have led observers to expect one, had been long remarked, but it was not until 1801 that any one of the numerous group of minor planets which occupy that space was observed. The discovery was made by Piazzi of Palermo, and was the more interesting as its announcement occurred simultaneously with a publication by Hegel in which he severely criticized astronomers for not paying more attention to philosophy, a science, said he, which would not at once have shewn them that there could not possibly be more than 7 planets, a study of which would therefore have prevented an absurd waste of time in looking for what in the nature of things could never be found. The new planet was named Ceres, but it was seen under conditions which appeared to render it almost impossible to forecast its orbit. The observations were fortunately communicated to Gauss. He calculated its elements, and his analysis proved to him to be the first of theoretical astronomers no less than the greatest of arithmeticians. The attention excited by these investigations procured him in 1807 the offer of a chair at St. Petersburg, which he declined. In the same year he was appointed director to Göttingen Observatory and professor of astronomy there. These offices he retained to his death, and after his appointment he never slept away from his observatory except on one occasion where he attended a scientific conference at Berlin. His lectures were singularly lucid and perfect in form, and it is said that he used here to give the analysis by which he had arrived at his various results, and which it is so conspicuously absent from his published demonstrations, but for fear his auditors should lose the thread of his discourse, he never willingly permitted them to take notes. I have already mentioned Gauss's publications in 1799, 1801, and 1802. For some years after 1807 his time was almost wholly occupied by work connected with his observatory. In 1809 he published at Hamburg his Theoria Motus Corporum Celestium, a treatise which contributed largely to the improvement of practical astronomy and introduced the principle of curvilinear triangulation, and on the same subject, but connected with observations in general, we have his memoir Theoria Combinatoris Observationum Aerobinus Minimus Obnoxia, with a second part and a supplement. Somewhat later he took up the subjects of geodesy, acting from 1821 to 1848 as scientific advisor to the Danish and Hanoverian governments for the survey then in progress. His papers of 1843 and 1866, Über Gegenstände der hohen Geodäsie, contain his researches on the subject. Gauss's researches on electricity and magnetism date from about the year 1830. His first paper on the theory of magnetism, entitled Intensitas vis magnetica terrestris ad mensurem absolutum revocata, was published in 1833. A few months afterwards he, together with Weber, invented the declination instrument and the bifilar magnetometer, in the same year that they erected at Göttingen a magnetic observatory free from iron, as Humboldt and Arago had previously done on a smaller scale. where they made magnetic observations and in particular shewed that it was possible and predictable to send telegraph signals. In connection with this observatory, Gauss founded the association called the Magnetische Verein with the object of securing continuous observations at fixed times. The volumes of their publications Resultate aus der Beobachtungen des magnetischen Vereins for 1838 and 1839 contain two important memoirs by Gauss, one on the general theory of earth magnetism and on the other on the theory of forces attracting according to the inverse square of the distance. Like Poisson, he treated the phenomenon in electrostatics as due to attractions and repulsions between imponderable particles. In electrodynamics he arrived in 1835 at a result equivalent to that given by W. E. Weber in 1846, namely that the attraction between two electrified particles E and E', whose distance apart is r, depends on their relative motion and position according to the formula E r to the power of minus 2 multiplied by the quantity 1 plus r umlaut minus 1/2 r squared quantity squared times c to the minus 2. Gauss, however, held that no hypothesis was satisfactory which rested on a formula and was not a consequence of a physical conjecture, and as he could not frame a plausible physical conjecture, he abandoned the subject. Such conjectures were proposed by Riemann in 1858 and by C. Newman and E. Betti in 1868. But Helmholtz in 1870, 1873, and 1874 shewed that they were untenable. A simpler view, which regards all electric and magnetic phenomena as stresses and motions of a material elastic medium, have been outlined by Michael Faraday and was elaborated by James Clerk Maxwell. The latter, by the use of generalized coordinates, was able to deduce the consequences, and the agreement with experiment is close. These and other electric theories were classified and critically discussed in a memoir by J. J. Thomson in 1885. Gauss's researches on optics, including systems of lenses, were published in 1840 in his Dioptrische Untersuchungen. From this sketch it will be seen that the ground covered by Gauss's researches was extraordinarily wide. I will now mention very briefly some of his most important discoveries in pure mathematics. His most celebrated work in pure mathematics is De Disquisitiones Arithmeticae, which has proved the starting point for several interesting investigations on the theory of numbers. This treatise and Legendre's Théorie des Nombres remains standard works on the theory of numbers. But, just as in his discussion of elliptic functions, Legendre failed to rise to the conception of a new subject, and confused himself to regarding their theory as a chapter in the integral calculus, so he treated the theory of numbers as a chapter in algebra. Gauss, however, realized that the theory of discrete magnitudes or higher arithmetic was of a different kind from that of continuous magnitudes or algebra, and he introduced a new notation and new methods of analysis, of which subsequent writers have generally availed themselves. In particular, the Disquisitiones Arithmeticae introduced the modern theory of congruences of the first and second orders, and to this Gauss reduced intermediate analysis. In it also he discussed the solution of binomial equations of the form x to the power n equals 1. This involves the celebrated theorem that the only regular polygons which can be constructed by elementary geometry are those in which the number of sides is 2 to the power of m multiplied by 2 to the power of n plus 1, where m and n are integers and 2 to the power n plus 1 is a prime, a discovery he had made in 1796. He developed the theory of ternary quadratic forms involving two indeterminates. He also investigated the theory of determinants, and it was on Gauss's results that Jacobi based his researches on that subject. The theory of functions of double periodicity had its origin in the discoveries of Abel and Jacobi, which I describe later. Both these mathematicians arrived at the theta functions which play so large a part in the theory of the subject. Gauss, however, had independently, and indeed at a far earlier date, discovered these functions and their chief properties, having been led to them by certain integrals which occurred in the determinatio attractionis, to evaluate which he invented the transformation now associated with the name of Jacobi. Though Gauss at a later time communicated the fact to Jacobi, he did not publish his researches. They occur in a series of notebooks of a date not later than 1808 and are included in his collected works. Of the remaining memoirs in pure mathematics, the most remarkable are those on the theory of biquadratic residues, wherein the notion of complex numbers of the form a plus bi was first introduced into the theory of numbers, in which are included several tables, and notably one of the number of the classes of binary quadratic forms, that of relating to the proof of the theorem that every numerical equation has a real or imaginary root, that on the summation of series, that on the hypergeometric series, which contains a discussion of the gamma function, and lastly one on interpolation. His introduction of rigorous tests for the convergency of infinite series is especially noticeable. Finally, we have the important memoir on the conformal representation of one surface upon another, in which the results given by Lagrange for surfaces of revolution are generalized for any surfaces. In the theory of attractions, we have a paper on the attraction of homogeneous ellipsoids. The already mentioned memoir of 1839, Allgemeine Lesssatz in Beziehung auf die inverkehrten Verhältnis des Quadrats der Entfernung, on the theory of forces attracting according to the inverse square of the distance, and the memoir Determinatio Attractionis, in which it is shewn that the secular variations which the elements of the orbit of a planet experience from the attraction of another planet which disturbs it are the same as if the mass of the disturbing planet were distributed over its orbit into an elliptic ring in such a manner that equal masses of the ring would correspond to the arcs of the orbit described in equal times. The great masters of modern analysis are Lagrange, Laplace, and Gauss, who were contemporaries. It is interesting to note the marked contrast in their styles. Lagrange is perfect both in form and matter. He is careful to explain his procedure, and though his arguments are general, they are easy to follow. Laplace, on the other hand, explains nothing, is absolutely indifferent to style, and if satisfied with that his results are correct, is content to leave them either with no proof or with a faulty one. Gauss is as exact and elegant as Lagrange, but even more difficult to follow than Laplace, for he removes every trace of the analysis by which he reached his results, and studies to give a proof which, while rigorous, shall be as concise and synthetical as possible. End of part 34. Recording by Paul King, Mississauga. http pjk.scripts.mit.edu/pkj. Chapter 19, Part 2 of A Short Account of the History of Mathematics by W. W. Rouse Ball. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripts.mit.edu/pkj. A Short Account of the History of Mathematics by W. W. Rouse Ball. Chapter 19, Mathematics of Recent Times, Part 2. Dirichlet. One of Gauss's pupils to whom I may here allude is Lejeune Dirichlet, who is generally known for his exposition of the discoveries of Jacobi, who was his father-in-law, and of Gauss, rather than for his own original investigations, valuable though some of these are. Peter Gustave Lejeune Dirichlet was born at Rennes on February 13, 1805, and died at Göttingen on May 5, 1859. He held successively professorships at Breslau and Berlin, and on Gauss's death in 1855 was appointed to succeed him as professor of the higher mathematics at Göttingen. He intended to finish Gauss's incomplete works, for which he was admirably fitted, but his early death prevented this. He produced, however, several memoirs which have considerably facilitated the comprehension of some of Gauss's more abstruse methods. Of Diraclet's original work, the most celebrated is that on the determination of means with applications to the distribution of prime numbers. The researches of Gauss on the theory of numbers were continued or supplemented by Jacobi, who first proved the law of cubic reciprocity, discussed on the theory of residues, and in his Canon Arithmeticus gave a table of residues of prime roots. Eisenstein. This subject was next taken up by Ferdinand Gotthold Eisenstein, a professor at the University of Berlin, who was born at Berlin on April 16, 1823, and died there on October 11, 1852. The theory of numbers may be divided into two main divisions, namely, the theory of congruences and the theory of forms. The solution of the problem of the representation of numbers by binary quadratic forms is one of the great achievements of Gauss, and the fundamental principles upon which the treatment of such questions rest were given by him in the Disquisitiones Arithmeticae. Gauss there added some results relating to ternary quadratic forms, but the general extension from 2 to 3 indeterminates was the work of Eisenstein, who in his memoir Neue Theorem der höheren Arithmetik defined the ordinal and generic characters of ternary quadratic forms of an uneven determinant, and in the case of definite forms assigned the weight of any order or genus, but he did not consider forms of an even determinant, nor give any demonstration of his work. Eisenstein also considered the theorems relating to the possibility of representing a number as a sum of squares, and shewed that the general theorem was limited to 8 squares. The solutions in the cases of 2, 4, and 6 squares may be obtained by means of elliptic functions, but the cases in which the numbers of squares is uneven involve the special processes peculiar to the theory of numbers. Eisenstein gave the solution in the case of 3 squares. He also left a statement of the solution he had obtained in the case of 5 squares, but his results were published without proofs and apply only to numbers which are not divisible by a square. Among Eisenstein's other investigations I single out for special mention the remarkable rule he enunciated by means of which it is possible to distinguish whether a given series represents an algebraical or transcendental function. Henry Smith. One of the most original and powerful mathematicians of the school founded by Gauss was Henry Smith. Henry John Stephen Smith was born in London on November 2, 1826, and died at Oxford on February 9, 1883. He was educated at Rugby and at Balliol College, Oxford, of which latter society he was a fellow, and in 1861 he was elected Savilian Professor of Geometry at Oxford, where he resided till his death. The subject in connection with which Smith's name will be always specially remembered is the theory of numbers, and to this he devoted the years from 1854 to 1864. The results of his historical researches were given in his report published in parts in the Transactions of the British Association from 1859 to 1865. This report contains an account of what had been done on the subject to that time, together with some additional matter. The chief outcome of his own original work on the subjects is included in 2 memoirs printed in the Philosophical Transactions for 1861 and 1867, the first being on linear indeterminate equations and congruences, and the second on the orders and genera of ternary quadratic forms. In the latter memoir, demonstrations of Eisenstein's results and their extension to ternary quadratic forms of an even determinant were supplied, and a complete classification of ternary quadratic forms was given. Smith, however, did not confine himself to the case of three indeterminates, but succeeded in establishing the principles on which the extension to the general case of n indeterminates depends, and obtained the general formulae, thus effecting the greatest advance made in the subject since the publication of Gauss's work. In the account of his methods and results which appeared in the Proceedings of the Royal Society, Smith remarked that the theorems relating to the representation of numbers by four squares and other simple quadratic forms are deducible by a uniform method from the principles there indicated, as also are the theorems relating to the representation of numbers by 6 and 8 squares. He then proceeded to say that as the series of theorems relating to the representation of numbers by sums of squares ceases, for the reason assigned by Eisenstein, when the number of squares surpasses 8, it was desirable to complete it. The results for even squares were known. The principal theorems relating to the case of 5 squares had been given by Eisenstein, but he had considered only those numbers which are not divisible by a square, and he had not considered the case of 7 squares. Smith here completed the enunciation of the theorems for the case of 5 squares, and added the corresponding theorems for the case of 7 squares. This paper was the occasion of a dramatic incident in the history of mathematics. 14 years later, in ignorance of Smith's work, the demonstration and completion of Eisenstein's theorems for 5 squares were set by the French Academy as a subject of their Grand Prix des Sciences Mathématiques. Smith wrote out the demonstration of his general theorems so far as was required to prove the results in the special case of 5 squares, and only a month after his death in March 1883 the prize was awarded to him, another prize being awarded to H. Minkowski of Bonn. No episode could bring out in a more striking light the extent of Smith's researches than that a question of which he had given in the solution in 1867 as a corollary from the general formulae which governed the whole class of investigations to which it belonged, should have been regarded by the French Academy as one whose solution which is of such difficulty and importance as to be worthy of their great prize. It has also been a matter of comment that they should have known so little of contemporary English and German researches on the subject as to be unaware that the result of the problem they were proposing was then lying in their own library. Among Smith's other investigations I may specially mention his geometrical memoir Sur calcul problème cubique et biquadratique, for which in 1868 he was awarded the Steiner Prize of the Berlin Academy. In a paper which he contributed to the Atti of the Accademia dei Lincei for 1877, he established a very remarkable analytical relation connecting the modular equation of order n and the theory of binary quadratic forms belonging to the positive determinant n. In this paper, the modular curve is represented analytically by a curve in such a manner as to present an actual geometrical image of the complete systems of the reduced quadratic forms belonging to the determinant, and a geometrical interpretation is given to the ideas of class, equivalence, and reduced form. He was also the author of important papers in which he succeeded in extending to complex quadratic forms many of Gauss's investigations relating to real quadratic forms. He was led by researches on the theory of numbers to the theory of elliptic functions, and the results he arrived at, especially on the theory of the theta and omega functions, are of importance. The theory of numbers as treated today may be said to originate with Gauss. I have already mentioned very briefly the subject of the subsequent investigations of Jacobi, Dirichlet, Eisenstein, and Henry Smith. Among other mathematicians who have written on it I may allude to the following: Riemann, who investigated the distribution of primes; James Joseph Sylvester, Savilian professor in the University of Oxford, born in London on September 3, 1814, who has also written on the distribution of primes; Cauchy, who in particular discussed the expression of quadratic binomials; Joseph Liouville, the editor from 1836 to 1874 of the well-known journal, who was born at Saint-Omer on March 24, 1809, and died in 1882, most of whose numerous investigations dealt with the representation of numbers by special forms. Ernest Edward Kummer, born at Soreau on January 29, 1810, and until recently professor at Berlin, to whom we owe the conception of the so-called ideal primes, which are required in the treatment of complexes, and which he applied to the problem of Fermat's equation, and whose paper on hypergeometric series may rank with that by Gauss as a classical memoir on the subject. Leopold Kronecker, professor in Berlin, born at Liegnitz on December 7, 1823, and died at Berlin on December 29, 1891, most of whose investigations on this branch of mathematics were on ternary and quadratic forms. On his investigations generally see the Bulletin of the New York Mathematical Society, Volume 1, pages 173 to 184. See also below, page 469. Charles Hermite, professor in Paris, born in Lorraine on December 24, 1822, who wrote on ternary forms. Julius Wilhelm Richard Dedekind, born at Brunswick on October 6, 1831, whose more important researches, given in an appendix to his edition of Dirichlet's writings, are on ideal primes. See also below, page 493. Panutij Chebyshev, formerly professor at the University of St. Petersburg, born in Russia in 1821, who has written on the number of primes between given limits, a problem also considered by Legendre, Dirichlet, and Riemann. And James Whitebread Lee Glacier, a fellow and tutor of Trinity College in Cambridge, born at Lewisham on November 5, 1848, from whose numerous papers I may single out those relating to prime numbers, those on functions of a number which are formed from its real or complex divisors, and on those on the possible divisors of numbers of a given form. Finally, I may mention that the problem of the partition of numbers, to which Euler paid considerable attention, has in recent times attracted the attention of Arthur Cayley, Sadlerian professor in the University of Cambridge, born in Richmond, Surrey, on August 16, 1821, of Sylvester, and of Percy Alexander MacMahon, professor at Woolwich, and a major in the English artillery, born at Malta on September 26, 1854. Interest in problems connected with the theory of numbers seems recently to have flagged, and possibly it may be found hereafter that the subject is approached better on other lines. The theory of functions of double and multiple periodicity is another subject to which much attention has been paid during this century. I have already mentioned that as early as 1808 Gauss had discovered the theta functions and their chief properties, but his investigations remained for many years concealed in notebooks, and it was to the researches made between 1820 and 1830 by Abel and Jacobi that the modern development of the subject is due. The treatment of it has been completely superseded that used by Legendre, and they are justly reckoned as the creators of this branch of mathematics. Abel. Niels Henrik Abel, born at Findo in Norway on August 5, 1802, and died at Arendal on April 6, 1829, at the age of 26. His memoirs on elliptic functions, which were originally published in Krell's journal, treat the subject from the point of view of the theory of equations and algebraic forms, a treatment to which his research has naturally led him. The important and very general result, known as Abel's theorem, which was subsequently applied by Riemann to the theory of transcendental functions, was sent to the French Academy in 1828, but, mainly through the action of Cauchy, was not published for several years. The name of Abelian function has been given to the higher transcendents of multiple periodicity, which were first discussed by Abel. He criticized the use of infinite series, but I do not know that the results lead to any definite rules for testing convergency. As illustrating his fertility of ideas, I may in passing notice his celebrated demonstration that it is impossible to solve a quintic equation by means of radicals. This theorem was the more important since it definitely limited a field of mathematics which had previously attracted numerous writers. I should add that this theorem had been enunciated as early as 1798 by Paolo Ruffini, an Italian physician practicing at Modena, but I believe that the proof he gave was deficient in generality. Jacobi. Carl Gustav Jacob Jacobi, born of Jewish parents at Potsdam on December 10, 1804, and died at Berlin on February 18, 1851, was educated at the University of Berlin, where he obtained the degree of Doctor of Philosophy in 1825. In 1827 he became extraordinary professor of mathematics at Königsberg, and in 1829 was promoted to be an ordinary professor. This chair he occupied till 1842, when the Prussian government gave him a pension, and he moved to Berlin, where he continued to live until his death in 1851. Jacobi's most celebrated investigations are those on elliptic functions, the modern notation in which is due to him, and the theory of which he established simultaneously with Abel, but independently of him. These are given in his treatise Fundamenta Nova Theoreae Functionum Ellipticarum, Königsberg, 1829, and in some later papers in Crell's journal. The correspondence between Legendre and Jacobi on elliptic functions has been reprinted in the first volume of Jacobi's collected works. Jacobi, like Abel, recognized that elliptic functions were not merely a group of theorems on integration, but that they were types of a new kind of function, namely one of double periodicity. Hence he paid particular attention to the theory of the theta function. The following passage in which he explains this view is sufficiently interesting to deserve textual reproduction. Equo cum universam que fingi potest, amplicatur periodaticatam analyticam elucet, functiones ellipticas non alis ad numerari deber transcendentibus, que quibusdem godent elegantis fortas pluribus, illas aut melioribus, sed speciem quadnam is ines perfecti et absoluti. Among Jacobi's other investigations I may specially single out his papers on determinants, which did a great deal to bring them into general use, and particularly his invention of the Jacobian, that is, of the functional determinant formed by the n-squared partial differential coefficients of the first order of n, given functions of n independent variables. I ought also to mention his papers on abelian transcendents, his investigations on the theory of numbers, his important work on the theory of partial differential equations, his development of the calculus of variations, and his numerous memoirs on the planetary theory and other particular dynamical problems, in the course of which he also extended the theory of differential equations. Most of the results of the researches last named are included in his Vorlesungen über Dynamik, edited by Klebsch, Berlin, 1866. Riemann. Georg Friedrich Bernhard Riemann was born at Bersens on September 17, 1826, and died at Selaska on July 20, 1866. He studied at Göttingen under Gauss, and subsequently at Berlin under Jacobi, Dirichlet, Steiner, and Eisenstein, all of whom were professors there at the same time. His earliest paper, written in 1850, was on algebraic functions of a complex variable, and on it the recent investigations of Schwarz, Klein, and Poincaré are largely based. To those I refer very briefly below. In 1854 Riemann wrote his celebrated memoir on the hypotheses on which geometry is founded. This was succeeded by his memoirs on elliptic functions and the theory of numbers. He also wrote on physical subjects. The question of the truth of the assumptions usually made in our geometry had been considered by J. Sacheri as long ago as 1733, and in more recent times had been discussed by Nikolai Ivanovich Lobachevsky, professor at Caen, born at Nizhny Novgorod in 1793 and died at Kazan on February 12, 1856, in 1826 and again in 1840. By Gauss in 1831 and in 1846, and by Johann Bolyai, born at Klausenburg in 1802 and died at Maros Vasarhelyi in 1860 and in 1832 in the appendix to the first volume of his father's Tentamen, but Riemann's memoir of 1854 attracted general attention to the subject of hypergeometry, and the theory has been since extended and simplified by various writers, notably by Eugenio Beltrami, professor at Pavia, born at Cremona in 1835, and by Hermann Ludwig Ferdinand von Helmholtz, professor at Berlin, born at Potsdam on August 31, 1821. The subject is so technical that I confine myself to a bare sketch of the argument from which the idea is derived. That a space of two dimensions should have the geometrical properties with which we are made familiar in the study of elementary geometry, it is necessary that it should be possible at any place to construct a figure congruent to a given figure, and this is so only if the product of the principal radii of curvature at every point in space or surface be a constant. There are three species of surfaces which possess this property, namely 1. Spherical surfaces where the product is positive, 2. Plane surfaces which led to Euclidean geometry where it is 0, and 3. What Beltrami has called pseudospherical surfaces where it is negative. Moreover, if any surface be bent without dilation or contraction, the measure of curvature remains unaltered. Thus these three species of surfaces are types of three kinds on which congruent figures can be constructed. For instance, a plane can be rolled into a cone, and the system of geometry on a conical surface is similar to that on a plane. These kinds of space of two dimensions are distinguished from one another by a simple test. Through a point of spherical space, no geodetic line, a geodetic line being defined as the shortest distance between 2 points, can be drawn parallel to a given geodetic line. Through a point of Euclidean or plane space, one and only one geodetic line, i.e. a straight line, can be drawn parallel to a given geodetic line. Through a point of pseudospherical space, more than one geodetic line can be drawn parallel to a given geodetic line, but all these lines form a pencil whose vertical angle is constant. It may be thought that we have a demonstration that our space is plane, since through a given point we can draw only one straight line parallel to a given straight line. This is not so, for it is conceivable that our means of observation do not permit us to say with absolute accuracy whether two lines are parallel. Hence, we cannot use this as a means to tell whether our space is plane or not. A better test can be deduced from the proposition that in any two-dimensional space of uniform curvature, the sum of the angles of a triangle, if it differ from two right angles, will differ by a quantity proportional to the area of the triangle. Hence it may happen possibly that although for triangles such as we can measure, the difference is imperceptible, yet for triangles which are millions of times bigger, there would be a sensible difference. If space be spherical or pseudospherical, its extent is finite. If it be plane, its extent is infinite. In regard to pseudospherical space, I should add that its extent may be infinite if it be constructed in space of 4 dimensions. In the preceding sketch of the foundations of non-Euclidean geometry, I have assumed tacitly that the measure of a distance remains the same everywhere. Klein has shown that if this be not the case, and if the law of the measurement of distance be properly chosen, we can obtain 3 systems of plane geometry analogous to the 3 systems mentioned above. These are called respectively elliptic, parabolic, and hyperbolic geometries. The above refers only to hyperspace of two dimensions. Naturally, there arises the question whether there are different kinds of hyperspace of three or more dimensions. Riemann shewed that there are three kinds of hyperspace of three dimensions, having properties analogous to the three kinds of hyperspace of two dimensions already discussed. These are differentiated by the test whether at every point no geodetical surfaces or one geodetical surface or a fasciculus of geodetical surfaces can be drawn parallel to a given surface, a geodetical surface being defined as such that every geodetic line joining two points on it lies wholly on the surface. I return now to Riemann's other investigations. In multiply periodic functions, it is hardly too much to say that he in his memoir in Bouchart's journal for 1857 did for the abelian functions what Abel had done for the elliptic functions, and it is this perhaps that will constitute one of his chief claims to future distinction. In the theory of numbers, Riemann's short tract of 8 pages on the number of primes which lie between two given numbers affords a striking instance of his analytical powers. Legendre had previously shewn that the number of primes less than n is very approximately n divided by the quantity log n minus 1.08366. But Riemann went further, and this tract and a memoir by Chebyshev contains nearly all that had been done, yet in connection with a problem of so obvious of a character that it has suggested itself to all who has considered the theory of numbers, and yet which overtax the powers even of Lagrange and Gauss. Among others than those already named, I may mention the following who have written on elliptic and abelian functions. Johann Georg Rosenhain, professor in Königsberg, born there on June 10, 1816, and died in 1887, who wrote in 1884 on the hyperelliptic double theta function and functions of two variables with 4 periods. Adolf Goepel, born at Rostock in September 1812 and died at Berlin in March 1847, who discussed hyperelliptic functions. See Krell's Journal, volume 35, 1847, pages 313 to 318. Karl Weierstrass, professor in Berlin, born at Ostenfeld on October 31, 1815, whose earlier researches related to the theta functions which he treated under a modified form in which they are expressible in powers of the modulus. At a later period he developed a method for treating all elliptic functions in a symmetrical manner, a process to which he was naturally led by his researches on the general theory of functions. In this theory, the theta functions are independent of the form of their space boundaries. Leopold Kronecker, who wrote on elliptic functions. Francesco Brioschi of Rome, who wrote on elliptic and hyperelliptic functions. Henry Smith, who discussed the transformation theory, the theta and omega functions, and certain functions of the modulus. Cayley, who was the first to work out in 1845 the theory of doubly infinite products and determine their periodicity, and who has written at length on the connection between the researches of Legendre and Jacobi. His later writings have dealt mainly with the theory of transformations and the modular equation. Cayley's collected works are now being issued by the University of Cambridge. The researches of Hermite are mostly concerned with the transformation theory, the higher development of the theta functions, and the connection between the methods and results of Weierstrass and Jacobi. The transformation of the double theta function has been also considered by Leo Königsberger, professor at Heidelberg, born in Prussia 1837. See his lectures published at Leipzig in 1874. The investigations of George Henri Haffan, an officer in the French army, born at Rouen on October 30, 1844, and died in Paris on May 21, 1889, are largely founded on Weierstrass's work. A sketch of Halphen's life and works given in Liouville's journal for 1889, pages 345 to 359, and in the Comptes Rendus, 1890, volume 110, pages 489 to 497. See also below, pages 481 to 482. Felix Christian Klein, born in 1849, now professor in Göttingen, has written on abelian functions, elliptic, modular functions, and hyperelliptic functions. Finally, H. A. Schwarz, formerly of Göttingen, now in Berlin, born 1845. H. W. Weber of Marburg, M. Nother of Erlangen, W. Stahl of Aix-la-Chapelle, F. G. Frobenius, now of Berlin and formerly of Zurich, and Glaisher have written on various branches of the theory, and Dr. Glaisher has in particular developed the theory of the zeta function. The textbook by Briot and Bouquet contains a clear account of the elliptic functions as it exists at present, developed from the point of view of the complex variable. Albert Briot was born at Saint Hippolyte in 1817, occupied a chair at the Sorbonne in Paris, and died in 1882. Jean-Claude Bouquet was born in 1819 and died in Paris in 1885. End of section 35 of A Short Account of the History of Mathematics by W. W. Rouseball. Recording by Paul King, Mississauga, Ontario. pjk.scripts.mit.edu/PKJ. Chapter 19, Part 3 of A Short Account of the History of Mathematics by W. W. Rouseball. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripts.mit.edu. A Short Account of the History of Mathematics by W. W. Rouseball. Chapter 19. Mathematics of Recent Times, Part 3. The consideration of algebraical, trigonometrical, elliptic, hyperelliptic, and other special kinds of functions paved the way for a theory of functions, which promises to prove a most important and far-reaching branch of mathematics. To a large extent, this is the work of living mathematicians, and therefore outside the limits of this chapter. I will content myself by referring to the following writers. First, I may mention Cauchy, who gave the general elementary theory of functions, and Liouville, who wrote chiefly on doubly periodic functions. Their investigations were extended and connected in the work of Briot and Bouquet, and further been developed by Hermite. Next, I may refer to the researches on the theory of algebraic functions which have their origin in Riemann's paper of 1850. Schwarz has established accurately certain theorems of which proofs given by Riemann were open to objection. Klein has connected Riemann's theory of functions with the theory of groups and have written on automorphic functions. Henri Poincaré, professor in Paris, born at Nancy in 1854, has also written on automorphic functions and on the general theory with special applications to differential equations. Finally, I may refer to the work of Weierstrass and Mittag-Leffler. Of these, Karl Weierstrass has created a large part of the modern theory of functions, and in particular has constructed the theory of uniform analytical functions. And Magnus Gustav Mittag-Leffler, born at Stockholm in 1846 and now professor there, has greatly developed the theory of analytical functions, a subject on which Hermite has also written. In connection with these researches, Paul-Émile Appel, professor in Paris, born at Strasbourg in 1858, C. Émile Picard of Paris, Edouard Goursat of Paris has written on special branches of the theory. As textbooks I may mention Dr. Forsyth's Theory of Functions of a Complex Variable, Cambridge, 1893, and Carl Neumann's Vorlesungen über Riemanns Theorie der Abschichten Integral, 2nd edition, Leipzig, 1884. The theory of numbers may be considered as a higher arithmetic, and the theory of elliptical and abelian functions as a higher trigonometry. The theory of higher algebra, including the theory of equations, has also attracted considerable attention, and was a favourite subject of study of the three mathematicians, Cauchy, Hamilton, and De Morgan, whom I propose to mention next, though the interests of these writers were by no means limited to this subject. Cauchy. The first of these mathematicians is the best representative of the French school of analysis in this century. Augustin Louis Cauchy, who was born in Paris on August 21st, 1789, and died at Sceaux on May 25th, 1857, was educated at the Polytechnic School, the nursery of so many French mathematicians of that time, and adopted the profession of a civil engineer. His earliest mathematical paper was one on polyhedra in 1811. Legendre thought so highly of it that he asked Cauchy to attempt the solution of an analogous problem which had baffled previous investigators, and his advice was justified by the success of Cauchy in 1812. Memoirs on analysis and the theory of numbers presented in 1813, 1814, and 1815 shewed that his ability was not confined to geometry alone. In one of these papers he generalized some results which had been established by Gauss and Legendre. In another of them he gave a theorem on the number of values which an algebraical function can assume when the literal constants it contains are interchanged. It was the latter theorem that enabled Abel to shew that in general an algebraic equation of a degree higher than the fourth cannot be solved by the use of purely algebraical expressions. To Cauchy and Gauss we owe the scientific treatment of series which have an infinite number of terms, and the former established general rules for investigating the convergency and divergency of such series. It is only a few works of an earlier date that contain any discussion as to the limitations of the series employed. It is said that Laplace, who was present when Cauchy read his first paper on the subject, was so impressed by the illustrations of the danger of employing such series without a rigorous investigation of their convergency that he put on one side the work on which he was then engaged and denied himself to all visitors, in order to see if any of the demonstrations given in the earlier volumes of the Mécanique Céleste were invalid. And he was fortunate enough to find that no material errors had been thus introduced. The treatment of series and of the fundamental conceptions of the calculus in most of the textbooks then current was based on Euler's works, and to any one trained to accurate habits of thought was not free from objection. It is one of the chief merits of Cauchy that he placed those subjects on a logical foundation. On the Restoration in 1816 the French Academy was purged, and, in spite of the indignation and scorn of French scientific society, Cauchy accepted a seat which was procured for him by the expulsion of Monge. He was also at the same time made professor at the Polytechnic, and his lectures there on algebraic analysis, the calculus, and the theory of curves were published as textbooks. On the Revolution in 1830 he went into exile and was first appointed professor at Turin, where he soon moved to Prague to undertake the education of the Comte de Chambord. He returned to France in 1837 and in 1848 and again in 1851 by special dispensation of the emperor was allowed to occupy a chair of mathematics without taking the oath of allegiance. His activity was prodigious, and from 1830 to 1859 he published in the Transactions of the Academy of the Comtes Rendus over 600 original memoirs and about 150 reports. In most of them the feverish haste with which they were thrown off is too visible, and many are marred by obscurity, repetition of old results, and blunders. Among the more important of his researches are the discussion of tests for the convergency of series, and the determination of the number of real and imaginary roots of any algebraic equation. His method of calculating these roots approximately, his theory of the symmetric functions of the coefficients of equations of any degree, his a priori evaluation of quantity less than the least difference between the roots of an equation, and his papers on determinants in 1841, which did a great deal to bring them into general use. Cauchy also did something to reduce the art of determining definite integrals to a science, but this branch of the integral calculus still remains without much system or method. The rule for finding the principal values of integrals was enunciated by him, and the calculus of residues was his invention. His proof of Taylor's theorem seems to have originated from a discussion of the double periodicity of elliptic functions. The means of shewing a connection between the different branches of a subject by giving imaginary values to independent variables is largely due to him. He also gives a direct analytical method for determining planetary inequalities of long period, and to physics he contributed a memoir on the quantity of light reflected from the surfaces of metals, as well as other papers on optics. Argand. I may mention here the name of Jean-Robert Argand, who was born at Geneva on July 22, 1768, and died circa 1825. In his essay, issued in 1806, he gave a geometrical representation of a complex number, and applied it to shew that every algebraic equation has a root. This was prior to the memoirs of Gauss and Cauchy on the same subject. But the essay did not attract much attention when it was first published. An earlier demonstration that the square root of -1 indicates perpendicularity due to Buet was published in the Philosophical Transactions for 1806, and the idea was foreshadowed in a memoir by H. Kuhn in the Transactions for 1750 of the St. Petersburg Academy. Hamilton. In the opinion of some writers, the theory of quaternions will be ultimately esteemed by one of the great discoveries of this century. The discovery is due to Sir William Rowan Hamilton, who was born of Scotch parents in Dublin on August 4, 1805, and died there on September 2, 1865. His education, which was carried out at home, seems to have been singularly discursive. Under the influence of an uncle who was a good linguist, he first devoted himself to linguistic studies. By the time he was 7 he could read Latin, Greek, French, and German with facility, and when 13 he was able to boast that he was familiar with as many languages as he had lived years. It was about this time that he came across a copy of Newton's Universal Arithmetic. This was his introduction to modern analysis, and he soon mastered the elements of analytical geometry and the calculus. He next read the Principia, and the 4 volumes then published of Laplace's Mécanique Céleste. In the latter he detected a mistake, and his paper on the subject, written in 1823, placed him at once in the front rank of mathematicians. In the following year he entered at Trinity College, Dublin. His university career is unique, for the chair of astronomy becoming vacant in 1827, while he was yet an undergraduate, he was asked by the electors to stand for it, and was elected unanimously, it being understood that he should be left free to pursue his own line of study. His earliest paper, written in 1823, was on optics, and was published in 1828 under the title of A Theory of Systems of Rays, which 2 supplements, written in 1831 and 1832, were afterwards added. In the latter of these the phenomenon of conical refraction is predicted. This was followed by a paper in 1827 on the principle of varying action, and in 1834 and 1835 by memoirs on a general method in dynamics, the subject of theoretical dynamics being properly treated as a branch of pure mathematics. His lectures on quaternions was published in 1852. Amongst his other papers I may specially mention one on the form of the solution of the general algebraic equation of the fifth degree, which confirmed the conclusion arrived at by Abel that it cannot be expressed in terms of the more elementary operations and functions. One on fluctuating functions, one on the hodograph, and lastly on the numerical solution of differential equations. His Elements of Quaternions were issued in 1866. Of this, a competent authority says that the methods of analysis there given shew as great an advance over those of analytical geometry as the latter shewed over those of Euclidean geometry. In more recent times the subject has been further developed by Tate. Hamilton was painfully fastidious on what he published, and he left an immense collection of manuscript books which are now in the library of Trinity College, Dublin, and some of which it is hoped will be ultimately printed. Grassmann. The idea of non-commutative algebras and of quaternions seemed to have occurred to Grassmann about the same time as to Hamilton. Hermann Gunther Grassmann, born at Stettin on April 15, 1809, and died there in 1877. He was a professor at the gymnasium at Stettin. His researches on non-commutative algebras are contained in his Ausdehnungslehre, first published in 1844 and enlarged in 1862. The scientific treatment of the fundamental principles of algebra initiated by Hamilton and Grassmann were continued by De Morgan and Boole, and subsequently was further developed by H. Hankel in his work on complexes, 1867, and by G. Cantor on his memoirs on the theory of irrationals, 1871. The discussion is however so technical that I am unable to do more than allude to it. Grassmann also investigated the properties of homoloidal hyperspace. De Morgan. Augustus De Morgan, born in Madura, Madras, in June 1806 and died in London on March 18, 1871, was educated at Trinity College, Cambridge, but in the then state of the law was, as a Unitarian, ineligible to a fellowship. In 1828 he became professor at the newly established University of London, which is the same institution as that now known as University College. There, except for 5 years from 1831 to 1835, he taught continuously till 1867, and through his works and pupils exercised a wide influence on English mathematicians of the present day. The London Mathematical Society was largely his creation, and he took a prominent part in the proceedings of the Royal Astronomical Society. He was perhaps more deeply read in the philosophy and history of mathematics than any of his contemporaries, but the results are given in scattered articles as well, which well deserve collection and republication. A list of these is given in his life, and I have made considerable use of some of them in this book. The best known of his works are the Memoirs of the Foundation of Algebra, Cambridge Philosophical Transactions, volumes 8 and 9, his treatise on the differential calculus published in 1842, a work of great ability and noticeable for the rigorous treatment of infinite series, and his articles on the calculus of functions on the theory of probabilities in the Encyclopaedia Metropolitana. The article on the calculus of functions contains an investigation of the principles of symbolic reasoning, but the applications deal with the solution of functional equations rather than with the general theory of functions. The article on the theory of probabilities gives a clear analysis of the mathematics of the subject to the time at which it was written. Besides those above named, I may mention the following who have written on the subjects of higher algebra, the theory of forms, and the theory of equations. Joseph Ludwig Rabe, who in 1832 discussed the test for the convergency of series, a subject also discussed later by Joseph Louis-François Bertrand, secretary of the French Academy, born in Paris in 1822, Kummer, Ulysse Dini of Pisa, and A. Pringsheim of Munich. And on the researches of the above writers see the Bulletin of the New York Mathematical Society, October 1892, pages 1 to 10. George Boole, born at Lincoln in November 2nd, 1815, died at Cork on December 8th, 1864, who invented a system of non-commutative algebra and from whose memoirs on linear transformations part of the theory of covariance has developed. Évariste Galois, one of the most original and powerful mathematicians of this century, born at Paris on October 26, 1811, and then killed in a duel on May 30th, 1832, at the early age of 20, whose writings are mainly concerned with the theory of equations and substitution groups. On his investigations, see Liouville's journal for 1846, volume 11, pages 381 to 444, and the American Journal of Mathematics for 1891, volume 13, pages 109 to 142. Carl Wilhelm Borchardt, professor in Berlin, born there on February 22nd, 1817, died there 1880, who in particular discussed generating functions in the theory of equations and arithmetic geometric means. A collected edition of his works, edited by G. Hettner, was issued at Berlin in 1888. Cayley, whose 10 classical memoirs on quantics, binary and ternary forms, and researches on non-commutative algebras, especially on matrices, will be found in the collected edition of his works. Sylvester. From among those whose numerous memoirs I may in particular single out, those on canonical forms, on the theory of contravariants, reciprocants of differential invariants, on the theory of equations, and that on Newton's rule, to which I may add that he has created the language and notation of considerable parts of the subjects on which he has written. Camille Jordan, who has written on the theory of substitutions in general and with special applications to differential equations. Sir George Gabriel Stokes, Lucasian professor in the University of Cambridge, born near Sligo on August 13, 1819, who has written on the critical values of the sums of the periodic series and on the summation of series. Cambridge Philosophical Transactions, 1847, volume 8, pages 533 to 583. See also below, pages 492 and 496. Eugene Netto of Strasbourg, who has written on substitutions. Hermite, who has in particular discussed the theory of associated contravariants in binary quantics, the theory of ternary quantics, and who has applied elliptic functions to the solution of the quintic equation. Enrico Betti of Pisa, who died in 1892, and Brioche, both of whom discussed binary quantics. Siegfried Heinrich Ehrenhold, born at Engerberg on July 16, 1819, who developed symbolic methods, especially in connection with ternary quantics. This was done concurrently with, but independently of, Cayley's work on the same subject. Paul Gordin, professor at Erlangen, who had discussed the theory of forms and shewed that there are only a finite number of concomitants of quantics. An edition of his work on invariants, determinants, and binary forms, edited by G. Kersteiner, was issued at Leipzig in 3 volumes, 1885, 1887, and 1893. Rudolf Friedrich Alfred Klebsch, born at Königsberg in 1833, died in Göttingen, where he was professor in 1872, who also independently investigated the theory of binary forms in some papers collected and published in 1871. An account of his life and works is printed in the Mathematische Annalen, 1873, volume 6, pages 197 to 202, and 1874, volume 7, pages 1 to 55. See also below. McMahon, who has written on the connection of symmetric functions, the derivation of invariants and the covariance from elementary algebra, and the concomitants of binary forms. Sophus Lie, professor at Leipzig, who has written on groups of continuous substitutions, differential invariants, and complexes of lines. Klein, who has investigated the problem of discontinuous substitutions in polyhedra groups. And lastly, Andrew Russell Forsyth, Fellow and Lecturer of Trinity College, Cambridge, born at Glasgow on June 18, 1858, who has developed the theory of invariance of differential equations, ternariants and quaternariants. No account of contemporary writings of this subject would be complete without a reference to the admirable textbooks produced by George Salmon, Provost at Trinity College, Dublin, born in 1819, in his Higher Algebra, and by Joseph Alfred Serret, professor at the Sorbonne in Paris on August 30, 1819, died in 1885, in his Cours d'Algèbre Supérieure, in which the chief discoveries of their respective authors are embodied. An admirable historical summary of the theory of the complex variable is given in the Vorlesungen über die komplexen Zahlen, Leipzig, 1867, by H. Henkel, professor at Tübingen, born at Halle in 1839 and died at Schramberg in 1873. Before mentioning the creators of modern synthetic geometry, it will be convenient to call attention to two other divisions of pure mathematics which have been greatly developed in recent years, but any sketch of the results arrived at or the methods by which they have been attained would be so closely connected with the work of living mathematicians that I shall do little more than mention the names of the subjects. Analytical geometry has been studied by a host of modern writers, but I do not propose to describe their investigations, and I shall content myself by merely mentioning the names of the following mathematicians. James Booth, born in the country of Leitrim on August 25, 1806, and died at Buckinghamshire on April 15, 1878, was one of the earliest writers in this century to devote himself to the development of analytical geometry. His chief results are embodied in his work entitled A Treatise on Some New Geometrical Methods. The researches of James McCulloch, professor in Dublin, born near Starbane in 1809 and died in Dublin in October 24, 1846, which include some valuable discoveries in the theory of quadrics, will be found in this collected works edited by Gellett and Houghton, Dublin 1880, see also below, page 496. Julius Plücker, professor after 1836 in Bonn, born at Elberfeld on July 16, 1801 and died at Bonn on May 22, 1868, devoted himself chiefly to the study of algebraic curves, of a geometry in which the line is the element in space, and the theory of congruences and complexes. His equations connecting the singularities of curves are well known. In 1847 he exchanged his chair for one of physics, and his subsequent researches were on spectra and magnetism. An account of his works was published by Klebsch, Gesellschaft der Wissenschaften, Göttingen, 1872, volume 16. The majority of the memoirs on analytical geometry by Cayley and by Henry Smith deal with the theory of curves and surfaces, the most remarkable of those of Ludwig Otto Hess, born at Königsberg on April 22, 1811, and died at Munich, where he was professor in 1874, are on the plane geometry of curves. See the notice of these by F. C. Klein. Of those of Jean-Gaston Darboux, professor in Paris, born at Nimes at 1842, on the geometry of surfaces, and those of Halphen on the singularities of surfaces and on tortuous curves. The singularities of curves and surfaces have also been considered by Hieronymus Georg Suthen, professor at Copenhagen, born in 1839, and by Hermann Caesar Hannibal Schubert, professor at Hamburg, born at Potsdam in 1848. The lectures of the latter have been published by F. Lindemann, 2 volumes, Leipzig, 1875 and 1891. Noether has discussed the theory of tortuous curves, and Klebsch has applied Abel's theorem to geometry. Among more recent textbooks are Klebsch's Vorlesungen über Geometrie, edited by F. Lindemann, and Salmon's Conic Sections Geometry of Three Dimensions, and Higher Plane Curves, in which the chief discoveries of these writers are embodied. Finally, I may allude to the extension of the subject matter of analytical geometry by the introduction of the ideas of space of n dimensions in the writings of Grossman in 1844 and 1862. Among those who have extended the range of analysis, including the calculus and differential equations, or whom it is difficult to place in any of the preceding categories, are the following, whom I place in alphabetical order: Appel, Bertrand, Boole, Cauchy, Darboux. Forsyth, who has written on Pfaff's problem and is also the author of the standard English treatise on differential equations. Frobenius, Lazarus Fuchs, professor at Berlin, born in Prussia 1833, Halphen, Jacobi, Jordan, Königsberger, Sophie Koloweski, professor at Stockholm, born on December 27, 1853 and died February 18, 1891. See the Bulletin des Sciences Mathématiques, volume 15, pages 212 to 220. Lie, Poincaré, Riemann, who wrote on the theory of partial differential equations, Schwarz, Sylvester, and Weierstrass, who has developed the calculus of variations. The writers I have mentioned above mostly concern themselves with analysis. I will next describe some of the more important works produced in this century on synthetic geometry. Modern synthetic geometry may be said to have had its origin in the works of Monge in 1800, Carnot in 1803, and Poncelet in 1822, but these only dimly foreshadowed the great extension it was to receive in Germany, of which Steiner and von Staudt are perhaps the best known exponents. Steiner. Jacob Steiner, the greatest geometrician since the time of Apollonius, was born at Utzendorf on March 18, 1796, and died at Bern on April 1, 1863. His father was a peasant, and the boy had no opportunity to learn reading and writing till the age of 14. He subsequently went to Heidelberg and thence to Berlin, supporting himself by giving lessons. His Systematische Entwicklungen was published in 1832. And at once made his reputation. It contains a full discussion of the principle of duality and of the projective and homographic relations of rows, pencils, etc., based on metrical properties. By the influence of Crell, Jacobi, and the von Humboldts, who were impressed by the power of his work, a chair of geometry was created for Steiner at Berlin, and he continued to occupy it till his death. The most important of his other researches are contained in papers which appeared originally in Crell's journal and are embodied in his Systematische Geometrie, Volume 1, edited by C. F. Geiser, Volume 2 by H. Schroeter. These relate chiefly to the properties of algebraic curves and surfaces, pedals and roulettes, and maxima and minima. The discussion is purely geometrical. Steiner's works may be considered as the classical authority on recent synthetic geometry. Von Staudt. A system of pure geometry quite distinct from that expounded by Steiner was proposed by Carl Georg Christian von Staudt, born at Rothenburg on January 24, 1798, and died in 1867, who held the chair of mathematics at Erlangen. In his Geometrie der Lage, published in 1847, he constructed a system of geometry built up without any reference to number or magnitude, but in spite of its abstract form, he succeeded by means of it alone in establishing the non-metrical projective properties of figures, discussed imaginary points, lines, and planes, and even obtained a geometrical definition of a number. These views were further elaborated in his Bertrand Géométrie de l'âge, 1856 to 1860. This geometry is curious and brilliant, and has been used by Kuhlmann as the basis of his graphical statistics. Among other works on pure geometry, I may refer to the Introduzione ad una teoria geometrica delle curve piane, 1862, and its continuation, Preliminari de una teoria geometrica delle superficie, by Luigi Cremona of the Polytechnic School at Rome. As usual, textbooks I may mention: M. Schalz's Traité de géométrie supérieure, 1852, J. Steiner's Vorlesungen über synthetische Geometrie 1867 and L. Cremona's Elemente Geometrie Projective, translated into English by C. Lusendorf, Oxford 1885, and Thomas Reyes, Géométrie de l'âge, 3 volumes, 3rd edition. I shall conclude the chapter with a few notes, more or less discursive, on branches of mathematics of a less abstract character and concerned with problems that occur in nature. Closely connected with the subject of modern geometry is the science of graphics, in which rules are laid down for solving various problems by the aid of the drawing board. The modes of calculation which are permissible are considered in modern projective geometry. This method of attacking questions has been hitherto applied chiefly to problems in mechanics, elasticity, and electricity, and it is especially useful in engineering, and in that subject an average draftsman ought to be able to obtain approximate solutions of most of the equations, differential or otherwise, with which he is likely to be concerned, which will not involve errors greater than would have to be allowed for in any case in consequence of our imperfect knowledge of the structure of the materials employed. The theory may be said to have originated with Poncelet's work, but I believe that it is only within the last 20 years that systematic expositions of it have been published. Among the best known of such works I may mention are Graphische Statik by C. Kuhlmann, Zurich, 1875, recently edited by W. Ritter, and the Lezioni di Statistica Grafica by A. Favaro, Padua, 1877, French translation annotated by P. Terrier in 2 volumes 1879 to 85, and the Calcolo Grafico by L. Cremona, Milan, 1879, English translation by T. H. Beer, Oxford, 1889, which is largely founded on Mobius's work. La Statique Graphique by M. Levy, Paris, 4 volumes, 1886 to 88, and La Statistica Grafica by C. Cerotti, Milan, 1888. The general character of these books will be sufficiently illustrated by the following note on the concepts of Kuhlmann's work. Kuhlmann commences with a description of the geometrical representation of the 4 fundamental processes of addition, subtraction, multiplication, and division, and proceeds to evolution and involution, the latter being effected by the use of equiangular spirals. He next shews how the quantities considered, such as volumes, moments, and moments of inertia, may be represented by straight lines, thence deduces the laws for combining forces, couples, etc., and then explains the construction and use of the ellipse and ellipsoid of inertia, the neutral axis, and the kern. The remaining and larger part of the book is devoted to shewing how geometrical drawings made up on these principles give the solutions of many practical problems connected with arches, bridges, frameworks, earth pressure on walls and tunnels, etc. The subject has been treated during the last 20 years by numerous writers, especially in Italy and Germany, and applied to a large number of problems. But as I stated at the beginning of this chapter, that I should as far as possible avoid discussions of the works of living authors, I content myself with a bare mention of the subject. End of section 36. Recording by Paul King, Mississauga, Ontario. pjk.scripts.mit.edu/pkj.
Chapter 19, Part 4 of A Short Account of the History of Mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripts.mit.edu/pkj. A Short Account of the History of Mathematics by W. W. Rouse Ball. Chapter 19. Mathematics of Recent Times, Part 4. Clifford. I may, however, add here a brief note on Clifford,
who was one of the earliest English mathematicians of the latter half of this century to advocate the use of graphical and geometrical methods in preference to analysis. William Kingdon Clifford, born at Exeter on May 4, 1845, and died at Madeira on March 3, 1879, was educated at Trinity College, Cambridge, of which society he was a fellow. In 1871 he was appointed Professor of Applied Mathematics at University College London, a post which he retained till his death. His remarkable felicity of illustration and power of seizing analogies made him one of the most brilliant expounders of mathematical principles. His health failed in 1876, when the writer of this book undertook his work for a few months. Clifford then went to Algeria and returned at the end of the year, but only to break down again in 1878. His most important works are his theory of biquaternions, on the classification of loci, unfinished, and the theory of graphs, unfinished, his canonical dissection of a Riemann surface, and the elements of dynamic also contain much interesting matter. I next turn to the question of mechanics treated analytically. The knowledge of mathematical mechanics of solids attained by the great mathematicians of the last century may be said to be summed up in the admirable Mécanique analytique by Lagrange and Traité de mécanique by Poisson, and the application of the results to astronomy is illustrated by Laplace's Mécanique céleste. These works have been already described. The mechanics of fluids is more difficult than that of solids, and the theory is less advanced. Theoretical statics, especially the theory of potential and attractions, has received considerable attention from mathematicians of this century. I have already mentioned that the introduction of the idea of the potential is due to Lagrange, and it occurs in a memoir of a date as early as 1773. The idea was at once grasped by Laplace, who, in his memoir of 1784, used it freely, and to whom the credit of the invention was formerly, somewhat unjustly, attributed. In the same memoir, Laplace also extended to space of 3 dimensions the idea of circular harmonic analysis, which had been introduced by Legendre in 1783. Green. George Green was one of the earliest writers of this century who investigated further the properties of the potential. Green was born near Nottingham in 1793 in a humble condition in life, and died at Cambridge in 1841. Although self-educated, he contrived to get access to various mathematical books, and in 1827 wrote a paper on the potential, in which the term was first introduced, proved its chief properties, and applied the results to electricity and magnetism. This contains the important theorem now known by his name. This remarkable paper was seen by some neighbors who were able to appreciate the power shewn in it. It was published by subscription in 1828, but does not seem to have attracted much attention at first. Similar results were independently established in 1839 by Gauss, to whom their general dissemination was due. In 1832 and 1833, Green presented papers to the Cambridge Philosophical Society on the equilibrium of fluids and on attractions in space of n dimensions, and in the latter year his memoir on the motion of a fluid agitated by the vibrations of a solid ellipsoid was read before the Royal Society of Edinburgh. In 1833 he entered at Caius College, Cambridge, and was subsequently elected to a fellowship. He then threw himself into original work, and produced in 1837 his paper on the motion of waves in a canal, and on the reflection and refraction of sound and light. In the latter, the geometrical laws of sound and light are deduced by the principle of energy from the undulatory theory, the phenomenon of total reflection is explained physically, and certain properties of the vibrating medium are deduced. He also discussed the propagation of light in any crystalline medium. Of Gauss's work on attractions I have already spoken. The theory of level surfaces and lines of force is largely due to Chasles, who also determined the attraction of an ellipsoid at any external point. I ought not to leave the subject of theoretical statics without mentioning Mobius. August Ferdinand Mobius, professor at Leipzig, who was born at Schulpforta on November 17, 1790, and died on September 26, 1868, was one of the best known of Gauss's pupils. He published his Barycentrisches Calcul in 1826. His collected works were published at Leipzig in 4 volumes, 1885 to 1887. Among living writers I may allude to Sir Robert Stawell Ball, Lowndean professor in the University of Cambridge, born in Dublin on July 1, 1840, who issued his Theory of Screws in 1876. Theoretical dynamics has been studied by most of the writers above mentioned. In addition to these, I may repeat that the principle of varying action was elaborated by Sir William Hamilton in 1827, and the Hamiltonian equations were given in 1835, and I may call attention to Bertrand's work on dynamics. The use of generalized coordinates introduced by Lagrange has become the customary means of attacking dynamical as well as many physical problems. The standard English textbook on the dynamics of rigid bodies is that by Dr. Rouse. On the mechanics of fluids, liquids, and gases, apart from the physical theories on which they rest, I propose to say nothing except to refer to the memoirs of Green, Sir George Stokes, Lord Kelvin, better known as Sir William Thomson, and von Helmholtz. The fascinating but difficult theory of vortex rings is due to the 2 writers last mentioned. One problem in it has been also considered by J. Thomson, but it is a subject which is as yet rather beyond our powers of analysis. The subject of sound may be treated in connection with hydrodynamics, but on this I would refer the reader who wishes for further information to the work published at Cambridge in 1877 by Lord Rayleigh, recently Cavendish Professor in the University of Cambridge. Theoretical astronomy is included in, or at any rate closely connected with, theoretical dynamics. Among those who in this century have devoted themselves to the study of theoretical astronomy, the name of Gauss is one of the most prominent. To his work I have already alluded. Bessel. The best known of Gauss's contemporaries was Friedrich Wilhelm Bessel, who was born in Minden on July 22, 1784, and died at Königsberg on March 17, 1846. Bessel commenced his life as a clerk on board ship, but in 1806 he became an assistant in the observatory at Lilienthal, and was thence in 1801 promoted to be director of the new Prussian observatory at Königsberg, where he continued to live during the remainder of his life. Bessel introduced into pure mathematics those functions which are now called by his name. This was in 1824, though their use is indicated in a memoir 7 years earlier, but his most notable achievements were the reduction, given in his Fundamenta Astronomiae, Königsberg 1818, of the Greenwich observations by Bradley of 3,222 stars, and his determination of the annual parallax of 61 Cygni. Bradley's observations have been recently reduced again by Dr. A. Auwers of Berlin. Leverrier. Among the astronomical events of this century, the discovery of the planet Neptune by Leverrier and Adams is one of the most striking. Urbain Jean-Joseph Leverrier, the son of a petty government employee in Normandy, was born at Saint-Lô on March 11, 1811, and died at Paris on September 23, 1877. He was educated at the Polytechnic School, and in 1837 was appointed as lecturer on astronomy there. His earliest researches in astronomy were communicated to the Academy in 1839. In these he calculated, within much narrower limits than Laplace had done, the extent within which the inclinations and eccentricities of the planetary orbits vary. The independent discovery in 1846 by Leverrier and Adams of the planet Neptune, by means of the disturbance it produced on the orbit of Uranus, attracted general attention to physical astronomy, and strengthened the opinion as to the universality of gravity. In 1855 Leverrier succeeded Arago as director of the Paris Observatory, and reorganized it in accordance with the requirements of modern astronomy. He now set himself the task of discussing the theoretical investigations of the planetary motions, and of revising all tables which involve them. He lived just long enough to sign the last proof sheet of this work. Adams. The co-discoverer of Neptune was John Couch Adams, who was born in Cornwall on June 5, 1819, educated at St. John's College, Cambridge, subsequently appointed to Lowndean professor in the university, and director of the observatory, and who died at Cambridge on January 21, 1892. There are three important problems which are especially associated with the name of Adams. The first of these is his discovery of the planet Neptune from the perturbations it produced on the orbit of Uranus. In point of time, this was slightly earlier than Leverrier's investigation. The second memoir to which I referred was on the secular acceleration of the moon's mean motion. Philosophical Transactions, 1855, volume 143, page 377. Laplace had calculated this on the hypothesis that it was caused by the eccentricity of the Earth's orbit, and had obtained a result which agreed substantially with the value it deduced from a comparison of the records of ancient and modern eclipses. Adams shewed that certain terms in an expression had been neglected, and that if they were taken into account the result was only about one-half that found by Laplace. The correctness of the calculations of Adams was denied by Plana, Pontécoulant, and other continental astronomers, but Delaunay in France and Cayley in England verified the work. The third investigation connected with the name of Adams is his determination of the orbit of the Leonids, or shooting stars, which were especially conspicuous in November 1866, and whose period is about 33 years. Newton of Yale had shewn that there were only 5 possible orbits. Adams calculated the disturbance which would be produced by the planets on the motion of the node of the orbit of a swarm of meteors in each of these cases, and found that this disturbance agreed with the observations for one of the possible orbits, but for none of the others. Hence the orbit was known. Other well-known astronomers of this century are Giovanni Antonio Amadeo Plana, born at Voghera on November 8, 1781, and died at Turin on January 20, 1864, whose work on the motion of the moon was published in 1832. Philip Gustave Dulcet, Count Pontécoulant, born in 1795 and died at Pontécoulant on July 21, 1871. Charles Eugène Delaunay, born at Lausigny on April 9, 1816, and drowned off Cherbourg on August 3, 1872, whose work on the lunar theory indicates the best method yet suggested for the analytical investigations of the whole problem, and whose incomplete lunar tables are among the astronomical achievements of this century. And Peter Andrew Hansen, born at Schleswig on December 8, 1795, and died at Gotha, where he was head of the observatory on March 28, 1874, who compiled the lunar tables published in London in 1857, and celebrated the most delicate methods yet known for the determination of lunar and planetary perturbations. For an account of his numerous memoirs, see the Transactions of the Royal Society of London for 1876 to 1877. Among living mathematicians I may mention the following names. Félix Tisserand of Paris, born in 1845, whose Mécanique Céleste forms a worthy pendant to Laplace's work of the same title. George William Hill, born in New York in 1838 and until recently on the staff of American Ephemeris, who in 1884 determined the inequalities of the moon's motion due to the non-spherical figure of the Earth, an investigation which completed Delaunay's lunar theory. Hill also dealt with the secular motion of the moon's perigee and the motion of a planet's perigee under certain conditions, and he has written on the analytical theory of the moon of Jupiter and Saturn with a view to the preparation of tables of their positions at any given time. Simon Newcomb, born in Nova Scotia on March 12, 1835, superintendent of the American Ephemeris, who re-examined the Greenwich observations from the earliest times, applied the result to the lunar theory, and revised Hansen's tables. George Howard Dowron of Trinity College, Cambridge, born in Kent in 1845, now Plumian professor in the University of Cambridge, who has written on the effect of tides on viscous spheroids, the development of planetary systems by means of tidal friction, the mechanics of meteoric swarms, etc. Perhaps also I may here mention Poincaré, who has discussed the difficult problem of three bodies and the form assumed by a mass of fluid under its own attraction. Within the last half-century, the results of spectrum analysis have been applied to determine the constitution and directions of motions of the heavenly bodies to and from the Earth. The early history of spectrum analysis will be always associated with the names of Gustav Robert Kirchhoff and A.J. Angstrom of Uppsala and Sir George Stokes of Cambridge, but it pertains to optics rather than to astronomy. Within the last few years, the range of astronomy has been still further extended by the art of photography. To what new developments this may lead, it is as yet impossible to say. Mathematical physics. An account of the history of mathematics in this century would not be other than misleading if there were no reference to the application of it to numerous problems in heat, elasticity, light, electricity, and other physical subjects. The history of mathematical physics is, however, so extensive that I could not pretend to do it justice even were its consideration properly included in a history of mathematics. Moreover, it is so closely connected with the works of living physicists, notably of von Helmholtz and of Lord Kelvin, better known as Sir William Thomson, that I may consider it outside the limits I have laid down for myself in this chapter. It is, however, interesting to note that the advance in our knowledge of physics is largely due to the application to it of mathematics, and every year it becomes more difficult for an experimenter to make any mark on the subject unless he is also a mathematician. Amongst recent writers on mathematical physics, excluding all reference to experimental physics, as also to theories to which mathematical analysis has not yet been applied, I may specially mention the following, whose names are here arranged alphabetically, though the list does not in any way profess to be complete or exhaustive. J. Boussinesq of Paris, who has written on optics. Ludwig Boltzmann of Vienna, whose writings greatly extended the kinetic theory of gases, and have done something to bring the molecular physics within the domain of mathematics. Rudolf Julius Emanuel Clausius, born at Köslin on January 2, 1822, and died at Bonn, where he was professor of physics in August 1888, who was among the earliest to discuss the subject of heat from a mathematical point of view. Klebsch, who discussed the elasticity of solid bodies. Julius Wilhelm Richard Dedekind, who is the author of a remarkable memoir on the vibrations of a liquid ellipsoid, which is treated as a problem in pure mathematics. Michael Faraday, born at Newington on September 22, 1791, and died at Hampton Court on August 25, 1867, who had a special gift in deducing results by general reasoning from fundamental principles, and in disentangling those principles from the symbols in which they are usually expressed. For further details, see the biographies of Tyndall, 2nd edition 1870, Bence-Jones 1870, or Dr. Gladstone 1872. George Francis Fitzgerald, professor in Dublin, born there on August 3, 1851, who has written on electromagnetism and optics. John Bernard Léon Foucault, born at Paris on September 18, 1819, and died there of paralysis on February 11, 1868, whose chief memoirs were on the predictability of photography, 1840, on the electric lamp, 1849, on the determination of the velocity of light in 1850, but repeated with improvements in 1862, on his demonstration of the diurnal motion of the earth by means of the rotation of the plane of oscillation of a simple pendulum, 1851, on the gyroscope, 1852, on the rotation of a copper disc between the poles of a magnet, 1855, and on a polarizer, 1857. For further details, see La vie et travaux de Léon Foucault by J. A. Lycejus, Paris, 1875, and also a notice by J. Bertrand, preface to the collected edition of Foucault's works, Paris, 1878. J. Willard Gibbs of Yale, America, who has written on the thermodynamics and Maxwell's electromagnetic theory. Richard Tetley Glazebrook of Trinity College, Cambridge, born at Liverpool on September 18, 1854, who has written on optics and electricity. His report in the Transactions of the British Association, 1885, on theories of optics, contains a valuable summary of most of the mathematical researches on that subject during this century and prior to the date of the report. After a brief allusion to the views of Green, Cauchy, McCulloch, and F. E. Newman, he describes the more recent work according as it comes under the simple elastic solid theory, or theories assuming an action between matter and ether, or Maxwell's electromagnetic theory. Green, whose physical memoirs were mostly on the theory of waves. Von Helmholtz, who is in the front rank of all departments of mathematics and physics. His collected papers were published in 2 volumes, Leipzig, 1882 to 1883. Oliver Heaviside, who has written on the mathematical theories of optics and electromagnetism. Lord Kelvin, or Sir William Thomson, professor at Glasgow, born at Belfast, June 1824, who has enriched every department of physics by his researches. His collected papers were published at Cambridge, Volume 1 in 1882, and Volume 2 in 1884, and Volume 3 in 1890. Gustav Robert Kirchhoff, professor in physics, first at Heidelberg and then at Berlin, born at Königsberg on March 12, 1824, and died in Berlin October 17, 1887, whose name will always be associated with the history of spectrum analysis and his researches on elasticity. His collected papers were published at Leipzig in 1882. Gabriel Lamé, born at Tours on July 22nd, 1795, and died at Paris in 1870, where he was professor at the Polytechnic School, whose best-known works are his Course on Physics, 1836, his Treatise on Elasticity, 1852, his work on Functions, 1857, an essay on the curvilinear coordinates, 1859, and lastly his Theory of Heat, 1861. He also wrote memoirs on different points in the theory of numbers. James Clerk Maxwell, born at Edinburgh on June 13, 1831, and died at Cambridge on November 5, 1879, where he was professor of experimental physics. His most important works were his memoir in 1859 on the stability of Saturn's rings, various articles on color, his memoir on the electromagnetic field, his Electricity and Magnetism issued in 1873, his Theory of Heat published in 1871, and his elementary textbook on matter and motion. To these I may add his memoir on reciprocal figures, which are useful in graphics, and his papers on molecular theory of gases and cognate subjects. His Electricity and Magnetism has revolutionized the treatment of the subject. Poisson and Gauss had explained the phenomenon of electrostatics by attraction and repulsions between imponderable particles, while Lord Kelvin, Sir William Thomson, in 1846 has shewn that the effects might be supposed analogous to a flow of heat from various sources of electricity properly distributed. In electrodynamics, the theory then generally current was that proposed by W. E. Weber, in which the attraction between electrified particles depends on their relative motion and position. Maxwell rejected all these hypotheses and explained the phenomenon by stresses and motions of a material medium. He concluded by shewing that if the medium were the same as the so-called luminiferous ether, the velocity of light would be equal to the ratio of the electromagnetic and electrostatic units. Subsequent experiments have tended to confirm this conclusion. For fuller details, his collected works, Cambridge, 2 volumes, 1890, and his Life by L. Campbell and W. Garnett, London, 1882, may be consulted. McCulloch, who wrote on physical optics. Franz Ernst Neumann of Königsberg, born at Uckermark on September 11, 1798, who wrote on elasticity and light. William John Rankine of Glasgow, born at Edinburgh on July 5, 1820, and died December 24, 1872, whose discoveries in thermodynamics and hydromechanics will be found in the collected edition of his works issued in London in 1881. Lord Rayleigh, born on November 12, 1842, who, besides some classical papers on the mathematics of physical optics, has written the standard English work on sound, published at Cambridge in 1877. Barré de Saint-Venant, whose researches on elasticity and torsion are well known. Sir George Gabriel Stokes, most of whose papers on hydromechanics or optics or allied subjects, these memoirs have been recently collected and published by the University of Cambridge. Peter Guthrie Tait, professor in Edinburgh, born at Dalkeith on April 28, 1831, who has written on the mathematics of various physical subjects, and especially on the molecular theory of gases. Joseph John Thomson, of Trinity College and Cavendish professor in the University of Cambridge, born at Manchester on December 18, 1856, who has written on vortex rings and the application of generalized coordinates to various physical problems. I may also allude to his report on the Transactions of the British Association, 1885, on electric theories, which he classifies into those not founded on the principle of conservation of energy, such as those of Ampere, Grassmann, Stefan, and Korteweg, those which rest on assumptions concerning the velocities and positions of electrified particles, such as those of Gauss, W. E. Weber, Riemann, and Clausius, those which require the existence of a kind of energy of which we have no other knowledge, such as the theory of C. Neumann, those which rest on the dynamical considerations but in which no account is taken of the action of the dielectric, such as the theory of F. E. Newman; and finally those which rest on the dynamical considerations and in which the action of the dielectric is considered, such as Maxwell's theory. In the report these theories are described, criticized, and compared with the results of experiments. Wilhelm Eduard Weber died in 1891, whose most important investigations were in connection with electrodynamics. His works are being produced by the Royal Society of Göttingen, Volume 1, edited by W. Voigt, Berlin, 1892. And Gustav Heinrich Wiedemann of Bâle, born October 2nd, 1826, who is the author of an admirable textbook on electricity and allied subjects, 4 volumes, 1882 to 1885. I am well aware that the above list excludes many who have studied physics from a strictly mathematical point of view, and I give it not as an account of a contemporary work, but as a pendant to this chapter, which may serve as an indication of the subjects discussed by many mathematicians in recent times, illustrated by the names of a few of them. To make it more than this would involve the knowledge to which I can make no pretense. End of Part 37. Reading by Paul King, Mississauga, Ontario. pjk.scripps.mit.edu/pkj. This is the end of a short account of the history of mathematics by W. W. Rouse.